may have seen, we've got a very packed agenda today. Slots are 12 minutes long, so to the speakers, I'll be sitting up here. I'll give you a warning at 2 minutes, and that's a sign to wrap up. We'll try to stay on time so that we can enjoy the coffee break and make it to lunch on time as well. I want to start giving a very brief working group update. The first update is that we have a new co-chair, Dylan Amaya, who is formerly NOAA scientist, now transitioning to North Carolina State University. So welcome to Dylan, and thanks to Kathy Pejan for her service as a working group co-chair. One update that I wanted to make everyone aware of is that we have now compiled a large set of CESM2 initialized prediction data sets spanning timescales from subseasonal all the way out to multi-decadal. And we've now set up GDEX repos for all of these initialized prediction data sets. Some of the newest repos are not yet filled with data, but they will be soon. And you can check for updates at the Earth System Prediction Working Group webpage, which you can get by just Googling. And then I wanted to mention ongoing activity in the working group. So we've got a new allocation. How are we spending that? Well, we're supporting the SPAT land atmosphere interaction experiments. We'll hear about some of that work from Judith and Meg today. As you saw in Dave's overview talk, we're starting to do CESM3 initialized prediction smoke tests and finding that things are smoking. So we'll be doing a lot more development on that before we get to production runs. And then the other thing the working group is supporting are coordinated dynamical pacemaker experiments in support of the Decadal Climate Prediction Project of protocol for CMIP7. Evan Meeker will be presenting a little bit on this effort. The idea here is that we want to come up with a way to probe coupled response to internal modes of variability like the NAO, the elution low, and SAM forcing to explore things like we published in 2023, where we found that the high-resolution decadal prediction system with CESM showed improved performance because we showed that the high-resolution ocean had a different heat transport trend in response to SAM compared to the low-res, opposite sign heat transport trend in the Southern Ocean. So groups are interested in this and want to probe this without having to run a very expensive initialized prediction decadal hindcast set. So these are the ongoing activities in the working group, and if you have any questions about these, come and see me. With that, we'll turn it over to Judith to kick us off.
Thank you so much. Good morning. I will just give a brief overview of some of the state-dependent predictability in subseasonal to seasonal forecasts over North America experiment we have done. So the motivation is subseasonal to seasonal forecasts are a challenging forecast timescale because the memory from the initial conditions of the atmosphere have been lost. And so you're relying on the other components like the ocean and the land, as well as some sort of internal dynamical modes like the Madden-Julian oscillation, et cetera, to give you predictability. We're having this subseasonal to seasonal hindcast suite, which covers about 20 years weekly initialization that Steve alerted to. And as part of this initiative on land atmosphere interaction, we also have repeated this with MPAS. One of the plenary talks was the introduction of MPAS, which is the model for prediction across the scales. It's developed as a weather prediction model rather than a climate prediction model. And so the subseasonal timescale is an interesting time range where we can see, how do these models perform on this timescale? And are the weather or the climate models better? You do need, in taller modes, you need teleconnections for subseasonal to seasonal prediction, but we also wonder to which degree having a better representation of weather processes can help on those timescales. So here in particular, we look at state-dependent skill. So we condition the system at initial time on different large-scale indices. This is the North Atlantic Oscillation, the Pacific and North American Pattern, ENSO, and the Madden-Julian Oscillation. So we are looking here at different suites. One is CSM2, initialized from ERA 5 initial conditions. One of our forecasts at Heimkept is initializing from NSEP initial conditions, but because MPAS is from ERA 5, we repeated that suite. We have MPAS A. So CSM is fully coupled. MPAS A has a prescribed ocean. And then we're also rerunning CAM6 with a prescribed ocean so that we can look at the atmosphere-only S2S hindcasts as opposed to the coupled ones. The S2S protocol I had alerted to, and we're looking mostly here in this talk because there's not much time at anomaly correlation coefficient after removing the Lita-independent bias. So here on the left side, this is a plot similar to what Gretchen showed in the plenary talk. However, it's a different subset of models. So we look at biweekly average temperatures in 2 meter for weeks 1, 2 on the left, 3, 4 in the middle, and 5, 6 on the right side. The first one is CSM initialized from NSEP forecasts, CFS V2, then from ERA 5, so different atmospheric initial conditions. And then we have 2 simulations, MPAS at 60 kilometers and at 120 kilometers. And so what we see is all these models, the typical things. The skill is initially in the extratropics, and for the longer lead time, the regions of most skills move to the tropics, which have a longer predictability. And we see sort of, to first view, that these models have all fairly similar skill. On the bottom right, it's just a global average, and now we can slice and dice this a bit more. For example, we can see that, yes, resolution brings you something. So MPAS at 60 kilometers in red is always better than at 120 kilometers. Next, we want to look at state dependence. So it's been known for a long time that there are statistical correlations. So ENSO is statistically changing your flow over North America. However, that this really has been verified in initial predictions, to my knowledge, started with this paper by Ferrante et al. In 2015, and she showed that if you had the initial state projects on the negative NAO, you have about 2 more days of predictability. And there has been a number of work after this under the S2S WMO project. For example, the one by Stan et al., who looked at the anomalies over the northern hemisphere, temperature anomalies in different MJO phases. Here I'm not looking at the actual anomaly states, but the anomaly correlation. So I'm really asking, where do we have increased predictive skill if we at initial conditions are in a particularly low frequency regime or in a tropically coupled regime? So here's the results of CSM2. These are week 3-4 forecasts, and in the middle is the skill at week 3-4 in the neutral cases. If I would show you all cases, it would be very similar. And so then we subselect the forecasts that initial state project on the negative PNA on the left top and the negative ENSO on the bottom one. And we see if we are in the negative PNA, we have a lot more predictive skill over CONUS than for the neutral state. If we're in the positive state, there's a region of increased predictability over, I'm going to call this Northeast Canada. And so in the ENSO states, we also see these regions of enhanced predictability. Now, if we take the mean over this, a lot of this will average out. So part of the findings of this study is that we really need to look at regional skill because of the teleconnection patterns and the regions where this skill increases is really highly regional. And so Europe and North America to first degree have the same landmass. And so if we look at these averages, we might miss some of these signals. And then we can do more things. We can here associate on a negative condition on the negative PNA and ENSO, and a negative ENSO, which is La Nina, and a positive ENSO pattern on the right, and a positive PNA. And so now we really end up having some regions that pop out as having increased skill for ENSO. It's the West Coast, and then also sort of Northeast Canada. Just to have a quick look how this looks across different models. So here's ESMWF on the top, CSM2, CAM6, and MPAS. So the first two are coupled models. The second two rows are with prescribed SSTs. And there's a lot of time, there's a lot of details you can look at. I would say to first glance, we do see regions with where there is consistency across the different models. For example, for the negative PNA, we see this increased predictive skill all along the East Coast. I also want to say this is the first time that somebody has looked at MPAS, at teleconnection patterns. So I think in some ways we can still consider this as preliminary results, because this has been really developed as a weather model, and teleconnections pattern is not something MPAS is tuned for. Whereas the climate models, we definitely want to have good climate variability in teleconnections. So people have looked at these for many times. This is the same, but based on MJO. Here, I'm just picking the neutral phase in the middle. This is just when the MJO amplitude, as measured by the RMM, is pretty small. On the left side is phase 3-4, and on the right phase 7-8. This is also known. We have increased predictability in phases 7-8 over North America. Where there is actually decreased connectivity over the convective activity over the Indian Ocean MJO region, and then we have decreased predictability in phases 3-4 when there is, compared to the neutral state, when there is a lot of activity, and this is because of this extratropical Rossby wave train. It is very active, so it's harder to predict. But again, the regional corrector pops out. 2 minutes. This is my conclusions. So we looked at this across different models and different states. You have to zoom in for each metric. We find that the strongest skill increase is associated with the positive and a negative PNA phase, but for different regions. And our results highlight the regionality of the state-dependent S2S forecast skill. And they point to a possible greater regional S2S skill than previously assumed. This is just, we also look at this in S2S simulations with an emulator that has been developed here at ENCA, which is Chemulator. This is at the very beginning. And these are my conclusions. So we're looking at state-dependent predictability across different MPAS models, NCAR model, MPAS, and CSM, and compare these to ESMWF. We see that there is increased regional subseasonal skill than maybe assumed. And I also wanted to just say, we also looked in the same data sets for perfect model and where predictive skill is coming from. And we find that in perfect model scenarios, the leading source of S2S predictability actually comes from the land. Thank you so much.
It's on? Okay. So in your second or third slide, you showed the globally average ACC skill across 4 configurations. And from a distance, the skill seems very similar across those. Is that surprising or expected? The differences are only a few percent.
Yes, I think that's a very good point. Yes. So I think it is, well, so What do you think? So,
Well,
I mean,
what
we
do we-
know
yeah.
that the details of the initial conditions of the atmosphere probably only play a large role for weeks 1, 2. And we do know that the skill moves from the extratropics to the tropics, and we understand that from spread error and variability, RMS error perspectives for 2 meter temperature. For precipitation, that would look just the opposite. Precipitation is predictable. I'm taking this back. The RMS error is opposite, not the skill. So I think this speaks to the fact that our models are actually pretty good at predicting low frequency variability.
Thank you.
Okay, we need to move on to our next speaker, who is Meg Fowler.
No, you're fine. All right, good morning, everyone. Thanks for being here today. I realize it's a tough choice this morning between AI and machine learning and predictability, but clearly you made the right one. So I wanted to take some time this morning to talk about work we're doing as part of SPAT. That's the Earth System Predictability Across Timescales initiative led by Jager Richter. And what we're looking at builds nicely on Judith's talk, where we're looking at the influence of soil moisture on subseasonal to seasonal, or S2S, temperature predictability over the United States. And I want to take a minute before I start and acknowledge a growing list of co-authors on this work, including Judith, Jager. I'd like to also shout out Abby J. and Sasha Glanville for running a lot of the simulations that I'll show you today. So whenever I start a talk on land-atmosphere interactions, I like to throw an insanely complicated figure at the audience and look at your faces. One of the things to point out with land-atmosphere interactions is that it is a complicated problem. The way that the surface interacts with the atmosphere really happens through soil moisture anomalies here at the bottom. Those drive changes in surface fluxes, so sensible heat flux, moisture flux, including transpiration from vegetation, and all of that then feeds into the very noisy atmosphere that exists above land. Things like turbulence, entrainment, precipitation, cloud cover, solar radiation, etc. JK, we have a technical thing? Seeing your presentation for some reason.
Oh, they're missing out.
Sorry about that.
No worries. Perfect. Awesome. So the way that the land surface interacts with the atmosphere really happens through these soil moisture anomalies. And one of the fun things to note is that it doesn't just impact daily fluxes and cloud cover, it can even impact things like extremes, droughts, and floods. And the reason this all matters for this group is that land-based memory is important on subseasonal timescales. So when you think about how long soil moisture anomalies might persist, it could occur on the order of weeks to months. And one of the kind of main milestone studies that looked at this was Randy Koster's paper in 2011, looking at Glass A2. What you're seeing here is the skill gained in forecasts when you have realistic land initial condition versus not having realistic land initial conditions, looking at precipitation skill on the left and air temperature skill on the right. And one thing to note is that prediction skill gained from land, this left column, mostly not a lot. Precipitation is really noisy, and as you noticed from the last figure, hopefully, the chain from a soil moisture anomaly up to a precipitation anomaly is a really complex chain with a lot of pieces. The influence on temperature is a little bit more straightforward, and there's fewer steps. And so what they find in this study that used 10 different model simulations is everywhere with color and stippling, which I realize is a little hard to see, color's a little bit more clear. These are regions where you would expect to see increases in skill from realistic land surface initialization. And all of this was something that we've been looking at in detail for a few years now. So Jager's paper in 2024 looked at sources of predictability in CSM2, and we expected to find something like this, where initially you expect predictability coming from the atmosphere, then from the land, and then from the ocean. What was found instead is really a limited role of the land surface in contributing to S2S predictability. Most of it came from the atmosphere. So what we've been trying to understand is how sensitive are temperature predictions in CSM to soil moisture conditions at initialization. So how do we do this? Well, first we take a series of reforecast sets. These are weekly initialized on Mondays, And so just to give you a bit of a visual, we take initial conditions from ERA 5 in this case for the atmosphere. The land surface initial conditions come from offline CLM simulations, and ocean SST is prescribed. So these are AMIP simulations similar to the CAM6 experiment that Judith mentioned before. These are 20 years of reforecasts, and each has an 11-member hindcast ensemble within it. And I'll be showing you kind of an average across all of those ensemble members, but there's more information we could glean as well. And as Judith alluded to nicely before as well, it's really important to consider this regionally. And I think that's also spoken to from the Coster et al. Diagram, where not every area of land was colored and stippled. Really, we only expect to see an increase in skill from land surface initialization over certain points. So what I've been doing is looking regionally, and here we're going to just zoom into the US South. This is a particularly interesting region, so I did kind of cherry pick it, but I think it's worth experimenting with. And what I'm looking at is a time series of soil moisture anomalies. So we've removed the lead-dependent bias, and we've averaged soil moisture over this whole region, and then defined wet days as soil moisture within the top quartile, dry days as days within the bottom quartile. And then 50% of days we would consider neutral. So if we consider how well the model does in predicting temperature on each of these kinds of days, I'll work on this kind of plot. So you're looking at anomaly correlation coefficient, averaged again for the whole US South region. A higher value means higher skill, lower value means lower skill. And just to give you a sense of how skill drops off with time, we're looking at neutral days here, where we start with a high skill for weeks 1, 2, and that drops off pretty markedly as you get to weeks 5, 6. But what happens if we look at days that are initialized with a soil moisture anomaly? Things change a bit. So here in blue, we're looking at days initialized with a wet soil moisture. In red, days initialized with a dry soil moisture. And my favorite part to look at is just this lead weeks 5, 6. So we go from having an anomaly correlation coefficient of below 0.1 to above 0.3. So when you initialize the model and you have your surface soil moisture in one of the tails, whether dry or wet, that memory persists, and it gives you skill on subseasonal timescales to understand your temperature predictability. One question that comes up, are we sure? Do we really think this is land, or is it just happenstance? So I'll toggle between these two plots for a minute or two, but I want you to pay attention, especially on this weeks 5, 6. These color bars aren't changing much. There's a little bit of a difference, but this is with a different experiment set. So this is from the fully coupled CSM2 reforecast set that was in Richter et al. 2024. So it's initialized with a different atmospheric forcing, so CFSV2 instead of ERA 5, and it's fully coupled, meaning active ocean instead of prescribed SSTs. We still see the same pattern. So that's reassuring and gives us some faith that this is something real. Now the next experiment I want to show you is Climo Land. And in this case, also from Richter et al. In 2024, the realistic land initial conditions are substituted with a climatological initial condition. So if we expect that this skill comes from land, we would expect that any skill that comes from the dry or wet anomaly should decrease. And we see that it does. So realistically, initializing your land surface condition when you have soil moisture anomalies in the tails gives you increased skill compared to if we don't. And to back this up physically a little bit more than just looking at prediction skill, it seems so far, this is somewhat preliminary, but it seems like a lot of the skill is coming from soil moisture memory. So this is looking at the soil moisture anomalies averaged over the dry initialization, wet initialization, and neutral initializations at day 0, so when you're initializing, day 15 and day 30. And even by day 30, especially for these wet and dry initializations, we still have these anomalies persisting out in space. And so one could assume then that that is driving a lot of what we see in increased skill. So are the temperature predictions in CSM actually sensitive to soil moisture initialization? So far, it seems like at skills of a little over a month, yes, and it's likely due to the land memory that we're seeing. This is still somewhat preliminary, so we're in the process of reproducing a few simulations that'll give us a little bit more faith in the signals we're seeing, but so far, things are looking promising. And I want to also note, as I mentioned before, that's true for one region, and in June, July, and August, so the warm season. That's not necessarily true across all regions and seasons. So just as an example, I'm showing you now the Southeast and the same kind of ACC bar plot, where now we see that neutral conditions do drop off in skill, not as fast as we saw in the South, but we don't really see any gain for initializing the model with either wet or dry soil moisture anomalies. So this is really regionally dependent. It's important to keep that in mind when looking at initialization sensitivity. There are still a number of open questions, including on what physical processes are actually driving the enhanced temperature prediction skill. We have some hypotheses, but I think it's worth testing further. And there's open questions on additional regions around the world. So far, I've really zoomed into CONUS, but there's regions in Germany, in Europe, and in Asia that are worth assessing as well. I just want to close, as I do most talks on this topic, that land does matter, I swear, particularly for enhancing society-relevant prediction capabilities. So with that, I'm happy to take any questions. Thanks.
Okay, thanks for staying on time. Maybe we do have time if anyone has questions.
Hi, Meg. Really great talk. I guess I'm curious if you have any thoughts or hypotheses why the Southeast doesn't give you better predictive skill at the tails?
It's a great question. Do you have thoughts on it?
I guess I'm curious, is there any physical, like, could you generalize this added skill broadly to other land regions?
Yeah, excellent question. I think that's kind of what I mean by, like, there's physical processes at play that I don't yet have an answer to.
Sure.
And so I think that looking at things like soil texture, like, is one really good at holding on to moisture versus another? Looking at soil moisture memory itself, there's really cool work being done by a grad student who's visiting for the summer, Nazanin Tavakoli, looking at regimes, and are we always in a wet regime, dry regime? Are we getting things quite right for the right reason? And I think once we have those answers, we'll be better able to generalize, but work in progress. And
Yeah, very cool. Thank you.
You know, and it made me think, and this is kind of a statement, I guess, in the Southeast, the moisture recycling climatologically is very fast. There's a lot of diurnal variability across the coast, which is different to Texas in terms of it doesn't rain every day in Texas. So maybe moisture anomalies can persist because of that. My question was, you had your wet and dry, and I'm wondering, do like neutral anomalies persist as well?
It's a good question.
It just occurred to me that, like, you know, persistence could be, you know, very boringly, it's average and it can, you know, continues to be average.
It can. Yeah, and I think another cool thing to look at is, like, the time at which these anomalies occur. Like, are you in a neutral period for like 3 months? And you're getting skill from something else, or not skill from something else, like ENSO or MJO. So there's still a lot of things that could be driving it. I think that said, we would expect to see skill coming from the tails as opposed to coming from the neutral. And so that's somewhat reassuring that we're seeing what we expect. Yeah, good question.
Okay, we should move on. Thanks, Meg. Our next speaker is Matt Newman.
Now I'm official, that's good, because otherwise, you know. Okay, I'm going to talk about work that was led primarily by Dylan Amaya, who's now at North Carolina State, actually, as of yesterday, and Ho Xuan Wei, who's also in PSL. And what we're interested in is getting at this. How do you advance? Oh, there we go. What we'd like to ask is what drives seasonal precipitation predictability in the real world. But what we're going to ask is just what is driving it in actual climate models, the current models that we have. And these are the typical possible processes which could drive predictability, prediction skills, soil moisture, atmospheric persistent variability, sea surface temperatures. And that schematic has been used to death, I think, at this point. Now, you would like to try to do that in the context of experiments with prediction systems, but the problem is it's hard to turn things on and off because everything is kind of in balance in the system. If you were to turn off the exotropical SST and keep the atmospheric initial conditions, you would have something that's out of balance. So what we want to do is use something called model analogs, which allows us to kind of do these sort of experiments. The idea of model analogs is very simple. It's just analog forecasting, but using climate data sets. So if two states in a system are close together, then we consider them an analog. And the question of how to pick an analog is a more complicated one. Kenya is going to show a more sophisticated way in the next talk. But here we're just doing simple pattern matching You just take an observed pattern and you match it, an observed anomaly, I should say, and you match it to model anomalies from some data library. So you can think of this as some large pre-industrial control run. You can try to match the best match you can find to the observed state, observed anomaly state, and then once you have that in the model, then its subsequent evolution within the model becomes the forecast. And the thing that's nice about this is I only have to match something like SST anomalies, but I get everything that the model generates. In particular, I get precipitation. And we can repeat this as many times as we want to create a model ensemble. And actually, that ensemble is going to be more skillful than just like the best match. So that's the idea. It's ridiculously simple, which has certain advantages. And so what we're going to do is we're going to do some analog forecasting, and we're going to compare where we use different domains or different variables to choose the analogs. So we'll either use essentially tropics and exotropics, or just the tropics, and different variables. So we'll start with a very clean comparison. We're going to compare to SMILE, and we're going to use the same model that was used in SMILE, so the CESM2. We're going to use the same period. We're going to use the same data set as well. So we're using initial conditions for the ocean coming out of Fosse, for the atmosphere coming out of JRA 55, and the soil moisture from, I guess it's trendy. And of course, in SMILE, again, it's a full three-dimensional initialization, but we're not going to do that sort of initialization. We're going to do the matching, try to find states in the CSM2, large ensemble in this case, that best match observed anomalies, see how they evolve. That's our forecast. We can do that cheaply. Doesn't cost us anything. So we can run this every month and as many ensemble members as we need. So here's the scale of SMILE for August initial conditions, going forward in lead time from kind of a 2-season lead to a 11-season lead, if you think of, we're defining the season by the central month. And obviously most of your skill in the tropics, some skill here in North America associated with kind of forecasts verifying in winter. And then here's the same thing for this model analog ensemble, and basically you can see it's very similar. In fact, there are almost no significant differences between the two. On the right, I'm showing any significant differences, and in fact, the main significant difference is that the model analogs are better in the Western Tropical Pacific, which is consistent with this idea that one of the nice things about essentially initializing the model directly on its attractor is I don't have an initialization shock. So in the model, I'm using a full three-dimensional system. It may generate an additional imbalance, but I don't have that problem. That actually gives me better skill there in that case. So there are cases where the model analogs could actually be better than the traditionally initialized system. Okay, so let's look at the impact of using different variables to pick the analogs. We can use SST, 500 millibar height, and soil moisture, and we can use various combinations. And what I'm showing here is essentially how good my initial match of precipitation is with these different various combinations of anomalies or variables. So obviously SST gives you a good match. Z500 doesn't give you as good a match on its own, but in combination with SST, it seems to improve. So it suggests that maybe we can get slightly better analogs if we use both SST and 500 millibar height anomalies. So that's the initial state. Let's see how it does for the forecast. So again, on the top left, you can see that we are getting a better initial match, but as we go forward, it's really not improving the skill at all. So we're not gaining anything from adding additional variables. In fact, this is what we find in general, is that if you use SST, sometimes SSH can give you a little more on a long lead, but in general, SST alone can pretty much give you all the skill that you get out of the full initialized system. That's kind of the important thing here. We don't need any other data to choose our analog. So there's no other additional initial information that's going into our system other than what's in SST. All right, so now we're going to focus on all the models that we have that are available. We have 33 CMIP6 models. We can turn them all into forecast models. And I would argue this is a much stronger test of the quality of the models than variance and other simple statistics that people usually use when they compare models, because you're actually looking at the evolution of anomalies within the model. We're going to compare using the domain from 60 south to 60 north and just 30 south to 30 north, just using SST to pick our analogs and see what the impact is of the skill. So what happens if we use the additional information in extratropical SST to make model analog forecasts? So these dots are comparing essentially a global measure of the skill, kind of an average anomaly correlation. And every dot is showing either different season or a different model. And so basically this line is comparing the skill of just using the tropics and also including the extratropics. And as you can see, by and large, all the values are, I think that's an old figure. Sorry, let me just get rid of that because that figure was wrong. This figure is right. All the dots are below the line. In other words, for a given model, for a given lead time, adding in extratropical SST actually might even slightly degrade the forecast. It certainly is not improving the forecast, and that's pretty uniform for all the models and for different initial conditions. So in general, what it's stating is that we don't need any information in the exotropics to give our forecast prediction skill in terms of precipitation. So everything, in other words, is coming from the tropical initial conditions alone. Okay, good. This is my last figure. And so we can also see how that compares to operational models. Here on the top left, I'm showing the North American multi-model ensemble. This is the forecast skill for DGF for August initialized forecast. And on the bottom, I'm showing the same thing out of this multi-model ensemble, model analog ensemble. And again, you can see the skill is basically the same. There's some areas where maybe the model analogs might be doing better, and it seems like it's doing a little worse here. That could be a place where you're getting some local effect maybe of the extratropical SST. But if I add an extratropical SST into this, it doesn't improve it. So it's probably more of an actual difference in the models. And then this gives you a more general idea of how the skill compares for these three boxes. So this is this offshore box on the top. This is a southwest box in the middle and a southeast box here on the bottom, and essentially showing the variation in skill as a function of both the lead time and the initialization. And so again, the skill is basically the same, so we're able to reproduce all of the NMME ensemble mean skill, again, just with knowledge of tropical SST alone. Okay, so that's just the conclusion. The paper's undergoing minor revision, and if you want to read more of the details, you can scan that. I think for this group, the one thing I would emphasize is that I think this is, again, a statement about current models. It's not a statement about necessarily predictability. The extratropical SST could be important. Initial conditions can be important. It's also not a statement about processes. All I'm saying is I'm talking about the initial information. So the initial information, all that matters is coming out of the tropical SST. That doesn't mean that there's no impact, obviously, of processes outside of the tropics. So there's an information statement, but it does suggest that this is a technique which can be used to evaluate models as they're being developed to see if there is improvement being made. So I'll stop there.
We can take one question if it's quick.
Could you push this further and find specific patterns in the tropics that are contributing?
Yeah, that's more what Kenya's going to talk about. So you basically, you would like, this is a very simple method, right? And so have we found the best analogs? Not necessarily, because even with 1,000 years of data, your analogs are still only going to be so-so, right? So you would like to make the analogs as perfect as you can, as good a match, and actually capture the evolution of the entire trajectory, which we have no such constraints. And yeah, that's, like I said, that's what Kenya will talk about.
Thanks, Matt. All right, our next speaker is Kenya Turide.
Hi everyone. So I'm just gonna talk kind of extension work of what has just presented. So we will use a neural network to pick better analogs by learning which features of each state matter most. So seasonal precipitation is hard to predict. This is the calibrated NNME tertiary forecast, which is the managed model operational benchmark for northern hemisphere extratropical land precip verifying in winter. So the scale is decent in short reads, but it drops sharply at long reads. So at read 7, when the forecast has to cross spring, the scale goes negative, and that's called spring predictability barrier when the answer is hardest to predict and that affects everything downstreams. So can we do better than this? And lo and behold, with our AI analog approach, we can get much better scale at these long reads. So now the orange AI analog line stays positive through the spring initialization months, and the method helps, specifically helps where the operational system fails. So let's dive in. So I'm just gonna go this briefly since Matt just explained this, but our starting point is model analog method. We will find similar state from a library of climate simulations. So here are the analogs based on the best match of mean scale distance in terms of tropical SSD and SSH. And we're just gonna follow what analog evolves within the model, and these ensembles are our forecast. One caveat is that, as you can see from these figures, the analogs are not the exact matches, so the initial scales can get worse than those that are initialized from actual initial conditions, but they are similar enough that they can provide good scale at long reads. So now we use a neural network to select better analogs. In the baseline unweighted analogs, every grid point counts equally. Tropical Pacific, Atlantic, everywhere the same. But not every region is equally informative for precipitation. So we train a neural network that takes the initial ocean state and outputs a map of weights. So the region that matter for forecast get more weights, and regions that don't get less weight. Then we select analogs using this weighted distance. So two things to note here. One, the weights are state dependent, so they change with the initial condition. And because they are just weights on physical field, we can look at them directly and see what the network learned. We trained the neural network on CMF6 pre-industrial control runs. 33 model runs serve both as training and library, which has about 18,000 years. And we hold out 9 model runs from different modeling centers for validations. We test on real world 1991 to 2023 using ORA S5 for ocean state and ZPCP for precipitation. The unit takes SSD and SSH as input and output weight used for the distance metric. And we train it on global terrestrial precipitation at an 8 months lead time. So here the result, the left is near 3.4 scale, So one thing to note is that even though we train on global precip, the analog method still provides forecast for other variables for free, so we can look at SST forecast. And as you can see, that all of the three models sit basically together for linear 3.4 scale. The orange line is above the black line, meaning that when we train for global precip, it also improves ANSYS scale. The middle shows global precision scale. You can see NNME has the highest scale, which is mainly coming from the tropical signal, but the scale drops with lead time, and AI analogs becomes better at around lead 7. The gain becomes more obvious if we remove the tropical signal. So this is the precision signal over extratropical land. And we can see AI analogs hold scale up to long reads where NNME scale drops sharply. So this is suggesting that while NNME has good tropical scale, it has some biases in its reconnection. So where does the network add scale seasonally? The left panel shows scale by initialization months on vertical axis, and the white diagonal line shows the verification seasons. So the baseline analog shows the highest scale during DJF verification, which is the ANSYS active season. And AI analog further enhanced the scale. This is shown in the difference plot, where green means improvement. And you can see improvements already verification season dependent, starting from summer, fall, winter to spring. And the improvements also extends to year 2 forecast. So network is sharpening the seasons that already had a good predictable signal. So where does this help geographically? Here the forecast initialized in May, verified in DJF. So absolute skew on the left and the difference on the bottom right. We see mainly improvement over the tropical Pacific and over the maritime continent, and also over the ANSYS teleconnected regions over North America, South America, Asia, and Eastern Africa. However, some regions get worse, including the West Pacific and East Pacific of the equator, probably related to ITCC biases. So you can see these negative regions corresponds to the region that has negative baseline scale. So that's the trade-off of training on climate models. So it gives overall better scale, but it can amplify model biases. So now I want to focus on high signal events, since the predictability of seasonal precision is generally low, and high signal events are what matter most. So we define forecast signal using the Shannon entropy of the 3 tensor probabilities. So this plot shows the scale condition on entropy. So the leftmost point shows the scale for all events. The rightmost point shows the scale for top 20% signals. So we see analog methods have higher scale than NNME for all events, but the baseline analog and NNME scale kind of converge at high signal event, whereas AI analog has much better scale for high signals. So the network exploits a strong prediction signal better than anything else. Now let's look at what the network learned. On the left are the average weights for May initialization, SST on the top, SSH on the bottom. So we can generally see the tropical Pacific lights up for both variables, especially this equatorial SSH band. The split is roughly even or between SST and SSH. And the light shows the breakdown of weight by ocean basin across all initialization months. and Pacific dominates year-round. So the network independently finding that Pacific is important, which is consistent with what we expect. We can go one step further and ask which weights actually matter. So we keep the weights only over specific region, zero out the rest, and measure how skill change. Takeaway is that keeping just tropical Pacific weight recovers pretty much the full weight skill, which is this orange line. So this again confirms that tropical Pacific is the key driver. Yes, I can skip this one. These are the two takeaways. First, AI optimized analog beats unweighted analog and LNME beyond 6 months lead time. And the gains are concentrated in high signal and so active seasons and events. And weights are interpretable. The tropical Pacific, SST and SSH dominate the total weight. Thank you for listening. Happy to take questions.
One quick question.
Very interesting work. I'm wondering, your loss for the unit is set at 8 months lead time, right?
Yeah.
So I wonder how the final result would be, how sensitive it would be to that lead time.
That's a very good point. So as I said, analog method is, it is limited by the, closest match at interstate. So I was also changing the lead time, but if you use too short lead, we don't have the, closest match, so the improvement's gonna get weaker. So there's 8 months is kind of optimal spot for enhancing the skill overall.
Thank you very much. Next speaker is Dan Amrine.
Okay, thanks. Good morning, everyone. Today I'll be discussing post-processing, thinking about if we can improve ENSO forecasts in CESM2 SMILE. The connection with Kenya's work is, I think, he's interested in how to move your initial conditions onto the model attractor. I'm kind of thinking about how to move them back off into the physical space. One of the basic starting points here is that forecast biases arise when the model statistics differ from those of the physical system, right? And we can see this here. I'm plotting in the top row time means of temperature in the equatorial Pacific, which I'll be talking about today. Thank you. Contrasting those between HAD-SST and lens 2. And in the bottom row here, contrasting their standard deviations, again, HAD-SST and lens 2. A canonical bias in many models is the westward extension of the cold pool and anomalies in this region. And to some extent, we see that mirrored also in the structure of variability here. So where I'm going with this is when we can think about anomaly forecasts, right, where we subtract the mean from these models and we put it into the mean of the observations, but it doesn't change the fact that variability might happen in a different place, right, because the feature in your model is extending too far in one direction. And these biases are one of the biggest problems, I think, we have in unlocking greater skill from improved initialization, for instance, actually doing data assimilation. So I'm interested here in whether we can learn a post-processing approach to SMILE that takes these spatial biases into account. So as a reminder, SMILE is 2-year-long coupled CESM2 hindcasts, 20 ensemble members from a forced ocean sea ice experiment. This was the state of the art. I don't know what the time range is right now, but at least from the 50s into 2019. And we're initializing in February, May, August, and November, and then running for 2 years, right? So lots of different 2-year simulations. The hypothesis here is that we can learn the ways that forecasts are consistently wrong and correct them, okay? And this is going beyond taking out the spatial mean. We want to actually warp our forecasts in space. And people have been doing this for a long time, especially in the weather world. So what's called model output statistics, or MOS, is basically saying, okay, we have some smile hindcasts, that's my Y. And I have, in this case, my had SSE, this is going to be my truth. And I'm going to say that's X. And I am going to take my anomalies from my hindcasts and my anomalies from my SSTs, and I'm going to regress them onto one another, right? That is the mathematical encoding of this model is always wrong in a kind of similar way. I am going to call this operator somewhat cryptically TMR. It is an operator that takes us from the model to this kind of reference state. So what am I going to do? I'm going to compute TMR for each initialization month. I'm going to target December SSTs as a proxy for ENSO strength. I'm going to subdivide the SMILE and had SST. I'm going to calibrate 1970 to 1999. I'm going to compute this TMR under the hood. I do have to regularize it. So you can think of this as, this is old school machine learning. So we're tuning our meta parameters. And then I am testing it on years 2010 to 2019. We have a bit more for November. I'm using it because we need all the data we can get for this problem. Okay, the punchline starting off is that we can see improvements from this learned linear post-processing over this admittedly short testing period. On the left-hand side, I'm showing root mean squared error between SST forecasts as a function of lead time. So at the top, we're initializing in February, and at the bottom, we're initializing in November. So we're getting closer and closer to our target time. So right off the bat, you see skill improve through time, as we might expect. And then on the right-hand side, I'm showing the improvement when we are using this model output statistic approach. So the thing that really pops out in the improvement is we see a reduction in root mean squared error on the western side of the Pacific. This is typically where ENSO warm anomalies protrude too far. That improvement is actually reduced somewhat in November because at that point, the model has been initialized already with some knowledge of this, so there's kind of less to improve. You can do the same thing with anomaly correlation coefficient. The story is qualitatively the same, although maybe you are disimproving some places outside of that kind of canonical tongue. One observation I had in the course of doing this work was that in a way, as we are proceeding at longer and longer leads, and with a caution, I should also caution, I've done these statistics a lot of times with various bootstrapping. They're noisy, right? And so I think we can trust maybe some of the large scale features that you see. The finer ones, we don't have that much data. But a qualitative observation is that as you go back further in time with leads, your ability to improve the forecast kind of plateaus, right? And so what that speaks to a little bit is the declining importance of the initialization for that time, right? So at some point, the forecast initialization gives you relatively little skill. So what could be improving this thing? And I think what it is knowledge just of the time, the relative correction of the time mean position of water masses in the equatorial Pacific, right? So we no longer care, we don't have a specific correction based on May or February or August, but it might be we're just going to stretch the equatorial Pacific to look more like the observations. So to test that idea, I said, well, okay, in theory, we should be able to learn this information from the large ensemble, right, which is lots of representations of this thing. So I kludged together what I'm calling just kind of like an EOF remapping operation. I'm literally just taking the leading EOF from lens, I project it onto the SMILE output, and I just replace it with the leading EOF from HAD-SST, right? And so this is a lead independent forecast correction. And I find these results to be qualitatively very similar, right? So at this point, I don't think we're getting a lot of skill from these lead dependent measures. It's more about correcting the time mean positions of variability in the model. Okay, this is what this actually looks like in the wild. So on the right-hand side, this is forecasting the 2015-2016 El Nino, which is in our test data set. The right-hand side is raw SMILE. The middle is this MOS approach, and the right-hand side is where I'm just using this lens correction. So for SMILE, you can see the westward extension of this thing contract over time as we get closer to the forecast period. Also, the amplitude increases a lot. What we gain from this post-processing is mostly, again, this contraction of the westward extent of the El Nino event. I don't have a ton of time, but I think that when we are synchronizing our model with the real state, and then we are learning the ability to warp from one to another. This is useful for forecasting, but it can also tell us about cognate structures that lie in the model, which might be informative for process studies. How do we do this? Well, remember that up here we are learning this TMR, and then we're using it to regress the SMILE forecast onto this post-process. We can SVD, take the singular value decomposition of this thing, and find out what structures in the model are paired with structures in the observations. I'm not going to talk about these, I'm going to show them to you. We can also do this for this kind of EOF replacement, and it's just trivially the fact that I am replacing the model EOF with that of HAT-SSD. Thanks, Steve. Okay, so MOS post-processing shows some ENSO skill improvements where CESM is biased. Maybe there's some lead time dependent corrections that we can find, but we're not working with many realizations of El Nino, right? So maybe we can turn to these large ensembles and learn a typical bias. Caveat right now is, we're kind of changing where ENSO lives, right? I'm not giving you the ability to better predict an El Nino event per se. Questions in the future. If we mine lens 2 for analogs, maybe we could get another SMILE with a bigger signal, not sure. This raises the question a little bit, maybe there's a lot of state dependence here, right? And you can imagine conditioning on Nino 3.4 in order to make a state dependent prediction or do something nonlinear. Again, this raises the question, do we have the data? And then the final piece is, this is work where we published with Niraj Agarwal a kind of full workflow where we optimize pre-processing and post-processing in a paired way. I think it'd be interesting to think about taking the inverse of this MOS and applying it to when we initialize SMILE. Thank you.
Questions for Dan?
Hi. I was wondering, since you showed that this seems to be more lead independent and generally due to the mean bias in this problem, do you think it's applicable to other areas of the ocean or other aspects of the climate system that might not be as well understood as this ENSO bias?
Yes, I applied it to the North Atlantic, and Steve graciously let me down that nobody really cared about the North Atlantic and I should look at ENSO. But yeah, in principle, you can.
Thank you.
Okay, we'll move on to our final talk before the break. This is a team talk. David Clemens-Sewell, lead it off.
Yeah, thanks everyone. We're doing this tag team style. So Andrew's going to start talking. If we could get Claire Singer online. Okay. Yep.
Cool. Thank you. I'm Andrew Gettleman, and on behalf of the team I'm going to introduce in a second, we're going to talk about a little bit of a shift, talk about impacts of marine cloud brightening in the Arctic and beyond. So this is a project we have between NCAR and the University of Colorado. It's funded by the Grantham Foundation. Let's see. How do I advance? There we go. So the team, which I'll introduce, the team is basically Marika Holland and I are the co-PIs, and then we have a team who we'll introduce in a second who's also working on this project. So we're talking about climate intervention, and we're focusing on the Arctic. So climate intervention, people think about doing things in the stratosphere to reflect sunlight away. They also talk about modifying the surface albedo or modifying clouds. And we're primarily in the Arctic. there's some particular issues, of course, because you have an additional feedback from the surface, the sea ice albedo feedback. And so there's a concept that if you try to cool the Arctic, you actually get a lot of knock-on benefits in the system. It's also a particularly sensitive region that is warming particularly fast, and we may be able to actually protect that sea ice. So we're going to focus on a couple of things here, looking at the albedo and focusing on looking at marine cloud brightening, low clouds in the Arctic. Many of these are supercooled clouds, so you're dealing with supercooled liquid. And also, we're not really going to talk about it, but we're going to eventually get to sort of cirrus cloud thinning in this project. But mostly, we're going to talk a little bit about marine cloud brightening experiments and the knock-on effects of those throughout the Arctic. So we want to understand what the potential for cloud modification in the Arctic is to alter sea ice and cool the region and the planet, what the sensitivity is of sea ice to cloud changes and modifications specifically, and then what are these effects, not just on sea ice, but throughout the Arctic climate and ecosystems and Earth system, and how are they distributed. So as said, the team is myself and Marika, and we have a large team. Walker has been working on the simulations. He's going to talk about those in a second. Claire Singer is remote. She will talk about clouds. Aaron can't be here today. We'll talk about cold cloud processes at the end. And then David and Courtney are working on sea ice and ecology. And Laura Landrum's also working on polar climate. And we have a variety of other collaborations that are listed here at NCAR and beyond. So before I turn it over to the experts, basically just to note, the clouds cool the Arctic only in summer. This is sort of looking at the surface cloud radiative effect. So we often think about top of the atmosphere. This is slightly different. This is looking at the surface, because that surface radiation budget is what's important to sea ice, so we're shifting our focus a little bit. And the black line is the net. So basically, the red is the long wave. There's a constant long wave warming due to clouds throughout the year in the Arctic. And then in the summer, there's a cooling and due to the short wave. And you see this balance where clouds are basically warming most of the year and they're cooling in the summer. And so you actually want to do different things seasonally. And you can see this is also related to where the ice is, because when you're worried about the surface, then the surface albedo plays into that. So blue is cooling, red is warming, and you can see it's really not over the ice. Most of this is happening. It's happening in the marginal ice zone, and it's happening in other regions. So with that, I think Claire is online. She's going to talk about, well, Walker's going to start, and he's going to talk about the methods and what the simulations are.
Thank you, Andrew. Good morning, everybody. My name is Walker Lee. I'm a scientist in CGD's AMP section, and my role in the team is to set up and run the model cases that we're using to analyze these perturbations. So we are running the fully coupled CESM2, and we're simulating a future warming scenario in model years 2035 to 2070. For those of you more interested in the specifics, we're running the SSP3 7.0 warming scenario. We have also incorporated the 4P2Z biogeochem mods, and we're running the less melt enhanced albedo sea ice configuration. So we have our baseline ensemble with no perturbations, and then on top of that, we are running 9 different simulations of marine cloud brightening, composed of 3 different strategies at 3 different strengths each. So our 3 different strategies, the first 2 are uniform perturbations inside the Arctic Circle, where we brighten low clouds within the model. One of them is we're calling annual, which is where we're applying the same constant perturbation throughout the year. And the other one, the other uniform strategy is summer only, where we're only brightening clouds in May, June, July, August, and September. And then the other months of the year, we're not doing anything to the model. And then the last strategy we're calling the dynamic mask, and this is intended to represent a more realistic deployment of marine cloud brightening. So we're still brightening clouds inside the Arctic Circle, but this time we're not brightening clouds over land, and we're also excluding grid cells from the seeding mask with a sea ice concentration that is higher than 90%. So we're only brightening clouds over the open ocean and inside the marginal ice zone. And then for each of these 3 strategies, annual, summer, and dynamic mask, we are deploying idealized drop number perturbations, where we artificially set the cloud droplet number concentration to either 100, 200, or 400 droplets per cubic centimeter. This has a brightening effect on the clouds within the seeded regions. And for some context, the baseline CDNC inside these regions is on the order of 20 to 50 droplets per cubic centimeter. So our lowest perturbation represents approximately a doubling of cloud droplet number concentration within this region. And then we have a doubling again, and then the highest strength perturbation is a doubling again. And so we are also, we've already run simulations with droplet number perturbations, but we are also looking at, eventually we're going to get to ice number perturbations, which will affect the optical thickness of ice clouds as well. And then later, the plan is to move towards perturbations of cloud condensation nuclei or ice nuclei directly, or releasing aerosols into the marine boundary layer to allow the aerosol code within the model to brighten the clouds for us instead of just simulating the droplet number concentration change. So briefly, I'm going to talk about an overview of the global scale impacts of this kind of intervention before the other members of the team get into the more nitty-gritty. So how does this kind of intervention affect the climate in CESM2? So in terms of surface temperature, the mid-level dynamic mask perturbation is a representative median of the 9 perturbation simulations that we did. For the reasons that Andrew talked about earlier about the seasonality of cloud forcing in the Arctic, the year-round changes tend to be the weakest, the summer only tend to be the strongest, and the dynamic mask are somewhere in the middle. So the dynamic mask mid-level perturbation cools the Arctic by the order of 2 to 3 degrees Celsius, and this version of the plot doesn't have statistical significance, but there is detectable cooling throughout much of the northern hemisphere, especially the mid-latitudes over land. So this is the kind of cooling that you would get from this kind of intervention. When you change the surface temperature, you're also going to change precipitation. The 2 main precipitation responses that we would expect and do see here are that you would reduce precipitation in the Arctic approximately proportionally to the amount of cooling that you're doing, and then also you're going to shift the ITCZ to the south because you're predominantly cooling one hemisphere over the other. And then lastly, one other impact that I personally found really interesting is that this kind of intervention has an immediate and pronounced effect on the strength of the AMOC, the Atlantic Meridional Overturning Circulation. And this is a very fast response compared to other kinds of climate intervention that we've studied in terms of how quickly the AMOC responds to this kind of intervention. And then a few words on how the Arctic climate is affected in CESM2. I'm not going to talk about sea ice, other folks are going to talk about that later. But briefly, it's very noisy, but the different strategies do increase Greenland surface mass balance to varying extents. And then also, we see a small decrease in the efficacy of the Arctic as a carbon sink. And the reason for that is by cooling the surface, we're going to increase the amount of permafrost in the Arctic, and we see that total soil carbon, which is pictured on the left, goes up, but we're also going to weaken the land vegetation in the Arctic as a carbon sink, and that effect is stronger than the soil carbon sink effect in these simulations. And with that, I'm going to turn it over to Claire.
Okay, thank you, Walker. I hope you guys can hear me online. Can you hear me?
Yes, but we lost the... Oh, yeah, 1 second. We're just getting you back on the screen.
Okay.
Yep, all set. Take it away.
Okay, great. Hi, everyone. I'm Claire Singer. Thanks for letting me present this remotely. So yeah, I'm going to dive into a few little details about how the Arctic climate responds to these cloud perturbations and focusing on the surface energy balance and the clouds themselves. So these plots here, I'm showing you the response of these key Arctic variables over the course of the seasonal cycle to our 9 different perturbation strategies. So on the left is the response of the sea ice area, the middle is the latent heat flux, and on the right is the total precipitation. And so the story here, you see that all of our perturbations are increasing the extent of the sea ice, primarily in its minimum season in the fall. And this growth of the sea ice is reducing the latent heat flux or the evaporation of water vapor into the atmosphere, which subsequently reduces the total precipitation during the fall primarily. What you can't see from this plot, because this is the total precipitation, but if we look separately at rainfall versus snowfall, In the summer months, when we have the strongest surface cooling, we also see a shift from where we have a slight decrease in the amount of rain and an increase in the amount of snow. Can you go to the next slide? Great. So now if we look across the different magnitudes or strengths of our intervention experiments, we see that for a number of key variables. Here I'm showing again the sea ice area and the surface temperature. But across a number of different climate variables, the response to our perturbations scale roughly linearly for each doubling of the droplet number concentration. So this is true across the 3 different intervention scenarios, whether we're applying the perturbation year-round, just in the summer months, or if we're restricting it in this dynamic mask just over the open water and marginal ice zone. The scaling is roughly linear. This is super useful because it allows us to make statements where we can interpolate between the different perturbation magnitudes that we've tested. So I wouldn't try and extrapolate this to higher perturbations of droplet number concentration. And then next slide. Finally, we've looked at what I'm calling the difference between the effect of a perturbation and its efficiency. So here I'm defining the effect as just the total change in the sea ice area in the Arctic. And as Walker already said, the summer-only perturbation where we apply it across the entire Arctic Circle is the one that has the largest effect. And the perturbation of the strongest magnitude has the largest effect there. So this ND set to 400 drops per cubic centimeter applied throughout the summer months everywhere is the one that increases sea ice the most. But if we calculate this efficiency metric, which is the change in the sea ice relative to how much seeding we're doing, so the total area times the actual change in the droplet number concentration, the perturbation strategy that is the most efficient ends up being the one that is applied only over the ocean and marginal ice zone, this dynamic mask at its lowest magnitude. So this is in line with this understanding that we have just looking at the climatology, that the cloud radiative effect at the surface is strongest when the surface albedo is lowest, so that the perturbation is most efficient when you're doing it not over this concentrated ice zone. And with that, I'm going to hand it off to David. Oh no, I'm going to give some conclusions. So yeah, just what I said, that the perturbations are most effective during the summer months, most efficient over open water, that the cooling across the Arctic is shifting precipitation from rain to snow during summer, decreasing total precipitation during fall because of the reduction in the surface latent heat flux, and that many of our climate variables respond roughly linearly to doubling of droplet number concentration. And now I'm going to hand it over to David, who's going to tell you about a very interesting nonlinear change in the system.
Thank you, Claire. So yes, Claire nicely foreshadowed. We are going out of the atmosphere down into the sea ice and the ocean. And so just to orient everyone to how we often look at the seasonal cycle of sea ice, these 3 plots are showing Northern Hemisphere aggregate sea ice variables. It's ice area in the upper left, ice volume, which you think of as ice thickness in the bottom left, and snow volume, which again you can think of as snow thickness in the bottom right. And when we talk about climate perturbations, we often explicitly or implicitly make the goal of returning the climate to some prior state, stabilizing it in the early 2000s or in the 1970s or something like that. And so on each of these plots, a different line is showing a different decade in the control run, going from the 1920s back in the yellow colors up through the 2040s in the darker green. And you can see, as you're probably familiar with, that the Arctic sea ice cover has declined over this time. And that's what you see in the declining lines here. And so to make explicit this comparison between what the perturbations are doing, shown here in the dashed and dotted lines, and the historical, we can see that indeed for the ice variables, so the ice area and the ice volume, the perturbations, generally speaking, are returning us to one of the historical states in the control, with the exception of the 400 summer that takes us to a more extreme ice conditions than we've seen in the control. But the big difference in the nonlinearity that Claire was mentioning is that what we see in the summertime snow. So in the summer perturbations, we see snow persisting on the sea ice throughout the summer as something that's never been seen historically. It also doesn't exist in the control. And this is a really dramatic state change for the system as a whole. I'll mention briefly that having this change in the snow and the melt rates causes a notable difference in the ocean mix layer and the seasonal cycle of how the ocean mix layer shallows. Snow is also a major limit to light entering the upper ocean for primary productivity, which Courtney is going to talk about now.
Hi, I'm Courtney. So here we've plotted July snow depth versus July shortwave radiation on the left, and annual mean shortwave radiation versus productivity for the year on the right. And just as David previously showed you, we again have kind of smears representing the relationships between these variables, color-coded by decade. So lighter colors are 1920s, and the darkest color is 2040s. And you can see that as snow depth declined a little bit over the 20th century, we saw an increase in shortwave radiation. And that radiation allowed a big increase in net primary production as more light was in the surface ocean. And what these perturbations really highlight is that in many of the more extreme high-end perturbations, we're really leaving that historic envelope of relationship between snow depth, shortwave, and net primary production. So in particular, the 400 level perturbation gives us productivity that is about half of what we are observing in the present. And even a more modest 200 summer perturbation leaves us outside of that historic envelope of production. I'm now showing you this spatially, that 200 summer perturbation relative to the 2040s baseline. And we can see that phytoplankton production drops by nearly 30%, and that productivity has pretty big implications for the rest of the ecosystem. We ran a fish biomass model called Feisty on these simulations, and we find that that reduction in productivity also yields about a 31% decline in fish biomass over the whole Arctic. As you can see, that change is not homogeneous. It's particularly pronounced in the central Arctic, where both phytoplankton production and fish biomass decline by more than 50%. So overall, in the snow and below that David and I have just shared with you, we find that these summer whole Arctic perturbations have the potential to produce unprecedented states in the ice, the ocean, and the marine ecosystem. These perturbations produce perennially snow-covered sea ice that greatly reduces light availability and leads to large declines in Arctic phytoplankton net primary production, as well as fish biomass. And we've shown you that these conditions really don't have a precedent in the last 100 years. We haven't shown you this, but we've done a little investigation with some last millennium runs, and it seems that they only have occurred ephemerally for fewer than 5 years in the last millennium, and all following the largest couple of volcanic eruptions. So these are really well outside of the normal kind of climate state that we've observed. And I'm now going to pass it off to Andrew, who will talk about some of Aaron's new and exciting work.
Thanks, Courtney. Aaron couldn't be here today, but I'll talk a little about some of these ice number experiments, which these are very similar to what we've already talked about. It's basically the same experiment, and what we've done is just a scenario where we've done ice number perturbation. We've done ice number perturbations instead of drop number perturbations. Eventually, we're going to start moving on to explore ice nuclei perturbations and more realistic aerosol perturbations. But we wanted to understand this mechanistically a little better. And so initially, we're taking low clouds and we're increasing the ice number to something like 20 per liter, which is it's about a 10-fold increase in ice number, just below 700 hectopascal. And we're doing this is sort of an annual perturbation. We're just doing it as similar to the initial annual uniform perturbations throughout the whole Arctic. So we haven't tried dynamic perturbations yet. But basically what we do is what we thought we were going to do is we end up adding ice number into supercooled liquid clouds mostly. And so that actually glaciates them. We see a drop in the ice water path on the left. We see an increase in the ice water path, which is small. You notice the numbers are pretty tiny. And the liquid water path decreases, but it decreases a lot more than the ice water path does. That's because the lifetime of ice is fairly short. Once it forms, it tends to sediment out pretty quickly. So overall, we're actually reducing the cloud fraction. We're reducing this throughout the year. And of course, you remember the first plot we saw were the contrasting radiative effects on the surface of clouds. When you reduce them, we basically reducing them in the winter allows more outgoing long wave because the clouds are warming, so we cool, and then this is the net radiation on the lower left. And then in the summer, it actually, by reducing the clouds, you actually allow more incoming shortwave, and that actually is a warming. So doing that in a sensitive season in the summer, pretty much throughout the spring, results in an overall loss of sea ice when we do this throughout the year, but we are getting a decent radiative effect in the wintertime. So if we actually did this sort of the opposite season and we did ice nuclei perturbations in the winter, we actually would expect to see a net cooling. That's sort of the next step, is to look at that efficiency. So taking a step back and doing an overall summary, what we've shown you is that when we try liquid cloud perturbations in the Arctic, they're most effective during summer months, and they're most efficient over open water because they have the maximum impact on a dark surface and the maximum shortwave impact. You don't want to do this you don't want to do this in the winter, of course, because the clouds are warming in the winter. You don't want to make them you don't want to make them brighter, or you don't want to make them thicker. Many climate variables respond linearly to a doubling of the drop number, so that's interesting that over this range that we did, and the range, as we said, is a doubling of the natural background in the Arctic. 100, 200, and 400 sort of corresponds to the drop number in over something like the US, China, and India. So these are pretty extreme drop number perturbations to polluted climates. But summer whole Arctic perturbations have the potential, if you push it too far, to produce unprecedented states in the ice, ocean, and marine ecosystem. And we're also starting to look at what happens on land and what happens to sort of permafrost and land-based ecosystems when you do this, even if you do it just over the ocean. And then perturbing ice clouds year-round decreases sea ice fraction compared to the baseline, but perturbing ice clouds in the winter would tend to result in cooling. We have to look at the effect of that on the sea ice. So you can see where this is going, is sort of coming up with strategies, but coming up with an optimal strategy, there are limits to what you can do in the Arctic without having pretty significant knock-on effects on Arctic and other ecosystems. And I think we're going to stop there. So thanks for your time.
Thanks very much for that fascinating talk. So we have time for questions.
Yeah, that's quite interesting. So I guess maybe I have two questions. With these large perturbations, I don't know whether I call them perturbations because they're large hammers, are you actually forcing the model parametrizations beyond their limits? And what are the energy budget impacts, especially with those big changes in AMOC and other stuff? I suspect that the TOA might be quite interesting to look at.
These are all transient coupled simulations, right? So the energy budget is the CESM energy budget. We're taking a simulation which has already got climate change baked in, and we're basically mitigating it in one region. So we're not actually pushing the parameterizations beyond where they would go. So for example, as I said, the drop number perturbations are basically like they're basically like doing it what we see over land. So it's the US, China, India, right? So it's extreme, but it's not orders of magnitude beyond what is physically reasonable.
Okay, thank you.
And part of the reason for doing this in the coupled model is to make sure that we preserve and all these energy budget feedbacks are propagating through the system the way CESM2 would handle them.
I'm taking notes on how to get more time for my talk in the future. So these are like multi-decadal experiments. I'm wondering a little bit about how quickly you see the effects. You showed a little bit of it with the quick response from AMOC, but how quickly you see these effects in the system, and then Are you planning on doing anything where, oh, this is going really wrong, we need to turn it off? How quickly does it go back?
Walker wants to take that one.
Great questions. So in answer to your first question of how quickly do we see the responses, in terms of surface temperature and sea ice area, those responses are pretty immediate. You're going to see that in the first year or so. And then the second question is, what happens if something goes wrong and you have to cut it off? That's a serious concern in the climate intervention scientific community. That event, something like that would be called termination shock. Where you're deploying some kind of intervention that's reflecting a lot of sunlight, and then very suddenly, if you stop that intervention, then the impacts would probably be very bad because the system is going to want to go back to the equilibrium warming state that it would have been in before the intervention started in the first place. And so the rate of warming that you're going to see in the affected regions is going to be much higher than it would have been under even unmitigated climate change. And so we haven't simulated any termination shocks yet, but it's definitely a space that would be worthwhile to explore in this framework.
Yeah, thanks for a very interesting presentation. Have you looked at all, kind of alluding to what you were saying, Andrew, about these simulations have implicit climate change, greenhouse gas forcing? For some of these impacts, maybe especially the ecosystem ones, have you looked at separating the effect of CO2 from the MCB radiative effects and how those two are contributing to the total sort of relative to the baseline climate?
Yeah, we started down that path. Yeah. So, I mean, the first thing is actually to separate the clouds from the surface and understand those effects and how they play out. And then that sort of leads us to what's the effect of climate. And I don't know, Courtney, have you looked at anything with respect to ecosystems, but carbon increases versus the sunlight, or that's not yet?
I think it'd be really hard to tease out what the changes in light are, what drive. I mean, I guess if you first determine what drives the changes in light, which seems to be largely these big changes in snow thickness, then I guess if you can attribute that change in snow thickness to either CO2 or the radiative effects, then you can kind of get an indirect way of determining what drives the changes in the marine ecosystems, but I don't think there's a direct way to do that looking at the variables we have output for phytoplankton.
Thanks.
Okay, let's thank all our morning speakers again. We have a coffee break and we'll reconvene here at 10:30 sharp. desk, I guess, near the front that you can share your participation in the meeting on social media if you so desire. So with that, our next speaker is Summer Manala.
Okay, hi everyone. I'm Summer. I'm a scientist in CGD, and I'm going to give a very broad overview of one of our projects, which is looking at linking internal oceanic modes to regional hydroclimates and hydroclimatic stress indices, but our focus is on decadal timescales. So over the recent time, there has been a lot of focus on seasonal to sub-seasonal timescales. Of course, we care about what's happening next month, next year, but different industries and areas care about different timescales. So my background is in civil engineering. I've worked on projects related to design of dams and irrigation infrastructure. And for those projects, we don't really care about what's happening next year or in next 5 years. We usually care about what's going to happen in the next 20 years with precipitation or with stream flow in the next 50 years, and even for major projects in the next 100 years. So for this work, our focus is on looking at these shifts in not just regional hydroclimates, but also the extremes, for example, drought, flood, and wildfire, how they're going to be changing in the future, and how we can use our knowledge to create more resilient design standards, resource allocation, and adaptation strategy. So that's one of the motivation for this work. Now, at these decadal timescales, especially when we look at regional scales, internal variability is important. So you would have seen these types of maps in multiple locations. This is from Flavio Lerner's 2020 paper. And he's showing the sources of uncertainty, and these are for 2 regions. The one at the top is for British Isles. The one at the bottom is for Sahel. And you can see the orange one, which is internal variability. That is a big source of uncertainty. And this is our focus for the current project. We are trying to constrain this internal variability at regional scales. All right, so this is a NOAA-funded project, and the broad goal is to provide foundational process understanding needed for explainable decadal climate projection for different extremes. These are a lot of words, but to have this foundation, before we go into these projections, we first need to understand what are the predictability sources and drivers. So that's the first box down there. Then we go into predictive skill, and then we go into our forecasts or projections. So for today's presentation, I'm going to be focusing on the first box only, but we are working across this flow. And what I'm going to be talking about is linking various oceanic modes of variability to hydroclimatic stress, and also trying to figure out where or which parts of the world we see strong relationships between them. So we are going to move across this chain, but for today, I'm only going to talk about the oceanic modes, and I'm going to link those directly with the stress indicators at the end. All right, so what oceanic modes do we want to look at these timescales, at decadal timescales, and only looking at internal variability? So this is a signal to noise ratio map, and this is indicating where the smaller values, the darker colors, those are indicating where internally generated decadal variability is more important and dominating over the externally forced variability. So based on this, we picked up 5 MOVs in the Atlantic region, the North Tropical and South Pacific region, and then the Indian Ocean basin. You can also see that the Southern Ocean and the Arctic region is also important, but for now we are going to skip those because they don't have as much impact on the terrestrial systems. So based on this, these are our predictors, the 5 MOVs. We are using a framework, a multivariate assessment framework called partial least square regression. So for that, we have these predictor matrices, and we are connecting them with a number of different variables and stress indices, trying to figure out how are these predictors related to the predictants. And I'm going to talk about Lens 2 dataset only, but we are looking at a number of different observation-based and model-based datasets. So this is all going to be over the historical time period. And there have a few results, but this is one of the summary results showing
how all the 5 predictors together influence or explain the variance in the vapor pressure deficit on the left side and in the standardized precipitation ET index on the right side. And you can see some regions which are these hotspots where the variance explained is quite high. And then this is good because, for example, in Alaska or Australia region, we are seeing that the fraction is around 40 to 60%. So this is non-trivial. Again, this is internal and decadal time period. So we're trying to build some basis where, okay, maybe there is some decadal prediction in these regions. Now this is ensemble mean results over a long period of time and looking at all 5 predictors together. So the next step is, what about the individual members? How are they behaving? And what about the individual predictors? How much they contribute to the total R-square? So for this, we selected these hotspot regions, averaged our assessments over these 8 domains, and that's what I'm showing here. So the top figure is the R-square between the individual modes and VPD and all 5 of them together. We wanted to look at the spread across the members, but more importantly, we also wanted to look at these outliers and the ones that you're seeing up here. So these are the members, the top 5, top 10 members, which explain the most variance, and the bottom 5, 10 members, which explain the least variance. And we want to see what's happening with these members. All right, so just as an example, I picked this member up here at the top, which is explaining the most variance, and the one at the bottom here. And this is showing some results from the PLSR approach. Black line is our original VPD anomaly time series. And based on those 5 predictors, we reconstructed the VPD anomaly time series. And this is pretty good. I mean, it's able to recreate that pretty well, but of course that's by design. We chose the one which explained the most variance, and the residual is small. And if you're curious, this is what the worst member looks like. So again, we wanted to see what's with these members, what's so special that some of them are better than others. And this is now breaking down even further where I'm showing all the 100 ensemble members. And I'm also showing the linkages between NPDV and VPD for all the regions. So again, we figured out earlier that in Alaska, NPDV is really important in explaining the variance. In, for example, Northeast America, AMV explain quite a bit of variance. But then you can, if you just look at the horizontal lines, of course, you can see the differences across the members. In AMV, there's quite a bit of spread. But then I was also interested in seeing these vertical lines. For example, a single member may be explaining a lot of variance across the regions. And it's a little hard to see, but there are these type of linkages as well. So we looked at a number of things related to these individual members. What's so special about that? We did look at the wavelet, the spectral structure of different MOVs. Is there something about their persistence? Is there something about their periodicity? But one of the things that popped up was that it's not individual MOV, their strength, but how they're working together. So the covariance structure amongst these MOVs. And this is a rather simplified figure trying to explain that covariance structure. So for the X and the Y axis here, what we did was pick up 2 MOVs, just did pairwise correlations. This is simplified statistics. And then we separated those based on top 10 and bottom 10 members, which explain the most of the least variance. Most of the least variance for VPD in Alaska region and equatorial South America. And one thing that was that became prominent was that the members which explain more variance have some relationship between AMV and NPDV, and the weak members had none, so there was just no correlation between them, and it popped up in a number of regions as well. But it's not always the case. I mean, for different regions, there were different pairs that were coming up. If you look at the Northeast America, it was the opposite. So it was actually the weak members that have some relationship in NPDV and AMV, and the strong members have none. So based on this, we thought that, okay, it's the MOV interactions, they can enhance or degrade the predictability. It depends on a number of things, but In some cases, these MOVs are working together to create strong relationships. In other cases, they're just working against each other. There's a tug of war, and that's why they're having these canceling influences. But my final slide is that so far this is statistical. So these pairwise or correlations by themselves do not really mean that they would, I mean, we don't really know the causality yet. So we are looking at in detail, if you look at this Venn diagram, so think of these as all 5 predictors, they would have some joint variants that they would explain. So we are breaking this down even further, but more than that, we're trying to build up pathways, how these different members, what's different in their spatial SST structure, and how they're affecting the atmospheric states, for example, looking at geopotential height or moisture flux convergence. And just to know that we are doing this assessment with a number of other large ensembles as well, and with observations. So just to wrap up, for the extreme indices that I mentioned, this is a publicly available data set. It is analysis ready, so it is on GDEX, and if you want to use those, you can download them. Thank you.
Maybe one question, if there are any. If not, we'll move on. Thanks, Summer. To Alexander Thompson.
All right, well, while we're waiting for that to get up, my name is Alex Thompson. I'm a research scientist at CERES, which is the affiliate with NOAA Physical Sciences Laboratory. And today I'm going to be talking about kilometer scale downscaling of the CESM2 large ensemble. And specifically, we're doing this at NOAA for modernizing extreme precipitation guidance, but I'm really hoping that these simulations have broad applicability kind of across communities, and so that's why I'm here today. So a little bit about motivation for this specific project, why we're doing this within NOAA. The Bipartisan Infrastructure Law and the Precip Act tasked NOAA with modernizing estimation of this extreme precipitation metric called probable maximum precipitation. I'm going to call it PMP from here on out. For those of you not familiar with PMP, it is a metric defined as the maximum depth of precipitation over a given area and duration that is meteorologically possible. And it's been really important for the last several decades because it's used as a design standard for high hazard infrastructure like dams and nuclear reactors. But over the last several decades, it's been calculated from observations within NOAA's hydrometeorological reports. Mostly these reports were generated from about the 1960s to 1990s. And as you can see from that plot on the left, it is woefully out of date for our modernized understanding of extreme precipitation, today and and moving forward as well. But this plot on the right shows the location of high hazard dams. So it's really important that we have updated and good numbers for PMP. So kind of as a part of this whole legal process with NOAA, a National Academies of Sciences study was released in 2024 recommending NOAA basically how to actually go about modernizing PMP. And there's 2 recommendations from here that kind of focus on kilometer scale modeling that I want to highlight. So one of them is actually revising the PMP definition. So historically, PMP has been a deterministic metric calculated from observations. The National Academies suggest that we move forward with PMP being the depth of precipitation with extremely low annual probability of being exceeded. So moving from deterministic more to probabilistic, with kind of a loose definition on that annual exceedance probability of like a 10,000 to 10 million year event defining this PMP. And so we can't really get that from observations, right? So we're moving towards a model-based approach to PMP estimation, constructing a multi-model large ensemble of these kilometer scale resolution simulations. And we need this to be able to actually construct a probability distribution of precipitation at the really far end of this tail, right? And so that's kind of the motivation for what we're doing within NOAA, is to actually do CONUS downscaling for PMP of both kind of constructing ourselves, but also compiling from a large community user base of a large ensemble of kilometer scale CONUS simulations that are fit for purpose for the really extreme precipitation. So what I'm doing is actually some multi-decadal downscaling of GCM futures to pair with some of these other NCAR-produced historical data sets, right? And so some of you might be familiar with the CONUS 404 and PGW, or pseudo-global warming, but these are 4-kilometer WRF simulations that downscale ERA 5 over the 1980 to 2020 period, roughly. And so you can see that this is in CONUS mean temperature, but the blue line is the CONUS 404 historical. You can think of this basically as like the historical weather in the historical climate. They also used the lens 2 temperature increase in the future to use a pseudo-global warming to look at the historical weather in a climate of the future. What we want to do with this effort is to actually look at future storms, and we're calling this ensemble of the CONUS futures, to not just see historical storms in new climates, but actually storms that we have never seen but are physically plausible in the climates that we're moving into. And so to do this, we're starting off by looking at the CESM2 large ensemble. Obviously this is a treasure trove of future precipitation extremes, or rather maybe the convective environments that produce them, right? Because we're at 1 degree resolution here, but 10 of these ensemble members have 6 hourly outputs, which means we can downscale them into WRF. And this image is just a depiction of all, and within CESM2 itself, all the different grid cell days of fairly extreme precipitation. So what I'm doing, and these runs are very, very soon to begin production. I'm driving WRF with Lens 2 data, so taking a smattering of variables here, many at 6 hourly outputs with the full 3D atmospheric column, some of the land surface variables at either daily or monthly. Notably, we don't have precipitation here. That is simulated by the WRF model. And then we are bias correcting these values using a fairly simple approach, Briere et al. 2014, using the reference of ERA 5 over the last 35 years of the CMIP historical period. Basically what we're doing, that's shown by the orange and the blue lines, is we're constructing the monthly varying cycle over this reference data period, and then just taking the offset between that. So this is not affecting the variability of the instantaneous data, right? We're just removing some of that broad regional bias that we know exists. So this is what it looks like at just kind of an instantaneous time for one of the ensemble members for 2 meter air temperature over the CONUS. And so you can see kind of a broad cooling due to bias correction, and then some kind of piecemeal cooling or warming in the Mountain West. And then we're taking this bias corrected data and then using that to drive the WRF model for these simulations. So we're getting started with CESM2, but that is not the stopping point at all. This is going to be, hopefully a broad ensemble that will term CONUS futures with one of the most recent versions of WRF. We're producing 4-kilometer hourly output that is designed to be kind of used in a continuous time series sense with that historical CONUS 404, right? And so from the extreme precipitation side, we're interested in those future storms that we've never seen before, but hopefully, this has broader applicability much beyond that. As being at 4 kilometers, there's no convection scheme, and then we're also using the NOAA MP module called MMF groundwater that's really important for MCS development over the upper Midwest. And then the last point here, kind of as the image is showing, these are free running simulations. We're not trying to nudge to the CESM state here, but we're really using CESM as kind of that initial and boundary conditions, and then letting the 4-kilometer physics within WRF define what's going on within that CONUS. Okay, so as I mentioned, we're close to getting these in production mode. We have some test runs that we've done, and I'm pleased to see that in the bottom left here is the hourly precipitation PDF going through each of our months, and I have those CONUS 404 and PGW, each month of those plotted in the red and blue. So we're matching kind of the hourly precipitation PDF in our test simulations. As you can see, we're spinning up a tropical cyclone here, perhaps. So, we're excited to get these going. Okay, so in the last couple of minutes, I'm just going to end with, this is going to be a broad ensemble. We're hoping to downscale several other GCMs for the PMP effort. But to get started, we wanted to find a Lens 2 member that can kind of give us the best depiction of extreme precipitation to start off with. And so what we're doing here is we're designing a 40-year simulation that will roughly have a 5-year historical period that I'm aligning with the 5-year historical from Era 5, so the last 5 years in 2-meter temperature averaged over CONUS. So this is kind of just in the mean, so we can compare our first 5 years against precipitation observations. Now, obviously, we're not going to exactly match them, but to kind of see how close we are with this period. So in order to do this with CESM, obviously there's some temperature differences and things like that. So I'm taking the bias-corrected T2 from CESM, and I constructed this kind of 40-year period of a 5-year historical that matches the mean from Era 5, and then the 35-year future. Following that, and you can see that each member has a little bit different period from that. And so what we're selecting here is the ensemble member I call 2, this 1031.002. So it is a 5-year period fairly close to the Era 5, 2021 to 2025. But I found that this has the best coverage kind of across the CONUS of what I'm going to call kind of moderately extreme precipitation events. And as I said, as we're not nudging these simulations, so even a moderately extreme precipitation event in CESM may end up being a much more extreme event in the WRF simulation. So this is kind of where we're started. We're really excited to get these going. And I will end with that. Happy to answer any questions.
We have plenty of time for questions.
How do you know that 4 kilometers will give you realistic extreme precipitation numbers, say compared to 2 kilometers?
Yeah, that's a great question. So there has been some work that Andreas Prine has done to look at kind of the computational efficiency between like 4 kilometers and 1. And I believe what he found is that 4 kilometers at the computational rate was about as good as 1 kilometers for less computational efficiency there. And so obviously at 4 kilometers we're not going to get everything that we might get, but especially for the PMP kind of side of things, we're really hoping to fill out this ensemble, and eventually, this might take years into the future, but we can get a big enough ensemble to sample all sorts of the really extreme tail. So, yeah.
I'm not sure if I understood this correctly about your methods, but it looked like maybe you're giving the model CSM soil moisture. Is that right? What is the motivation for that versus letting WRF?
Yeah, so that's mostly for the initialization. It kind of, the NOAA MP model then uses that initialized soil moisture to iterate forward, and we don't need to continue. It doesn't continue using it. Okay. Another part of that is we are constructing basically like a 1-year offline spin up for the soil state. And so that I'm hoping can be kind of usable for any of the ensemble members as long as we're starting from that temperature, kind of moving that time period of when we start.
Okay, thanks.
Mm-hmm. Go ahead, yeah.
Really great talk, Alex. I'm just curious, is there a reason you chose CSM2 for this rather than something like Mesa Clip, which is higher spatial resolution?
Yeah, great question. So this has been in the works for like 2 years. So Mesa Clip didn't exist when we initialized this idea. I would really love for the next iteration of this to use Mesa Clip.
Yeah, thank you.
Mm-hmm. Okay, thanks, Alex. We'll move on to Justin Small.
I'm going to talk about predictability in high-res models in the Gulf Stream and eddying region, which you'll see on the right. top right, you can see eddies associated with the Gulf Stream. This is work that's been funded by two NOAA projects. One is looking at precipitation, one's looking at sea level. I'll explain why they're related to the eddies. And Mazica produced all this high-resolution model data I'm going to take advantage of. So it's going to be two parts. Hopefully I'll get through them. Part one is eddy predictability. It's chaotic eddies. And the motivation is S2S predictability of precipitation. And we heard talks this morning about everything comes from the tropics. So we'll kind of revisit that with high resolution. And then part two is on predictability of actually the kind of the main current in the Gulf Stream. Offshore of the separation point, motivation there is East Coast sea level, which is key topic. And I'll focus on 1 to 2 years of predictability there. And I'll be using this set of high resolution prediction data sets produced part of Mazica and Steve and Gokhan, many people involved in that, 1/10 degree in the ocean and 1/4 degree in the atmosphere, 10 ensemble members, 21 sets of start dates, and I'll also be comparing briefly with the 1 degree decadal prediction and the ensemble members just created by small perturbations to the atmosphere. The ocean's the same initial conditions. So the initial conditions come from the forced ocean, sea ice, high resolution, and there's a total of 5 cycles of 1958 to 2018. The predictions run off cycle 5, so it's run quite a while by the time it does that. I'll just say here that for variables SST and SSH, I'll be comparing HRDP ensemble members with FOSI. But for precipitation, FOSI does not have precipitation, it's an ocean ice model. So I'll be comparing HRDP ensemble means with individual sets of HRDP members, basically different examples of the truth. And there'll be statistics, which are fairly standard, being applied. So part one, eddy predictability. I came into this because I knew eddies are predictable for some period, like a few months. And I know that from the literature and my own experience. I also know the precipitation response to small-scale SST. So maybe there'll be some predictability. Some details on the data. I'll be using high-pass spatial filter for most of the results. I'm looking at chaotic eddies. I'm just going to use the model system. I'm not comparing with observations here. This is a case study example. Top panel is from the FOSI HR. These are spatially filtered anomalies of SST, so you see the plus or minus signs in the Gulf Stream, few degrees C anomalies. Top is the target, FOSI HR. In the middle is the signal HRDP ensemble mean. And in month 3, which is on the left, HRDP, if you look in the middle, colors, HRDP ensemble mean looks like FOSI, which is the contours. And the spread is reasonably small, the bottom panel. If you go later on to month 11 for the eddies, the predictability has basically gone away. The middle panel signal is very weak, and the spread is very high, the bottom panel, bottom right. That gives you an idea, that's a case study. Then you can compute these skill scores, anomaly, correlation coefficient, and MSSS. And I do it for a box in the Gulf Stream on the left, and the box is shown in the plot on the top there. And you see the decay with time on the x-axis of the ACC, that's the thick solid line, going down from 1 to about 0.6 after 70 to 90 days or something. It gives a time scale of predictability. It's basically 2 or 3 months. If you use MSSS, it uses amplitude information as well as phase. It's harder to get it right. It decays off after about 2 months to 0.6. Persistence does very poorly. This means the dynamics of the HRDP system are doing well in capturing the eddies for 2 or 3 months. On the right is an example from the Eastern Basin. Predictability time is much longer, but the anomalies are small, so maybe less interest. And, oh, okay, too far. This is the motivation. I'm now looking at precipitation. This is convective precipitation, which we know in CSM is the part that responds to this small-scale SST. And I'm showing the third month, and the skill score is called signal to total. It's defined up there. The three panels left to right are HRDP filtered data, spatially filtered. In the middle is unfiltered data, and on the right is the decadal prediction system. And we were getting skill scores around 0.7, 0.8 in the Gulf Stream system in the filtered data. So we got some skill for precipitation on S2S timescales is the kind of summary of this. And you also see it in unfiltered data, which is in the middle, and it's higher than what you see in DPLE. I'll point out DPLE is not negligible. I want to move on to part two. We're now looking at sea level, East Coast sea level, because previous papers have noted a connection between the Gulf Stream variability and East Coast sea level. There's a mixture of forced and a lot of intrinsic variability in this region. For this analysis, I will not be applying a spatial filter, and I'll be comparing with some observations will come in. It's just to kind of introduce it. On the left panel is the anomaly correlation coefficient month 11, and a lot of it is pretty weak. It won't be significant below about 0.5. But if you kind of zoom in on that bottom left, there's a region of high predictability, basically where the Gulf Stream separates. That's where the northern box. I'm also interested in the coast and the Florida current, so you can see Charleston and the box for the Florida current. And on the right is an estimate of how much intrinsic variability is in the system. It's from a nice paper by Donatelli et al. And the caption's not quite right. It's the fraction of intrinsic variability to the total variability. And it ranges from, in the coastal region, it's around 30%, the kind of greenish colors. And then in the Gulf Stream eddying region, it's 80 to 100% intrinsic. That was part one of this talk, was talking about the 80 to 100%. But now I'm interested with the connection with the sea level. This is an example time series in the Gulf Stream box, which is illustrated again on the right, where we had high predictability. And I'm showing here just the first 2 years of the prediction. The solid line in both panels is from FOSI. It's a time series in that box of anomalies. And the dashed line is the prediction. In the top panel, you can see they roughly overlie for at least 2 years. In the bottom panel, I displaced the two lines so you can see them more clearly. And the prediction is, in most cases, following FOSI quite well. So there's quite nice results. And I'm going to bring in some observations. Charleston tide gauge is in the top panel. It's the thick dashed line. The Gulf Stream from satellite data is the solid line in the top. If you ignore the red line initially, what's of interest is that Gulf Stream satellite data actually follows the tide gauge quite well. So the connection between Gulf Stream and US East Coast sea level. Red is the mean of all FOSI cycles. We remove some of the intrinsic variability, I'd say. It has, it kind of has some matching periods with the observations, but also some not matching. If you look at the bottom panel, shows all the cycles, you can see the huge variability. And now I'm going to connect it to the southeast coast more directly. The bottom panel is the tide gauge at Charleston, satellite data of Charleston and FOSI. They do quite well. It's all the cycles are shown there. They all have similar phase, a little bit of variability. However, the top panel shows the Gulf Stream has a huge amount of variability. So it's a bit hard to say how important is the Gulf Stream to the East Coast sea level. So much variability in the top panel, much less in the bottom panel. And I want to leave time for questions. I just want to point out limitations, always important. On part one, convective precip it's only part of the precipitation. The large scale is not responding so much. Most of the precipitation is over the ocean. It's point-wise analysis and spots it over the ocean. Perfect model. We have done a lot of work into how good the model is. It's quite good. Part two, I would say we kind of need more members, more cycles to really distinguish forced and intrinsic variability in the Gulf Stream box. I'll finish there.
We can take one question. If not, thanks, Justin. And we'll move on to Evan Meeker.
All right. Hi, everyone. My name is Evan Meeker. I'm a PhD candidate at the University of Wisconsin, working with Liz Maroon. And this is some work that I've been doing with Hui and Steve here. And we're going to look at the predictable response to strong wintertime forcing from the Aleutian low. So as Steve mentioned, this is work that we're doing as part of the Decadal Climate Prediction Project. Specifically, these experiments are run as a pilot project to establish protocols for DCPPC and CMIP7. The full experiment has 3 regions: North Pacific, North Atlantic, and Southern Ocean. I'm going to show some North Pacific results today. And the design is an expansion of the Kim et al. 2024 paper, where they force climate models with heat flux associated with the NAO in the North Atlantic, and find that the multi-year oceanic memory led to a predictable delayed response in AMOC for up to a decade after the forcing is turned off. So we're going to be forcing the model with the Aleutian low, and we define that here as the first EOF of DJFM sea level pressure over the North Pacific. And a couple potential responses we're going to be looking for include shifts in the Kuroshio/KOE region, potentially an ENSO/IPO response through tropical-extratropical interactions, and teleconnections to the North Atlantic through jet stream influence or polar/NAM changes. So we take that sea level pressure pattern and we regress it onto surface heat fluxes and wind stress. And we take those values, which I'm showing in the top right here, and we feed it into the ocean model through the coupler with a freely evolving atmosphere on top of it. And this is a 2 sigma surface heat flux and wind stress forcing, so a pretty strong hammer. This is forced every winter in DJFM with a linear transition out of the season, and 10 years with the forcing, and then 10 years afterwards with no forcing to see what the response is afterwards. This is a 10-member ensemble with plans to extend to 20 members with 10 that have opposite signed forcing. And each member is initialized from PI control with a 40-year offset between each of these ensemble members. And we've also ran the equivalent experiment with no wind stress forcing, just the surface heat flux in that pattern. And I'm going to show for the first couple slides here differences between the surface heat flux only and surface heat flux plus wind stress responses. So this is the years 1 through 10 average in winter for both of these experiments. So this is while that forcing is being applied. And on the right, you see that when we are only applying surface heat flux, we get a response from the system that looks about the same as what we're putting into it. So that's a good sanity check. But when we include the wind stress forcing, we see both a stronger surface heat flux response in the magnitudes overall, as well as a much stronger response in the Kuroshio region. And if we look more directly at the wind stress, so this is the barotropic stream function for each of these cases, and there's a fairly weak response when we include when we don't include wind stress, but when we put wind stress in, there's quite a strong response in the gyre circulation. So this is a spin up of both the subpolar and subtropic gyres. I think this is interesting, especially we're hoping to do some high-res simulations of this, and it'll be cool to see what happens when you're explicitly resolving the KOE region. So now I'm splitting that up into year by year, and so this is for the surface heat flux and wind stress forcing. And what we see is this gyre response is pretty immediate. So in the first winter, we're already seeing really strong changes in the gyre circulation here. And it's pretty consistent through the 10 years that we're applying the forcing. It looks like once we turn the forcing off, there might be a secondary response that you see in years 12 through 13. And what I think this might be is so that subpolar gyre seems like it's expanding farther south from our imposed forcing. So when you let go of it, it seems like the subtropical gyre is actually returning to its preferred state within the model. So for the rest of this stuff, I'm just going to be looking at the experiment with surface heat flux and wind. And now this is the sea surface temperature response here. So in the first 10 years on the left, we see locally there's a strong surface SST response in the region, as well as what looks like a weak IPO positive response. And you can kind of see the mirroring across the equator there. After we turn the forcing off, it seems like this cold SST anomaly is fairly persistent locally, but not a very strong response outside of the region. I did run a signal-to-noise test following Rubik-Robert et al. In 2017, and these values vary between 0 and 1 and are effectively measuring how much variance is explained by the difference between these ensemble means versus the variance within all of the ensemble members. And you see there's a really strong response locally when I'm applying the forcing, not surprising, and that response stays relatively strong in the North Pacific in years 11 through 20. In the tropics, there's not, the values aren't that high, but there's quite a bit of interannual forcing going on here as well. And I'll show a little bit of that. So I wanted to, again, break this down into year-by-year forcing. So unlike that wind stress, that gyre response, we see in the sea surface temperatures that in the North Pacific, it takes 3 to 4 years to get those differences up to the values we're seeing in the decadal average in the Northeast Pacific. And then if you look at the whole 10 years that we're applying the forcing, actually in the Kuroshio region, you see larger and larger differences growing throughout those 10 years. And as I said, so that IPO positive response that we're seeing is averaging over quite a strong interannual variability in the tropics. And finally, just after you turn the forcing off, you see that these differences in the Kuroshio extension region especially take, again, 3 to 4 years to die back down to a climatological state. Okay, so now I'm going to look at the sea level pressure response. And these are, again, averages over the first decade and then after we turn the forcing off. So we're applying this forcing in a Aleutian low pattern, but the sea level pressure response is somewhat offset from that with low pressure over Alaska and kind of going into the Arctic. We also see somewhat of an NAO negative response while we're applying the forcing, which I'll talk a little bit more about later. After we turn the forcing off, we actually see a fairly large response over Northern Europe, which I'm honestly not entirely sure how to interpret. But looking at the North Pacific again, we see some persistence in that low pressure, high pressure dipole. But looking at the signal to noise ratio, it's fairly weak here. And you do see, even in the decadal averages of the individual ensemble members, quite a bit of difference in sea level pressure here. So this is not a very large signal that we're picking up, even locally. And so this is a pilot project that we're doing with a number of other models. So this is credit to Ned Williams at the Met Office who put this together. So this is sea level pressure for CESM in the bottom left here, but then also the UK model, Indian model, and Norwegian model. And we see that the sea level pressure response in the North Pacific is fairly different between these models, ranging from actually a fairly large high pressure response in the UK model to very strong low pressure response in the Indian model. So I think there's more to be done here, figuring out what exactly the atmospheric response here is on the decadal timescale. So just to finish up, that NAO pattern that we see in the first decade here does seem like it's driving a small but significant decrease in AMOC strength, which is a little bit surprising to see. And what this tells us is that potentially, if you can imagine a decade where you have about normal forcing over the Atlantic, but you have a very strong forcing over the Pacific in this pattern, you might end up having some amount of predictable slowdown in AMOC for that time frame. So in conclusion, we imposed a wintertime aleutian low associated surface heat fluxes and wind stresses to CESM on a decadal timescale. We drive a spin up of the North Pacific gyre circulation and large local SST anomalies, which persist for 3 to 4 years after the forcing is shut off. And an interbasin connection to the NAO may indicate that there's a predictable AMOC response to strong Aleutian low anomalies. And also, so these protocols will hopefully be finalized this year, and in the next few years, be able to do some multi-model studies on this sort of thing. I just want to say that I'm going to be in Boulder for the next couple of weeks, so if you're interested in talking about this or have other model experiments you think would be cool to run, come have a chat with me. I'll be around. Otherwise, happy to take questions.
We have plenty of time for questions.
Thanks. Very interesting talk. So it looks like the tropical, tropical Pacific is almost independent of the forcing you import.
Yeah.
Is it?
That's at least on this shorter time scale. So it's a weak IPO response, and you would expect there to be strong internal variability at that shorter time scale. I was actually hoping to see a little bit more of a response in the tropics here, and actually some of Hui's work forcing the SAM, you actually get a stronger IPO response from your southern hemisphere forcing than we did from this northern hemisphere. I think there might be some ways that you could tease out a little bit more of that signal, or perhaps think about whether or not the Aleutian low pattern is the right pattern for getting a tropical response versus other patterns over the North Pacific. But yeah, it was weaker than expected, and that was probably the main source of what I would have expected the global response to come from, is an influence on the tropics, which then proceeded to influence globally. So we're not seeing as much of that as I would have thought beforehand.
Okay, thanks.
Thanks, Evan. We'll move on.
Thanks.
The next speaker is Jacob Cohen.
Great, thank you. Hi, I'm Jacob Cohen. I'm a postdoc at the Cooperative Institute for Climate, Ocean, and Ecosystem Studies at the University of Washington and NOAA PMEL. This is work that I did at the end of my PhD at the University of Washington that I'll be presenting today, looking at decadal predictions of sea ice and ocean heat transport into the Arctic. So hopefully not surprising that over the last several decades, Arctic sea ice has been declining. On the right, showing a plot of recent September low sea ice extent with an outline of the 1981 to 2010 average sea ice. And this sea ice decline has implications for communities in the Arctic, as well as shipping and climate responses as well. But if you look closer at this plot, there's kind of two stages where we have sharp sea ice decline in the 80s and 90s into the 2000s, and then since 2007, a slowdown in Arctic sea ice decline. And this has been explored recently in several papers. This one by Mark England looked at a large ensemble of climate simulations and showed that these 20-year pauses or hiatuses in sea ice loss are not that uncommon or not that rare, and do exist and are consistent with internal climate variability. And then a paper from 2015 that Steve Yeager led showed that this slowdown in Arctic sea ice loss, primarily in the Atlantic, was predictable in decadal climate simulations and predictions. So looking forward, we want to expand on this work and look past Atlantic wintertime sea ice, include summer sea ice, include Pacific sea ice as well, and then an updated view on this 10 plus years later, well into this sea ice loss hiatus, to see if we can predict anything for the future. So the mechanism of predictability that was identified in that Yeager paper showed that the winter NAO, this persistent NAO pattern, was related to North Atlantic deep water formation, which influences AMOC strength, heat transport northward into the Arctic. And the patterns that we see are high NAO and North Atlantic deepwater formation in the 80s and 90s. This coincided with strong sea ice loss. Low North Atlantic deepwater formation and a low NAO pattern over this sort of 20-year period from 1995 onward. And then more recently, a return to high positive NAO. This persistent positive NAO pattern has influenced AMOC strength that we are starting to see. So here I'm showing AMOC strength from a forest ocean sea ice simulation, and then in blue, those are observations from the Scotia array, which was mentioned in the ocean model working group. They don't agree exactly. They're also not at the same place, so that's somewhat expected, but both do show this increase after about 2015. And this paper from Zhang et al. Showed that AMOC strength is well correlated with heat transport at even further north latitudes into the Arctic Ocean with some lag. So we expect that this pattern will influence Arctic sea ice. And they had a nice figure that kind of summarized this. So NAO leads to AMOC changes. This leads to enhanced heat transport into the Arctic, which leads to, across summer and winter, reductions in sea ice in the Arctic. And then from the other side, on the Pacific, you can also have heat transport that influences sea ice. And I won't be talking about the Arctic dipole today. But from correlations in the forest ocean sea ice run, we can see where heat transport is affecting sea ice mostly, and it's mostly what you would expect. Atlantic Ocean heat transport is leading to reductions in sea ice in the Barents Sea, and Pacific Ocean heat transport leads to reductions in sea ice in the Chukchi Sea and kind of central Arctic areas. So now that we have this picture set up, we can start looking at decadal predictions. We have the initial conditions that lend to being able to understand what might happen in the future. So using initialized predictions from the CESM2 decadal prediction system, we can look at sea ice predictions and ocean heat transport. So a lot of people have mentioned SMILE today. The decadal prediction system takes the November initializations from the seasonal prediction system SMILE and extends them out to 10 years. So we're left with 10-year predictions with 20 ensemble members each from 1958 to 2023. And we can look at, we take annual averages for those, so we have 10-year predictions, and we can look at the anomalies from those predictions as well as short-term trends. So we can take the trend over those 10 years and compare that with short-term 10-year linear trends from observations. For ocean heat transport, we compare anomalies and trends to FOSSI, and that's the forced ocean sea ice simulation. And for sea ice, we compare to FOSSI and observations from NSIDC. We define heat transport across a number of gateways, and then kind of simplify those down to Atlantic Ocean heat transport through the Fram Strait and Barents Sea opening, Pacific Ocean heat transport through the Bering Strait. And we also split the Arctic in half to look at regional-ish sea ice on the Pacific side and the Atlantic side. So now we can look at what we see. Here I'm showing heat transport at 50 degrees north in the Atlantic, and we see that 5 to 7 years ahead of time, we have reasonable prediction skill from the decadal prediction system. Moving further north, there's a lot more variability through the actual Arctic gateways. So here we have more skill looking at these 10-year linear trends. Here the red, on the top the blue, and on the bottom the orange is the prediction. The spread is shown in shading, and the black is trends or anomalies from FOSSI. And we see that, again, we have pretty good skill getting these oscillations in heat transport correct. Better skill in the Atlantic than the Pacific on this annual timescale, which is also expected. And these 10-year linear trends in ocean heat transport through these gateways can be pretty well related to sea ice extent trends in both regions. So it's more related in the Pacific, where the ocean heat transport is, when it's strongest, really connected and occurring at the sea ice edge. But in both of these regions, especially in the last 20 or 30 years, have strong relationships with sea ice extent trends. So we can look at these trends and anomalies from the decadal prediction system. Now, again, orange is the prediction, black is the forced ocean sea ice simulation. For sea ice, we do have satellite observations from NSIDC as well. So for this 5 to 7 year forecast of anomalies, most of the skill is coming from this long-term decline. We can see some variations around that, but we're going to be more interested in predicting these short-term 10-year linear trends. When we do this, we see that the decadal prediction system does a pretty good job, especially in Pan-Arctic sea ice extent and Atlantic sea ice extent in the annual average. We see especially these strong negative trends in the 90s that were well captured in the prediction system. The return to a zero trend, so that's the sea ice hiatus around 2007. And then looking forward, we see a steep drop-off where our more recent predictions that we don't have long enough observations to compare to show a steep decline in future sea ice extent. When we look just at summer sea ice extent, these all kind of blow up and get bigger. But similarly, we are able to capture both periods of strong sea ice decline and periods of weak sea ice decline. And again, across all three regions now, we do have better skill in summertime Pacific sea ice. In all three regions, we are predicting accelerating decline of sea ice in the future. And this is now comparing that to the summertime ocean heat transport. And we can see that we have better prediction skill of ocean heat transport in summer in the Pacific, as I mentioned, and these are related and is likely what's giving us predictive skill for sea ice. So as a quick recap of what's happened that is giving us this prediction skill and then what may happen in the coming years, we've had this persistent NAO positive state, and that has shown up in the AMOC signature as well and in heat transport northward. The CESM2 decadal prediction system is predicting increased ocean heat transport through the Arctic gateways in the Atlantic as well as in the Pacific, which is not affected by that NAO and AMOC signal, but is also showing weak but positive trends in the future. And then that translates to a return, potentially a near future end to the sea ice loss hiatus, where we see stronger and stronger declines of sea ice across the Arctic. When we look at that spatially, we can see that there is pretty much no area in the Arctic on these, in the 2023 initialized predictions that shows anything but sea ice loss and warming conditions in sea surface temperature. The strongest signals are in the Atlantic, where there's a lot of warming that is predicted to occur at the sea ice edge that coincides with sea ice loss there, but also in the Pacific, we see widespread warming in the Gulf of Alaska and the Bering Sea that influences sea ice via ocean heat transport. And with that, I'll leave some conclusions up here and take questions. Thank you.
Thank you. One of the questions I had, so you were showing these annual Pan-Arctic or Atlantic Pacific. Have you started to look, or are you considering looking at different seasons? Because that can have big impacts for the people who depend on these areas.
Yes, so here I also had summer, which shows those like stronger trends. I have this for winter as well. It's a lot to try to show all of those at once. And then, yeah, trying to do like a moving window as well to get the whole picture.
Great, thank you.
Yeah.
Really great job, Jacob. I'm curious, maybe I missed this. I see a discrepancy between foci and observations around 1990. Do you have any idea what's going on there?
like
Yeah, like the left-hand side, right? Like the blue and the black. I don't know. Maybe that's, yeah.
I don't have a clear idea. These short-term trends probably have some variability around. The trends, if you look at the left plot, even the overall trend in the observations is slightly stronger than the overall trend in Fosse.
Yeah.
Just
I see.
looking at that. So there's some discrepancy around those, and
And you're
I
just
haven't looked.
compounding that when you're doing the trends.
I think so. Yeah.
Okay, cool. Thanks.
They also have different regional masks, which is because NSIDC is 1/4 degree, satellite CSM is 1 degree. So, yeah.
Thanks, Jacob. We'll move on. Our next talk is online by Dylan Oldenburg.
Hi, everyone. Okay, let me share my screen here. So, okay, done. Okay, hi, everyone. So I'm Dylan Oldenburg. I'm going to be talking about the subpolar North Atlantic, upwelling heat content, predictability, and CMAP6 decadal prediction systems. So I'm a postdoc at NCAR. I work with Steve Yeager, Gokhan, Isla Simpson, Hu Kim, and Liping Zhang is also a co-author on this work. And so the goals of this work first are to determine the subpolar North Atlantic upwelling heat content predictive skill in the CMIP6 decadal prediction systems. And for this, we use all available models that have decadal prediction systems that we can access data for, so high and low skill models. And the question here is, so in Jaeger 2020, it was found that the primary mechanism that drives predictable upwelling heat content in the subpolar North Atlantic in CESM, which is a high-skill model, CESM1, is propagation of these deep ocean density anomalies or thickness anomalies that form in the Labrador Sea and propagate towards the Mid-Atlantic ridge and persist and accumulate, which then drive changes in the sea level gradient and hence enhanced near surface flow, northward flow towards the subpolar North Atlantic. And then also topographically coupled gyre circulation and overturning circulation, which also then impact the subpolar North Atlantic upwelling heat content. So the question is, do these linkages exist in all of the other models that we can find here, or at least in all other high-skill models that are not CESM? And if they do, if this mechanism does appear in all the models, even the low-skill models, then is it just that the variability is incorrect in some models? And so we use these CMAP6 DCPP hindcast simulations. So they're 10-year hindcasts initialized from different reanalyses and observations. And so this shows the predictive skill of the upwelling heat content, so 0 to 300 meters for the forecast years 6 through 10 of these different hindcast simulations relative to EN4. All of these are computed using ensemble means, generally between 10 and 40 members, depending on the model. So there's a wide range of predictive skill across these models, and we're interested to see what drives this large variation in skill. And so this shows the anomaly correlation coefficient averaged over the SPNA box, which was highlighted in that previous figure, in those previous figures. So we can see that the highest skill models over years 6 through 10 are CESM1 DP, which has been studied extensively, including in Jaeger 2020, CESM2 as well, which is a fairly similar model, at least in the ocean, and then CMC having the third highest skill, although it's significantly lower skill than CESM. And the lowest skills seen here are CAN ESM5 and F goals, which both have initially high skill, like at the first month after initialization, but then that rapidly degrades over forecast years. The upwelling salinity shows a similar picture, except CMCC shows low skill at later forecast years. And so for the rest of the analysis, we'll focus on these top three models and these bottom two models. So CAN ESM5 and F goals for the bottom two models, and then CESM1, CESM2, and then CMCC for the top three models. And so we can see that all of these models initially accurately predict variability seen in EN4, so the first month after initialization. And we can see on the top right here the climatological drift over forecast years. So CESM models show a large drift despite showing high skill at later forecast years. So we can say that there's no clear indication that higher climatological drift means lower skill. And F goal shows a small drift despite being a low skill model. And so this shows how the upwelling heat content varies over historical years for these later forecast years of these hindcast simulations. So we can see here that the poor skill, well, where the low and high skill models really diverge is during this 1990s to 2000s event. This main warming event in the SPNA in the 1990s, which is associated with a large Labrador seawater production event. So densification of the Labrador seawater leading to strong AMOC and hence propagation of warm water. And this is not properly represented in low-scale models. And we can see how this plays out with the 5-year low-pass filtered EN4 data. And so we can see here, first the Labrador seawater production, production of dense anomalies at depth in the Labrador Sea, which then propagate eastwards. And then we see a subsequent warming of the SPNA, so south of Greenland, south of Iceland, which then persists until the mid-2000s. And we look at CESM2. This is one of our highest skill models. CESM1 looks fairly similar. I don't have time to show both. And so we can see here that indeed there's a strong AMOC. We have dense anomalies being formed in the Labrador Sea, which then propagate eastwards, and they persist near the mid-Atlantic ridge. We have a spin-up of the subpolar gyre, and then a subsequent warming of the subpolar North Atlantic. That's at forecast year 1. We look at the later forecast years, the verification years for those later forecast years of the hindcasts. We still see the same process playing out. We have a strong AMOC driving warming in the SPNA, and we have these dense anomalies propagating eastward towards the mid-Atlantic ridge, and we have a spin up the subpolar gyre. But in CMCC, so this is our third highest skill model, we have only, and at the later forecast years, so on the right here, we only see a sporadic increase in AMOC. And we have really only an increase of the upper limb, so the North Atlantic current, and of the very deep limb, but we don't have a broad strengthening of AMOC the way that we see in CAN ESM5. We do see some level of propagation of density anomalies towards the mid-Atlantic ridge, and of course, this warming occurring in EN4 is still represented relatively well in this model compared to the other models beyond CESM. So that's interesting. And if we look at 45 degrees north, just across, just a mock at 45 degrees north, we also see that there's a big discrepancy between the CESM models and CMCC. CMCC at these later forecast years. You can also look at years 3 through 7 with a similar picture. Years 6 through 10, 3 through 7. It's really just limited to this upper limb and this very deep limb in the AMOC, where we have this strengthening occurring in CMCC. And we expect to see like a strong link between these density anomalies at depth and the sea level, because we expect the sea level gradient near the Mid-Atlantic ridge to be linked closely to these density anomalies at depth. That's part of the mechanism. And so we don't quite see that connection as much in CMCC. We can see a very clear link between the two in CESM, but in CMCC, it's a much weaker link. We don't necessarily have depressed sea levels where we have dense anomalies. So that's one thing. And year 1 is just quite noisy. But yeah, years 6 through 10, or if you look also at years 3 through 7, it's a similar picture. We don't have that same link that we see in CESM. Another interesting thing is to look at the sea surface height gradient and the meridional velocity and see whether those are closely linked. So we do see that link appearing in CMCC. So we expect the sea surface height gradient to drive an anomalous meridional velocity, an anomalous northward velocity. And so we do see that occurring to a degree at the later forecast years in CMCC, alongside, of course, what we know happens in CESM1, as well as CESM2. But it is more limited, more to just the very late 90s and through the 2000s, and it's a little bit weaker than certainly in CESM1. In the low-skill models, on the other hand, we just have initially at the first forecast lead year, we have a very strong boost of AMOC, which then drives warming in the subpolar North Atlantic. It plays out quite differently. It starts more west, and then that warm water propagates eastward, so quite different to EN4. But at later forecast years, we have no broad strengthening of AMOC, and we have warming limited just south of the subpolar North SPNA box. And we actually have cooling where there should be warming. And we can see that also when we look at MOC at 45 north. It's just not, it's not representing that strong AMOC at the later forecast years when it should be. And we also see that when we look at the sea surface height gradient. The conclusion here is that the highest skill models show a clear Labrador seawater production event in the 1990s, which drives strong AMOC and hence upper ocean warming in the SPNA region, and the Labrador seawater thickness anomalies persist near the mid-Atlantic ridge. But CMCC only shows a limited strengthening of the upper limb of AMOC and only some level of propagation of Labrador seawater anomalies towards the mid-Atlantic ridge. And it seems like the North Atlantic current is enough to drive this SPNA warming and lead to decent skill of the SPNA upper ocean heat content. And the poor skill models are all over the place. And I'm out of time. Yeah.
Thanks, Dylan. In the interest of time, I think we should move on to Helen Kershaw, who's also online.
Hi, everyone. Hopefully you can see my screen. I'm Helen. I'm a software engineer with the Data Assimilation Research Testbed developed here at NCAR. And I'm going to talk today about a project we've been working on for a seam-based workflow for out-of-the-box data assimilation in CESM. Why the problem matters, what we've built, and how you can get involved. So here's the Earth, picture of the Earth, a model of the Earth, not quite the Earth. Models are biased, right? You're trying to model some particular aspect of it, whether it's weather, ocean forecasting, you never have everything. You're measuring things, so you have observations. Observations have errors, and data assimilation lets you combine these two to get the best possible estimate of what's actually happening. And then local impacts are really important. So you might be interested in the local impacts of carbon capture, or maybe impacts of an oil spill in your part of the world. This example is from last year. A ship ran aground off Hull. And if you live in Hull, local suddenly becomes really important, like what's happening, where it's going to go. And the same applies to things like carbon capture impacts, ocean events, impacts on fisheries. How do we design systems to capture these phenomena? Or a bit more formally, how do we increase usability of infrastructure that translates global dynamics to human and actionable scales? Well, answer, regional modeling and data assimilation. Talk done, right? Only kidding. So that's the motivation behind the Crocodile project, and that's the CESM Regional Ocean and Carbon Configurator with data assimilation and embedding. It's a slightly forced acronym, but it makes for a great logo. And it's a collaboration between NCAR and Woods Hole, and it's really about sort of observationally constrained regional oceanographic modeling. This is the original slide. There's way more people involved now, so do check us out on GitHub. And I do want to stress, like, people are already doing data assimilation in CSM. This is not new. It's very productive. It's been going on forever, way before Crocodile. Here's a reanalysis product with CAM6 and Dart. Check out dart.ucar.edu for all the cool stuff people are doing with DA. So people are already doing it. What problem are we solving, right? And it comes back to usability. So running Dart with CSM traditionally required like quite a lot of intricate knowledge and lots of manual file staging, moving things about, archiving, custom scripts per model, often custom scripts per model per person. And so you needed a lot of familiarity with the Dart internals and the seam scripting as well. And every time you do something bespoke, it's just a multiplier of human effort, right? Like every postdoc, every grad student, every new scientist is paying this onboarding cost. Is an example from Dart, so I like to show our own examples. This is 24 scripts of about 800, 1,000 lines long. You will have to read this and understand it in its entirety. I mean, no, I don't think you do, right? I think we can do better than that. And I do want to caveat the title of the talk, right? DA is never completely out of the box. There's deep science in understanding your problem, your observations, your model biases, diagnosing how much your observations are influencing things, but the infrastructure shouldn't be the barrier. Last year's Crocodile workshop, people were hacking away in an afternoon or two and getting their regional MOM6 cases going. That's a massive improvement over like regular regional setup. And so the goal for 2026 is to do the same thing, but with data assimilation. So what did we build? Dart as a CSM component. So like if you're familiar with CSM, setting up a case should look very familiar. Regular CSM on the left, Dart CSM on the right. So it's essentially like choose a comp set, set up, build. Except with Dart, you switch on data assimilation. So maybe you want it in the ocean, maybe you want it also in the ice, set the flags. And that's it from the CSM user point of view. If you're already a Dart user, maybe you're familiar with this. So this is the Dart name list, but just in CSM format. Everyone loves Fortran name lists, right? So Dart applies globally across all components, but you might want to specify things differently. So you might want to localize differently in the ocean and the land. So you can do that. And then preview name lists, same CSM tools to view them. And it's all Dart, right? We haven't changed Dart. So all the wonderful stuff you can do with Dart, you can read the Dart documentation and just get it going in CSM. So under the hood, we have a Dart interface. That's a layer that connects Dart to CSM. So if you've had a look at like MOM6, same idea. It's implemented as an external system process, which is the bit that lets Dart sit within the seam workflow rather than being bolted on afterwards. We're targeting MOM6 and SICE at the moment because we're a Crocodile project, so we're ocean focused, but we want to design it with all components in mind. And then the other key component of data assimilation is observations. Right, so people use Dart with the whole Earth, so from like soil to space weather and everything in between. So we have a bunch of obs to deal with, but luckily for Crocodile, who we have developed this product called CrocoLake. And so it's one database, a bunch of ocean obs that we can just query and use for data assimilation. And they actually have a model to obs comparison tool, which uses Dart as a backend. So if you're not quite ready for full-blown DA, but you want to compare your model runs to your observations, that's a great tool. And then how do you prepare observations? So I tend to think of observations like boundary conditions. They're an external source of information from outside your model, and you need to get the correct info, required info at the correct time. So we have a tool to do that, .obsgen, configure your experiment, what observations you want, when you want them, how often you want to assimilate them, and then you choose a source. So for Crocodile, it's going to be CrocoLake, but we are experimenting with other things like the NOAA-NASA Joint Archive, synthetic obs, if you have a nature run that you want to sort of create into fake obs or synthetic obs to run Aussie experiments. And this tool will generate all the things that Dart is going to read during case run. And then doing a mention on the diagnostic side, which we're also thinking about, we've created some Python infrastructure for managing observations and obspace diagnostics. Previously, this was Fortran and MATLAB. which you can still use, but now there's Python. And you can say, so what, right? Same thing, different language. But we think we've really opened up some interesting work, moving to the language of data science and interactively exploring your obs. So this is a screenshot of a tutorial that was happening this week. Moha's teaching this. It's like real-time regional ocean DA in a notebook form. So that's really cool. And just to show that these tools go beyond Crocodile. Because nothing lives in isolation, right? We wrote these tools to slot into the Crocodile notebook setup, but we're just finding them useful for all sorts of different things. These are pieces of a larger ecosystem that's designed to work together. And this is the Crocodile ecosystem. This isn't even all of it. Crocodash, which is all about setting up a case. Manish is going to talk about this afternoon. We have Crocolake, a database of observations from Hui, Dart, which Jeff will talk about next. All sorts of stuff, all sorts of ways to get involved. And we really want you to bring your expertise to this. Like, I'm a software engineer, I like to build infrastructure that people use, right? So help shape what's next. And we've got 2 ways to get involved coming up. There's the Crocodile Workshop, that's in September. I think you can still get travel support, actually, the deadline's coming up. So this could be you if you want to play with setting up regional modeling for the places you're interested in, if you want to add DA, if you want to play with model to obs. Highly recommend that. It's a really good workshop last year. And then this isn't announced yet, but stay tuned. There's going to be a workshop on novel observation pipelines. So if something like Crocolake excites you, and you'd like to get your observations into Crocolake so other people can use them, if you want to think about having your observations used in DA pipelines, this might be for you. I'm super interested if people have observations that would require multiple models for a comparison. So if you're measuring something that would really need like the ocean and ice, sea ice, ocean atmosphere, all 3, I'm really excited about that. That'll shape what we build in the future. So that's my email. I think I've got plenty of time for questions. But yeah, and if you have better ideas or you think, you've got cases that you would think be interesting for Crocodile, let us know.
We do have plenty of time for questions, if there are any. No questions. Thanks, Helen. And now, last but not least, Jeff Anderson, who requested a short time slot. That's why he got the 6-minute.
Right before lunch, too. So what do I have to do to get to my slides? There we go. Okay, so following up on Helen, I'm Jeff Anderson from the Data Assimilation Research section. We make Dart, which Helen talked about. A super quick review of data assimilation, which Helen already set up for me, is it takes prediction models like the ones many of you run and observations like the ones many of you use. Data assimilation combines forecasts, ensemble forecasts in our case, with observations to generate an analysis, which is used for initial conditions and all kinds of diagnostics. And of course, one of the key important things for applications here is using these things for initial conditions for different lengths of predictions. But there's lots of other stuff you can do too. You can identify systematic errors in the model. It is now long since forgotten, but I actually coined the phrase confronting models with observations about 35 years ago, and it is spread into this community from different communities. You can also directly estimate parameters, which is being done in various other ways in this community. You can also work on the observations themselves. So what is Dart? Helen already gave you a little bit of background on specific things, but it is a state-of-the-art DA system for geoscience applications. It can also be used for data assimilation research, and you'll see the fruits of some of that in just a minute. A professional software engineering team, Helen was an example of that team. She leads it, and then the rest of the people that are available to answer questions and help support also. And a statement that we actually have had for years on our homepage is that you need state-of-the-art DA to really do the best you can possibly do for research on prediction, predictability, for model development, including model emulation these days, and improving observation systems. So I've showed this slide for years. It's stolen from a CESM slide from earlier. This is a subset of the large geoscience models that have interfaces and work with Dart. The red ones are NCAR models. I'll highlight that now with yellow. These are CESM models that work with Dart. Every one of these has at least one peer-reviewed publication. Many of them have tens of peer-reviewed publications through the years. And I left off Marble on this. I don't know how that happened. So Marble's in here too. Just as an aside, we're also starting to work more with DOE models again. So we've recently got EAM and ELM working in Dart also, and so we'll be expanding there. Lots and lots and lots of observations. Helen gave you a little information about that just for the ocean, but those observations exist across the Earth system. Now the key point of today's talk. So historically, we've had available in Dart weakly coupled data assimilation that might work with CESM components. So above the dashed line here, coming in from the left, you might have forecasts for CAM and for CLM. Those could be from a coupled model. Those could be from uncoupled models forced in some way. And the way the assimilation has worked is that we have computed forward operators, that is, simulated observations for CAM, and then assimilated those in CAM. And at the same time, we can assimilate the observations of the land in CLM. The key point here is that observations of the atmosphere impact the atmosphere, but not the land. Observations of the land impact the atmosphere, the land, but not the atmosphere. And if you can excuse the egregious grammatical error in the final bullet point, this is suboptimal, just like the grammar in that bullet point. What we've been able to do now recently in Dart is through some actually really minor software modifications, we can do strongly coupled DA. And the flow chart for this, the details aren't important to you necessarily, looks like this. We can initially assimilate the atmosphere observations in the atmosphere model and in the land model. And then the Dart infrastructure allows us to proceed to assimilate the land observations in the land model and the atmosphere model. This is a specific algorithm that is unique to the way that Dart is set up. And so all the other assimilation systems out there in the world, which are not as supportive of CSM as ours, also require tens of thousands of lines of custom code for each combinatoric choice of models. So if you do CLM with CAM, if you do CLM with MPAST, you have huge development chores. There is no development left for the actual core code anymore. There is still scripting, as Helen mentioned, but that is also being modernized quite a bit. And this trivially generalizes to if you want to do strongly coupled DA with CAM and CLM and MOM and Marble and CICE all at the same time. So the infrastructure now exists. What doesn't exist is scientific collaborations to use it, although a number of people I see in this room have said over the years that they would like to do strongly coupled DA to eliminate some of these spin-up shocks and other things. So like Helen's last point, we are actually looking for collaborators. That's the point of this talk. Infrastructure exists. If you want to be the first person to use it, if you want to be the first team to use it, we'd be happy to support them. So thanks for your attention.
Questions for Jeff?
Just wondering what it would cost to do a full reanalysis from, say, over the satellite era. Is that something that's feasible to do?
It would cost a lot. Kevin's sitting in the room. With earlier versions, we have done land-only assimilation. Nick Petitella, who I don't think is in the room, oh, Nick's back there. Nick is currently running a reanalysis at moderately low resolution in Wacom X. The actual detailed numbers would be something that would have to be discussed. We have discussed it at the leadership level before. It is viable, but it is super expensive.
I would just follow up. And there's a sense, emulation can make things a lot cheaper. What are your thoughts on the route of emulation to help speed Ensemble DA?
So if you saw on that list, no one read it in detail. There are a number of emulator models actually on there that have worked with Dart and which Dart interfaces exist with. The common problem continues to be that the emulators are not providing enough variability, enough spread in their ensembles at this point to be state of the art. If you want to sacrifice that, then this is a trade-off in cost versus capability and other things. Certainly one could do evaluations of the impact of the strongly coupled in a suboptimal model.
Quick question. If you do coupled data assimilation, there's a lot more uncertainty in ocean or land. Will that contaminate the atmospheric reanalysis and it'll be worse for certain purposes?
So I don't think there's any evidence that that would happen if you had appropriately tuned localization. Localization did not come up explicitly in my talk here. It is the need to take into account the strength of the correlations between the different components. Alicia Karspek did a lot of work on that in earlier versions of DART and earlier versions of CESM models. The suggestion there is that what you're worried about would not occur. Lunch.
Thanks, Jeff. Yes, lunch. Please join me in thanking all the speakers from both sessions.
Check, check. Check, check.
Yeah, yeah, the last day of the conference. I don't want to sit.
A few more people trickling in.
So who were you watching?
Lunch hour in Portugal against the
Yeah, that's what I was wondering.
DR Congo.
Are pretty good, right?
Hi, everyone. One more time. Okay, we're going to get started. So I think last year we just like briefly said hi and it was super informal, and then I looked up and realized I didn't know half the people in the room, so we thought we'd be more formal this time and actually like put names and titles and affiliations on the slide. So I'm Mike Levy. I'm a software engineer in CGD at NCAR.
I'm Ligia Bernardet. I work at the NOAA Global Systems Laboratory here across town in Boulder.
So we'll just briefly go through the agenda. So before there's a break at 2:30, so before the break we'll have 5 talks. And then after the break there'll be 4 more. It'll all happen here. As you can see, there are some remote, some in person. And then we'll go through updates both from NOAA and from the CSM side of things.
All right, well, so it's very nice to be external co-chair for this group. I think this is a great opportunity to cross-pollinate a little bit between the great community of CSM and things that go on at NOAA. There are a lot of things that go on at NOAA. For the purposes of this meeting here, I'm just going to say a few words about our unified forecast system. So the UFS is a community model, much like CESM. It is a coupled model, so it has, atmosphere, ocean, sea ice, waves, atmospheric composition, etc. components. It can be run both in global and limited area configurations. And even though it is a community model, it is what NOAA uses to draw its code base for operational implementations of a number of applications. This is very small. I can barely see my own slide. I think the important point here to highlight is that we are very open to having collaborations with the community, and a lot of those are done through the EPIC, the Earth Prediction Innovation Center. So there is a little symbol on the bottom right. That is the entity that takes care of community support, but also the code management and infrastructure for the UFS. So the interesting thing about talking about the UFS here in the CSM community is that we share many components between these two modeling systems. So I just listed here not all components that UFS has, but the ones that we have in common. So for example, we both have the FV3 die-core and the MPAS die-core, and I listed in blue those that are somewhat new for us or for the CSM community. So MPAS is new to the CSM, new to the UFS. We're just bringing it in. We also share the common community physics package component that has been in the UFS in research and operations for a number of years, and it's now being brought into the CSM for the next generation CAM-SEMA model. So to me, this is super exciting because it means we're not just sharing software infrastructure, but we'll have the ability to share physics science between the two organizations. We also share MOM6, SCI6, WaveWatch 3, parts of the CLM, in particular the lake model that we use, parts of the atmospheric composition, in particular Musica, which is part of many NCAR models, but also being brought into the UFS. And we use the same coupler. So, wow, there's like not much that we don't share. So just to highlight a few interesting things in terms of recent operational implementations, recent and upcoming. So one application is the hurricane analysis and forecast system. That's our operational model. It runs with 6 kilometers over major oceanic basins like Atlantic Basin, Pacific Basin, with a 2-kilometer moving nest that tracks the storms during the forecast. So that's FE3-based implementation coupled with the regional MOM6 model. Second highlight here is that we will have the implementation of the rapid refresh forecast system in a couple of months from now, version 1. That's a 3-kilometer, also using the FE3 dynamical core. That's an hourly cycling 3-kilometer model over the entire North America that makes prediction of meteorology, weather, but also some atmospheric composition aspects like smoke, which is depicted here in the video. And finally, I'll highlight our global forecast system, GFS version 17, which will be implemented at 9-kilometer atmospheric grid spacing later this fall. And this is the first fully coupled version of the global forecast system. This is deterministic, so just one realization, but we'll have atmosphere, ocean, and other Earth system components. And finally, this is my last slide. I just want to say that NOAA is going into this new, foray, this new adventure, which we're calling the Moonshot, which is the development of a global, fully coupled, convection allowing 3-kilometer Earth system prediction model, which means coupled, using the MPAS dynamical core. So this initiative was announced in January, and it's now, I guess, up to us involved in software engineering and infrastructure to make this thing happen. So we've been very involved with this. You can see here the first MPAS UFS prototype. We already have this running very in simplified configurations, and I think this opens great opportunities for our communities to work together. Thank you.
So just a few CSM updates. And on the first day, Dave went through a lot of the science that went into things, but it's fun to highlight the software side. So a few new features. We have diagnostics coming from the wave model now, and it actually comes out of the coupler because of the way the wave model was written. That was work done by Al Pear. There's a new SEIS flow size distribution. The science of this has been talked about a lot at the workshop, and that was developed by Weddy Roach at AVI in Germany. And when it first came in, there's a huge hit to the cost of the model. But on the software side, Jim and Dave and others were able to work together to bring it down to a more manageable increase. I think it's okay to say this. I'm pretty sure CSM3 is expected by the end of the year, plus or minus a few months. Probably plus. The spin-up is in progress and is currently on track to finish in the fall, and then people in this room will need time to finalize documentation and get the last tags made and all of that. And this will be a production release, so as far as I understand it, that means we'll be supporting CSM 2.15 for 1 more year, and CSM 2.2 support will just like end as soon as the model comes live. I'm a mathematician by training, so I'm drawn to numbers like moths to a flame or my children to a screen. So I thought it'd be fun to go through some stats. So we only made 2 beta tags, but I mean, I think there were like 20 or more alpha tags involved in beta 7 and beta 8, and beta 9's on its way. CAM made 80 or more tags, CTSM made 70 or more tags. I didn't go digging in CEIS or the MOM repos, but those components also made bunches of changes over the last year. It's easy to highlight CAM and CTSM just for the, like they can be run as the independent model through their tag system. I asked around for notable updates from the components, and so this is reporting out what people tell me happened. CAM and SEMA were able to put together an automated GPU test, which is pretty cool. There are a ton of acronyms on the slide. My favorite one is that CIRRUS, the name of our cloud computer, is actually an acronym. It stands for Cloud Infrastructure for Remote Research Scientists and Universities. No, I did that backwards, universities and scientists. But there's an RTTOV satellite simulator. I'm not gonna go through all the acronyms, just that one that I liked. There's TUVX and halogen chemistry in CAM. There's abstract aerosol interface. That's the part of the sentence that I know what it means, I think. They took out Unicon, so I guess that leaves Club is all that's left. They've updated the MPAS DICOR and lots of bug fixes. And Eric on the LAN side said that CTSM is now in the version 5.4 cycle. There's support for Mizroute, which is one of the runoff models. Fates is now supported in transient comp sets, and also updated how its parameter file is read into the model. So that's something that should make it a little more user-friendly. Lots of new data sets. I assume there were more bug fixes than just this one, but this was a big one to get the nitrogen deposition from the atmosphere correctly, and a lot of work on the documentation. And as you can see, it takes a huge team to accomplish all of this. On the infrastructure side, CSM and NORISM are, I think, let's see if I get this right, they're sharing the CDEPS code, and soon we'll also be sharing the CMEPS code that's in progress. And so it's just turning a lot of disparate code base changes into a unified code base with runtime configuration options. And this was worked by a lot of people as well. And Bill Sachs has been working on the water isotopes code, and that's now in the model as well. And so with that, I'll hand it back over to Leisha, and we'll start the talks from you all. I guess we have 3 minutes for questions if there are any.
So I guess we might as well get rolling. We have to get out of this presentation and into this presentation. All right. So our first speaker will be Sherry Volz, and she's going to talk to us about the NSF-NCAR Community Software Facility. Thank you.
So thank you, everybody. So I guess we're official now. We have a website and we have a logo. We still, but what I really appreciate about this logo is it's the people, and the community in our name reflects that. And that is why we're here today, is we need your input. We want your input into how we design this. What I'm going to present, we do not have everything in stone. We're still designing this. We're still figuring out how we operate, what we work on, and we really want the community aspect into this project. So what I'm going to present is what it looks like today. We are not going to get it right the first time. We're going to be agile. We're going to always be adapting and learning and growing along the way. So take that for where this talk is right now. So this is our vision across the organization. And John kind of sorry, John, you presented this at one time with a different kind of idea in mind, but I really appreciated your thought on how these initiatives really work across the organization, because I wanted to frame this talk as to where we're coming in. You know, we're faced with a lot of different complex scientific challenges that we're facing across the organization. And how do we work together? How do we come up with our ideas? How do we actually put these things into action? How do we work together? And that's the goal of these initiatives. And, you know, we're not entirely there right now, but this is where we want to be someday. Hopefully soon, though. So the community software design and delivery, that's where we're at right now. You know, if we go back in time, we were originally put together to help modernize how NCAR as a whole develops and supports and sustains community models. So as we spin up, we're working through all of these different things. We're designing our model and our structure, making sure we have alignment with the scientific goals of the organization. We're here talking to all of you guys. We really want this to be a community, a project. We don't want top level down. We want up coming up, or bottom coming up into our designs as well. It's critical. We also are working on learning from these projects that I'm going to be talking about. You know, we want to understand what's working, what's not working, but also focusing on the ultimate goal of the organization is interoperability, and that was the theme that was discussed earlier today. Thank you, Leisha, for bringing that into this conversation, because that's essential of what we're trying to do here. And then as we go, we're working from implementation to full operation. So here's all our lovely faces to kind of tell us who we are. So we have a board. So John is part of that board as well as Gretchen and Glenn. I myself is the project lead. We have Kate Kazemka as the project manager. Domi Colgrove, who is just back from vacation, is our strategic initiative projects lead, and Suda Kamali is our system engineer lead. So when I think about the software facility, we like to frame it in 4 separate pillars, and I'm going to frame the rest of these slides talking about these particular pillars. So we think about the people. Like I said, our logo is people. It's cultivating that thriving workforce. How do we work better together? How do we train up our workforce? All of that kind of falls under this particular umbrella. Process and governance. Governance is sometimes a scary word, but it's just how do we work together across the organization to really accomplish these really challenging, you mentioned moonshots. This is our moonshot. How do we work and develop these systems across the organization? We also have software development practices. And again, this isn't going into your code saying, please indent 5 spaces or 3 spaces, or your variables must look like this. And it's nothing like that. It's very high level conversations we're having, you know, particularly how do we deal with being inundated by AI contributions? It's things, you know, standardizing across the organization so we can work better together, especially across these boundaries. And then we have the capabilities and the infrastructure, and these are these larger projects across the organization. So deep diving. So the people aspect. So some of you are aware that we had a workshop back in August, and through that workshop, we really wanted to understand how do we develop this software facility. We wanted to learn from external organizations, as well as what are some of the thoughts of what's happening internally, what's working, what's not working. And we just published that report. It's available on OpenSky. So if you're really interested in it, it's a pretty long report. I think it's over 80 pages, but there's really good nuggets of information in there if you're really curious about different types of processes, how to work better together, some tips and tricks of different things going on. So it's full of different kinds of little nuggets of knowledge, and if you're curious, you can check that out. We're also offering our first training session on software architecture coming up. It's a pilot session. We're hoping to offer many more trainings in the future, and we've been going around the organization and really getting some great feedback into what people are looking for training on. And this is coming from software engineers as well as scientists. You know, we are a community. Scientists code, software engineers code. We want to make sure that we bring everybody on board and make sure everybody is involved with the software facility, as well as part of the trainings as well that we're offering. So we open them up for everybody, regardless of your position in the organization. We're also looking to partner more with the software engineering assembly. Thank you, Jesse. So coming soon, we're looking to specifically partner too with establishing travel funds for people within the organization. We have to set up some stuff ahead of time to get that to happen, but we want to make sure that software engineers and scientists around the organization have opportunities to present on software engineering that's happening in the organization. So process and governance, just really quickly here. So it's basically engaging. And part of this, again, is the stakeholder engagements that we're doing here. We're having conversations around the organizations at many different levels, having different types of conversations with people, and presenting here at workshops just like this. We really want to get input into how do we design this? What are some of the roadblocks that you think we're going to hit? What's working for you? What's not working for you? Where are you seeing things happen within your part of the organization and getting that feedback? We also want to be very purposeful in getting external stakeholders' feedback as well. So this possibly will include a community workshop that we're still thinking through those details. But we also want to be engaging with peer or partners to understand what are they doing in this space, how can we learn from you and organize better. So software development better practices, I like to think of these as the foundation of software. And like I said, it doesn't get very deep into the code. Right now we're looking at GPU acceleration, and this is really looking at across the board at the different technologies, what's working, what's not working, evaluating pros and cons, and learning as we go. We also have automated testing, and Mike, you mentioned a couple of the projects already within CSM. So we have some testing going on in CAM and CTSM. The Turbo project is also using some of this technology. We're working with MPAS, we're working with RAL, we're working with ACOM on this. So it's really a cross-organizational effort. We're almost there with HAO. So I put that as an asterisk, and we still need to figure out how to work with EOL. We had some great conversations there, so I'm really hopeful we can bring EOL into these conversations, and we have a great community of practice that's involved with this it's really cool. They're working to organize and design and solve problems together. This is a new space. Not everybody knows all these answers, and the group is coming together to solve these challenges. And if you're interested at all, just let me know and I can connect you to that group. We also have correctness and reproducibility. This is Allison Baker's work, where sometimes we just don't end up with bit-for-bit answers. How can we be more confident if we change an algorithm that we're not changing scientific conclusions based on that? So that's the ensemble consistency test. We also have large language models, and Iris is our postdoc on that project, and you guys will hear from her later. But it's also advising, on different methods and help kind of shepherd a herding of cats in that area. I'll just call it that. And then officially defining better practices. This is going to be a grassroots effort, so it's not going to be anything top-down. We want to gather information around the organization and really build up these foundational pieces that we share across the organization and the knowledge. Okay, my last slide. Capabilities and infrastructure. So this is where you guys have seen a lot of work as well. So the top one is the coupling of MPAS with MOM6, and Dan presented on that, I believe, yesterday. So I won't go into too many details, but we're providing some support there. We have the interoperable physics and dynamics, and this is the SEMA project. And you notice that there's a lot of interoperability here. We're building a system to answer those complex scientific challenges. We don't have anything that works across all time scales right now that's flexible and easy to use, but when we add this interoperability and this flexibility into our models, we can start asking new questions of our science. And this is building up those capabilities. We have the interoperable chemistry, and I'll add /aerosols to there because we have not forgotten about aerosols. They are on our radar to work on, and we're also working with HAO on Wacom-X and figuring out how to get them into this space, but also how to run ultra-high resolution simulations without the computational burden of full CAM underneath it. How do we enable that? And then the infrastructure the glue code that holds it all together. So this is CCBP. This is looking at I/O. Are we using I/O efficiently across our systems, and where can we improve on this? This is Ren's work on language interoperability. How do we bring in codes that are not Fortran? We should have some way we do that across the organization as a uniform way. How do we do that? And I think that's all that I have. So questions?
Yeah, so on your best practices and standards slide, you had reference to LLMs, and I'm just wondering if you can expand on what that looks like in that context. Is that like guardrails and constraints on the use of LLMs? Is it ethical oversight, responsible use?
Yeah, and Iris will talk about that later today, specifically on that work, but she's going through it, doing an evaluation. You know, I believe she's specifically looking at language translation. So it's looking at it not just, hey, I am using this, I think it's making me more productive. It's actually looking at it, what is it producing based on what kind of prompts? Is it running? Is it performant? If she, you know, she's going through and actually doing a systematic evaluation of it. But I don't want to steal her thunder. Stay tuned.
I do have a question, more organizational. So does this mean that you still have like software engineers embedded in the specific program, say with CSM or MPAS, whatnot, but then there's also like a host of like individuals who support all the projects? Or does it mean that most of the software engineering activities will be happening in this context?
Yeah, great question. So, so there's no plans for moving people out of their home base. And so the software facility has some base funds. So people are, you know, partially or fully funded depending on their situation. And there's actually what I'm really proud of. You notice we're doing a lot of stuff. Our budget is not that big compared to the stuff we have listed here. There's an amazing amount of co-sponsorship coming from labs, especially from the scientists, and it's been really great to see. So we have people that just are really interested in learning these things. You know, I always say, if you're interested in any of these things, please reach out. No experience is needed. If you want to grow in any of these areas, you want to learn, reach out. It's been really great to see all of that, the community aspect of it. So where the organization goes in 10 years, I don't know. I'm not that pay grade. But, you know, we have something, you know, we're working across boundaries. You know, when I was very purposeful with the automated testing, we have representation from almost all corners of the organization helping with that effort, growing and learning from each other. It is entirely co-sponsored. There is not one dime, or wait, no, I take that back. I'm sorry, Sam. Sam is partially funded for CTSM, I'm sorry. Partially funded under to do that work, but it's entirely co-sponsored. So it's just, you know, momentum and excitement in doing these things. And, you know, we're hoping to grow based on that as well. So I know that doesn't answer your question directly, but yeah. Yeah, I mean, it's essential for trust, and we need that knowledge working hand in hand with the scientists. There's certain things that you can be separate and contribute to from this, but I think that's always going to be necessary at some point. Thank you.
All right, so we'll move on to our second presentation that is going to be remote by Daniel Sarmiento. Do I bring it up here? Or he's going to bring it up. Daniel, you were going to bring it up and you're going to talk to us
Yes.
about.
Hope you can hear me.
Yes, we can hear you. So thanks for talking to us about addressing core modeling infrastructure barriers in the UFS.
Yeah, the title is a mouthful. Hi, I'm Daniel Sarmiento from NOAA OMD, the Office of Model Development formerly known as NOAA Environmental Modeling Center, or NOAA EMC. I want to start off with talking about the crossroads of community models and infrastructure. So something that's in common with the UFS and CESM and other community models is that we do get advantages that are essential for model development as a community model. We get accelerated development cycles, we get shared code maintenance across academia and government labs, and since all the code is public, there's easier auditing, replication, and validation of results. But as models are developed, there's added complexities, there's new components coming in. And so this can start to slow down development if proper structures aren't in place. And I think communication and collaboration, not only within your own community, but across other communities and models, will allow us to efficiently grow and maintain our models. And that's kind of why I'm here, is to learn from you all what CESM is doing and hopefully talk to you of what UFS is doing and learn from each other and how to tackle this growing, I don't want to say issue, but this growing need. So the Unified Forecasting System, UFS, weather model is a coupled Earth modeling system that spans a range of application and operational forecast systems. Here I have the cloud of submodules and libraries and dependencies. At the top, we have the UFS weather model. There are a lot of submodules that Ligia talked about that we share between the UFS and CESM. And in addition, all the libraries and dependencies that are needed to run all of these different all of these different submodules and components. So challenges from a UFS perspective, honestly, UFS is a community model, but it is also the backbone of operational products such as GFS, RRFS, and HAFS. And so as an operational product, there are strict requirements for maintaining operational ready code. And so this adds an additional standard that not only code maintainers, but users have to kind of abide by. And that's kind of where it gets tricky, because we have to draw a line between having strict code governance, because this has to be operationally ready, but also not deter people from open collaboration because of all of the rules and, coding standards that they have to abide by. So what we're doing now is to try to balance this operational and community need. So every pull request requires passing a suite of regression tests. And this ensures that multitude of configurations within the weather model meet operational standards. So this includes compiling in debug mode, and then reproducing on restart, reproducing when you're doing MPI, threading, when you change the layout of cores in the atmosphere. If it doesn't bit-to-bit reproduce, then the regression test fails. Unfortunately, over time, this suite of regression tests has grown a lot. So now we're running anywhere from 150 to 300 regression tests across 7 different systems. And again, this is for every PR. And the runtimes can vary anywhere from 1.5 to 3 hours on different systems. As you can probably know, this causes a lot of delays in PRs and burdens both the code managers and the users. Unfortunately, we can't really just get rid of the regression tests because they are a critical part of ensuring that code maintains operational status. So what we're trying to strike is a balance between, again, that operational needs and then making it easier for collaboration from the user side. So we're undertaking an effort to reduce the amount of regression tests by a lot. And we're going to focus on just testing current and future operational configurations for the GFS, the RFS, and the HAFS. So this reduces code management, it reduces the amount of resources needed, and it reduces the burden on the user to abide by all of these regression tests. We also recognize that users are going to want to run regression tests for their systems sometimes. So if a group has a radiation scheme or a microphysics scheme that they want to implement operationally in the future, you might want to have these tests going during development. So we're also reworking the regression test system to make it very user-friendly, or more user-friendly than it currently is, in order to allow users to easily maintain baselines and run operational requirement tests as needed during their development. We're also looking to expand unit tests across repositories and using CI/CD GitHub tools to their full potential. Right now, we have some code coverage here and there, but we're really looking to expand that and just having unit tests acts kind of like a sieve. So the more tests we have downstream, that means we can have less tests upstream, but still keep the code at a rigorous operational readiness level that is needed. Another issue that we're running into is portability and modularity. So the UFS weather model is currently supported across several different systems. Here I have a picture showing all of the different computing locations that we support. These are our quote unquote tier 1 systems. But if a user wants to use UFS on a system that is not actively supported, then the building of those libraries on the systems, other systems, is a common roadblock. So we've had people ask, why can't we, or it's difficult to run the UFS weather model on Stampede, for example. And we use SpackStack. The SpackStack library has all the libraries that are needed, and we know it works with the weather model. But then getting that installed on a non-supported system or a non-tier 1 system is sometimes difficult. And we recognize that. So what we're looking into is containerization and versioning. So containers are currently being developed for CI/CD. So that will allow us to actually run very low resolution global runs on the GitHub CI/CD platform in order to test whether or not the code compiles and you actually can run the model. And then also for general use. So you can take a container from one system and plop it on another. And as long as you have the resources, you can run the model. And while this is not really a perfect solution, it is the first step in improving portability across platforms that are not being actively supported by Epic. And Epic, for those that don't know, it's the Earth Predictions Innovation Center, and they're responsible for kind of like the user interface between the UFS weather model and the community. We're also looking to reduce the reliance on external libraries and eliminating partial redundancies. We're always going to have libraries, but we can try to reduce our dependencies on them and make it easier for users to compile the essential libraries. We're also discussing the benefits of versioned releases for the UFS weather model and its submodules, and establishing kind of a UFS governance and with collaboration from the community on supporting efforts to make the code more portable across different systems. Another thing that's come up is just the ease of use of the UFS weather model. The abilities for users to use the weather model for their experiments has become a bit more difficult as the weather model has grown. I counted last week that the input file has about 300 different variables that you can change values and turn things on and off. There's multiple modes that you can run the UFS in. So global versus regional versus the hurricane. And there's also multiple potential configurations that you can have. So we need tools to help with that. We also need to have tools to help the user look at model stability and have metrics to look at why the model is crashing or why it's running slowly. And although the weather model scripts and the global workflow are robust, users might find it confusing when they first get started. And I'll clarify here, the global workflow is kind of the end-to-end system for operations. So from getting initial conditions, getting observations, running DA, nudging those initial conditions, running the forecast, and then doing post-processing. All of that is encapsulated by the global workflow. So it's robust because it's in operations, but it's also really complicated. And I myself still have trouble sometimes navigating it. So what we're doing to help this is integrating some really basic tools into the weather model. So we can add this directly to the weather model or via SpackStack. One of them is UFS tracing, and this will allow the user to see subroutine calls for the different components of the coupled model. And this enables quick identification of bottlenecks and optimal core allocations. And I'll show an example of that on the next slide. Other lightweight tools that we're working with right now to get added is Scholastica, which is a parallel program optimization, and a memory management tool called Police Me. And so allow users to look at maybe catch memory leaks and stuff like that before they come into the weather model. This is an example of UFS tracing output that is currently in the weather model. So you see here we have the different components, so CMAPs, the atmosphere, the right grid component, MOM, SICE, wave. And then you can see the timing of all the different subroutines that are running within each of the different components. And what this really allows you to do is, if you look at mom here, there's a lot of downtime, the same with WaveWatch. And so maybe you're allocating too many cores to mom and WaveWatch, and you can speed up your run by allocating them to the atmosphere. And so this is a really simple way for users to look at their runs and see if they're optimally allocating cores across the different components. So I think it's a small tools like that that can really help. And one of the big projects that we're looking at now is using LLMs and other AI ML methods. So there have been a lot of talks about using it for weather forecasting and Earth system predictions. But here I want to talk about using the LLM to help the user navigate the code. So a project is underway for LLMs. A RAG has been built, and agentic tools have been built around the UFS global workflow repository, and that's including the UFS weather model. And so the idea is give the LLM guardrails, only trained off the code, only trained off the documentation. It can't go outside of that. But then us at OMD have gone in and built tools to help users, help developers, help code maintainers. And so some of these tools fall under assisted coding. And so you see this here, number 2, some of the different code or some of the different agentic tools, helping with validation and implementation standards. So that's that EE2 compliance over here on the right-hand side. We have tools that diagnose model failures, tools that help you set up stuff, tools that help you find scripts if you're looking for like DA scripts. And so all of these different segmented tools, it's a lot of work to get spun up in the first place, but it really does help down the road, especially to get new users spun up or just current users to help code and debug things. So finally, I'll leave with that communication is key. Many of the changes that we're enacting were directly due to user and developer feedback. We're even in the process of sending out a survey to users to try to get more data to see where we might be lacking, because us as developers kind of live in our own little bubble, and sometimes we really see where the deficiencies are. And more importantly, we're also looking to learn from other institutions and other community modeling groups to see what works and what doesn't. Sometimes we catch ourselves asking, well, CESM, they have these submodules and run these components. What are they doing? What is ECMWF doing? UK Met Office and stuff like that. So it's nice to have the ability to create touch points and collaborative efforts, not only through a multitude of community models, but especially between UFS and CESM, and especially when there's so many shared components and goals. And I have had a lot of fun attending this meeting, this workshop, and learned a lot. My email's here in case you want to get in touch, because I certainly will get in touch with a few of you. Thank you.
All right. Thank you, Daniel. Eric?
Yeah, Daniel, that was a great talk. Really cool stuff you're working on there. It's really nice to see that happening. I had a couple questions. So on your regression tests, it sounds like some of those are done by hand, and it's not all in a CI/CD automated workflow?
So the global workflow does run automated tests.
Okay.
We do run into issues where we can't directly connect with GitHub to the HPCs. So they're doing a bypass through GitLab and then having runners run there. For the weather model, they're currently working on getting that implementation working. So it will be automated soon, but it currently isn't.
Oh, okay, right, cool. Yeah, because that's one thing that just makes it really hard if you have to. Everybody has to log into all these different machines and all that.
Mm-hmm.
Yeah, cool. And the other thing I was wondering about is it sounds like maybe a different GitHub workflow where you have more than one branch might make sense for you, because it seems like maybe you'd have a main branch that's used for the operational stuff and has a higher standard than the development branch, for example. I'm wondering if you've thought about that. And
yeah, so we do have we currently do have branches for the production products. So if you go to our repository, there's production for GFS Z17, 16. But we do try to branch off late in the process, and we don't know if that's correct or not, because if there are fixes that need to go into production, sometimes it gets lost and doesn't make its way back into the development branch or the main branch.
Yeah.
And so that's a constant struggle, and we don't know. That's when we're talking about versioning and maybe creating like concrete cutoff points and not just hashes that people go back and forth with. Yeah.
Yeah, that makes sense. Yeah, cool. Yeah, thank you.
Thanks.
All right. Thank you so much, Daniel. We're going to have to move on. So our next speaker is going to be Becky Schwantes. And she's going to, wait, let me do this. I can't do two things at once. Okay, I think we're supposed to present from the PowerPoint. Okay, and she's going to talk to us about chemistry, UFS Chem and CAT Chem. Yours.
Thank you. Hi, everyone. So I'm Becky Schwantes. I'm a research chemist at CSL, and I'll talk to you about how we're unifying atmospheric composition in the UFS. And this is a large collaborative effort across a number of the NOAA OER laboratories, also Weather Service and EPIC, our cooperative institutes, and also already a collaboration with NCAR as well. So this is just a quick schematic to talk about what we're doing and what we mean by unifying atmospheric composition in the UFS. So originally in the UFS, chemistry was added through various processes like GOCART and CMEC, but it wasn't unified. So now we're unifying it all through this chemistry library or modeling component called CAT Chem. So all chemistry processes will go through this component. And then similarly on the emissions side, we're creating a unified emissions processing system called CC, which will handle all offline and online emissions. And this connects with the UFS for meteorology and then chemical data assimilation for JEDI. And all of this together is representing our UFS Chem system. And then we are going to use model evaluation tool called Melody's Monet, and that's already a collaborative project between NCAR and NOAA, so we're jointly creating that repository. And that allows us to evaluate against a variety of observations like surface, aircraft, and satellite data sets. And then our overall objective is to get a greater understanding of societal challenges related to weather, air quality, and smoke, so atmospheric composition. At NOAA, we're really interested in improving forecasts, but we also want to use this system for stakeholder science needs, so our ability to inform optimal decision-making. And so we need a lot of complexity within the system as well, beyond forecasting needs. So this is just a quick summary of what CAT-Chem is. It stands for the Configurable Atmospheric Chemistry Library and Modeling Component. Again, it's going to store all of our chemistry-related code and be flexible and configurable. It will have full process level configurability. And what we mean by that is that users can choose the right aerosol scheme, the right gas phase scheme, et cetera, for their desired application. Even from the operational perspective, you need this. If you want to do smoke forecasting, you just need some simple smoke tracers. But if you want to do air quality forecasting, you need a kind of medium level aerosol scheme and medium level gas phase scheme. So this is really important for being able to use UFS Chem for all of our applications. And we're still going to link to all the authoritative repositories from external collaborators like we were doing before in the UFS, but only at a process level so that we maintain this full process level configurability. So we'll be pulling in the model independent chemistry module from NSF NCAR. We'll also pull in the CRACOM chemical mechanism, if you're familiar with that, we're collaborating with EPA on, and also the GOCART process G library. And we'll talk more about that later. So this is our code architecture for CAT-Chem. It has kind of all the standard folders in the beginning. Importantly, we're just like many of these repositories, we have a docs folder that connects with our read the docs. We have a drivers folder that this is how CAT-Chem connects to all of our host models. So right now we're connecting CAT-Chem through NUOPSI into the UFS. We'll also build a driver for CCPP, and then theoretically we can connect CAT-Chem to other host models too. So this is all kind of generalized. Most of our code is in the source folder. We have some high-level API stuff, core stuff. We're linking directly to external repositories in that external folder. And then a lot of our processes all coming in with full process level configurability are in that process folder. And on the higher level, we're requiring tests for each process from the beginning. So we make sure our code is well tested. And it's best to do this from the beginning, so that way you make sure that you encourage that rule. And then we also have a tools folder that runs our process generator. And this is a little different, so I want to talk a little bit about the process generator. Whenever you're adding chemistry or any scheme into a model, there's a lot of like boilerplate template, like Fortran code that you have to write, and the scientists, aren't the best at writing this. So this process generator basically just generates all that code for you for a process. It's all based on Python, which is useful for scientists, and just a simple YAML configuration file. And this will generate all that boilerplate code. And this keeps our code really consistent across all of the processes, so it's easier for us to maintain, and also just make sure that things are consistently handled for validation and error handling. And then it also creates templates for documentation and tests, so it encourages whoever's adding that process to make sure that they actually do that part of the tool. And so this is just a summary of what we've gotten in right now. We've pulled in all the processes from the GoCart2G process library, and this is work being done by Wei Li at NOAA ARL. And so we have all the common processes like dry deposition, wet deposition, sea salt, settling, dust, OCBC, sulfate chemistry. And already we have various schemes that you can use and different options that you can use within the system as well. And all of this is fully process level configurable, so you can switch schemes easily, and it should all work well within the tool. And so now we are at a testing stage to make sure that we can kind of replicate the current NOAA effort, which is called GCAFS. You may not have heard of that, but it's the UFS Global Aerosol Planned Operational Product. It was planned actually for the spring, but got delayed. But it's what we need to be better than in order to go operational, so that's why we're comparing against it. And actually, we have really good similarity for sea salt, dust, sulfate, OCBC compared to GCAFS. This is just a movie showing an example of sea salts. Right now, we're just comparing at a process level and making sure that we're duplicating everything well. And the next step is actually to compare with more observations. And then we're actually officially adding CATChem version 2 pretty soon into the official UFS weather model. So that'll be exciting as well. And so at the same time as doing the aerosol work, we've also been working on pulling in gas phase chemistry. And this is a collaboration between NCAR right now. So we're using their Musica library, which stands for the Multi-Scale Interface for Chemistry and Aerosols, if you haven't heard of it. It has MICM in it, so that's a model-independent chemistry module, so that solves gas phase chemistry. It has a 2VX photolysis scheme, and under development is also a generalized aerosol scheme called MIM. And the Musica library is also being added, so it's being added into CATChem to go to the UFS, but also being added into MPAS-A for ChemPass development, and also into CAMSEMA for like the next generation of CSM. So in gold here will be what we share for chemistry, even right now, for these kind of next generation versions of these models. And this is really important for the user community. We're adopting the exact same input files for the mechanisms in our system versus the Musica system, so that makes sure that it makes it easier for users to be able to share chemistry across these models. So this is just a quick summary of getting the Musica library in. We're kind of getting there with it. And this is work being done by Maggie Bruckner at NOAA CSL. So we're hosting all of our CATChem mechanisms on GitHub right now, and we're reformatting a number of the NOAA mechanisms that we need. So that includes the AIM4.1 and RACOMS mechanisms. But eventually we'll pull in like the Mozart flavor of mechanisms that you're all familiar with working within CSM too. And we fully connected it and it builds, and we made sure that all of the formatting is consistent. And now we're actually adding MICM as a process, and we're following the same structure as ChemPass-A and CAMSEMA so that it's consistent across these modeling frameworks. And we're actually testing with just simple SO2 loss, so as simple as it gets for chemistry. And that actually runs in CATChem now, and so we're actually now testing it in the global system with the GoCart2G results I showed before. And I also just wanted to quickly go over our new emissions processing tool too, which is called CC. It's the Community Emissions Computing Engine. I just have one slide of this because this is just getting started. But if you're familiar with the emission system in the UFS before, it was called Nexus. You might be more familiar with HEMCO. That's actually what's used in GeoSchem. It was based off of HEMCO. We're transitioning into this new CC emissions component system, largely because it's written in C++, so we can actually use it with GPUs. And the HEMCO system was struggling with having online connections with the UFS and other host models as well. So we've corrected that within CC to make it easier to actually run these online processes, which is really important for getting your online and offline emissions in one tool. So those are the advantages of moving to CC. So this is just a quick summary of how we're kind of connecting amongst the community between these models for the UFS as well as the NCAR and NASA systems. So in gold here are the components that we're sharing across the NCAR NASA models. So that's the GoCar2G library for NASA and the Musica library for NSF NCAR. And then we're building in components and processes in CAD/CHEM to be able to have full global gas and aerosol chemistry working in a couple of years, because we need to actually have that ready for operations. So we have to build in a lot of components for that too, on both the emission space and the chemistry space. And then I added a little arrow for the gold to connect CAD/CHEM and Musica, because now we're kind of starting to explore how our CAD/CHEM library and our Musica library can interact more together, and can we use components from them in each other's models? How can they kind of benefit each other? So we're thinking about that now. There are different timelines and priorities for both of these models and the modeling components, which makes it hard to completely merge. But with this new infrastructure, it makes it easier that we could share things. So in order to facilitate this, we have a planned hackathon later in the summer. So if anyone wants to be involved in that, let me know. I can get you added. But we have dry deposition in CAD/CHEM, but not yet in Musica. So we're kind of going to explore what that might mean for sharing dry deposition across all of these models. We have CAD/CHEM connected through NUOPSI into the UFS, but not yet through the CCPP. So that could be tight physics, chemistry coupling into the UFS. And then we could explore connecting CAD/CHEM dry deposition into the Musica library to be able to benefit ChemPass development and CAM-SEMA development. So that's to be determined later on. And then I just wanted to highlight a tool that we're working on with NCAR already called Melody's Monet, which is a model evaluation tool for atmospheric composition, but also is useful for meteorology. You can evaluate against surface, aircraft, and satellite observations. There's just some eye candy of what you can do with the tool. And this, we just share a code repository between NCAR and NOAA, so we're actively just developing it together. And just like we have these community models, it makes sense to have community model evaluation tools too, so shared components so that people can learn from learn and quickly make these plots. And we already have the capability to evaluate CSM and UFS, and we're also adding unstructured grids like MPAS into the system too. So this will have all of the models and important modeling capabilities that we need across NOAA and NCAR. So I just wanted to end with all of the links for both CAD/CHEM CC and Melody's Monet. If you want to check out our code or our user guides, these are the code repositories. It's all public and online, so you can check it out. And so we're creating UFS Chem, trying to modularize chemistry and emissions. We're trying to pull in all the processes available in the community because we need to grow fast for developing UFS Chem. And also we recognize that not everyone's going to be able to run the UFS in the community. So our goals is really to grab what's available in the community. They might be using those community tools in other models, but as those community elements grow, so does UFS Chem. So this helps us grow a user community for UFS Chem, but also use all the great science that's being done across the community and make sure that we remain state of the art. And my contact info is here too if you want to email me and talk to me again after the workshop too. Thanks.
Go ahead, Jesse.
Great. Thanks, Rebecca. That was a good talk. One thing that we're trying to figure out is kind of how to connect the physics and the chemistry. So, for example, you showed the aerosol-aware microphysics, and one of the questions we have is kind of who owns like droplet activation or that thing. So, have you guys thought about it at all? Do you have any plans? Should we talk offline? I don't know. Yeah.
Probably for that specific process, we can talk offline, but that is a big part of it, is bringing everyone together and figuring out where does this lie? Does it lie in physics? Does it lie in chemistry? And what makes the most sense? I feel like from the chemistry perspective, we're most interested in making sure that gas phase chemistry and aerosol definitions are all stored in one location, but then the physics information can still be in physics, right? You can just call CAD/CHEM or Musica library to get that information. So as long as you get the information for chemistry and aerosols from chemistry, that's what needs to be stored in CAD/CHEM and Musica, but otherwise things can be stored in physics, yeah. So kind of depends on your process, yeah.
Cool, great, thanks.
All right, any other question? Okay,
Awesome.
Thank you, Becky. All right, we're going to move on to another remote talk that's going to be by John Dennis, who's going to talk to us about the Turbo project. So, John, you're already there. You're ahead of me. We can see your screen. Just needs to go in presentation mode.
Okay. Does it work?
Well, we're seeing kind of the, oh, something is coming. Yes, perfect. Go ahead.
Thank you for this opportunity to talk. I am in Scotland at the moment, so there may be some delay associated with the distance. And so we named the name of the talk to be a little bit different. So code modernization through language interoperability, and this was kind of a case study. So I'm going to give an update on the Turbo project. For those of you who are not familiar, I'll define what that is, and then we'll talk about kind of a more general thoughts on code modernization through language interoperability. And okay, so Turbo, this was a work to GPU enable MOM6, and GFDL is doing some of this work with right now with directives using Fortran, and so we're taking a slightly different approach. I guess I'm getting ahead of myself. So this is a 5-year project. It's a collaboration with a number of entities, and we've just finished, or we're close to finishing the first year. And the motivation here is really the NSF Horizon system, or one of the big motivations. This is a really large National Science Foundation investment. And we need, 20% of the system is CPU based and 80% of the system is GPU based. And we really need to provide software to the community that can utilize the entire system, not just a small piece of it. So the Turbo software approach is to evolve the MOM6 code base such that it can be efficiently utilizable CPU and GPU, create an alternative for the flexible modeling system, and evaluate the viability of a pivot away from Fortran, and we'll say more about this in the talk, to an alternate language approach. And this alternate approach that we're experimenting with is Amrix as a key enabling technology. And so what the Turbo software looks like, it's quite a bit more complicated than your run-of-the-mill MOM6. Which has the MOM source code, the FMS infrastructure library, and then the interface into it. So it will have, what we're working on here is a TIM interface that looks the same as the FMS interface that accesses into TIM, which is a thing called Turbo infrastructure for MOM6. So this is a alternative to FMS, and that's built upon Amrix. And then ProtoMOM-XX is a prototype MOM ocean model that would be written in C++ to see what that would look like. So the current status of the project, and this is just kind of a brief run through of where we're at, because I wanted to get to the language interoperability and agentic AI work. So we have the integration of existing MOM6 build with CMake. We have multiple CIs that are going on, existing MOM6, FMS and TIB interface, and also ProtoMOM. So we're testing this extensively. We have PF Fortran unit tests going on for the interface partial implementation of the FMS alternative. We have the ability to execute MOM6 using the first non-trivial Amrix C++ code. So this is a nice result that we've gotten quite recently. So we can run part of the continuity solver within MOM in the Amrix C++ code. This allows for bottom-up development, and we also have a prototype C++ driver that allows for top-down development, and we have Google tests for that, about 52 of them. So this is really predicated on the notion of a test-driven development process. And we don't see really any other option to for this project to succeed, because we're going to need to rewrite or modify a large code volume. So what about performance? This is that's what a lot of people are excited about, or at least that's what I've been obsessed about for for many decades. So we actually have some performance results. These are pretty hot off the presses in the sense of in the middle of last week, I saw the initial versions and they're like, that's too good to be true. And so we redid them. And so they actually are true because they've been verified using a couple different timing methodologies. So what we're looking at here is the ratio of the performance of the sections of the code that have been converted to C++ compared to the sections of the code that are still in Fortran. And so basically we're right now we have 6 subroutines that have been converted into C++. So the values above the line indicate that the C++ is running faster, and values below indicate that that Fortran is running faster. So we have a problem size sweep. So the kind of the pleasant surprise here is that with the exception of one case, the C++ is consistently running faster on both the CPU and the GPU. The one case where it's not is essentially utilizing one core on a node, which is really not what you want to do. So this was a pleasant surprise and I would say unexpected. The Fortran that we're comparing this to is using do concurrent and OpenMP target offloads, directives for parallelism. For GPU parallelism, this work was done or is being done by GFDL and Access NRI. So how does a single CPU compare versus a single GPU? This is really the bottom line kind of speed up result here. And what we're seeing is about a factor of 6x faster comparing devices. And this is a fair comparison because they kind of have similar, they're not exact transistor counts and energy usage. So this is a great result. This is kind of what we were hoping for. And so we're seeing this on the code that we've converted so far. So I want to go on to agentic code transformations, and people have been mentioning this, on and off in the talks. So this is kind of, I wanted to talk a little bit about or mention about our approaches. It's based upon different language flavors. And so in converting between the different language flavors. So there's the MOM6 style Fortran, that's the original. The MOM6 GPU style Fortran, this was modified by GFDL and Access NRI. And will eventually be present in the broader MOM6 code base, but it's not there yet. There's this thing called AMRIC style Fortran, and this is temporary. It's developed as part of the Turbo project. It changes the data structures to be more C++ / Fortran interoperable friendly, but it kind of trashes performance. And we're okay with that because we think it's temporary. And then we have Fortran style AMRICs. It's developed as part of the Turbo project. Maintains the original structure of the code, but it's just written using AMRICs. So what we do for kind of the translation process is you convert the MOM6 style Fortran into GPU style Fortran. And this was so far has been done by the GFDL and Access NRI. And this is really human effort. That's kind of challenging actually. And it's still an open question about how effective AI can do this. But then you can convert into from this style into an AMRICS style Fortran, and this is kind of a human AI collaboration. And then once you have an AMRICS style Fortran, you can convert it into the Fortran style AMRICS, which is primarily an AI. And so we started this process with a couple of subroutines. This was pair programming like. So chat GPT plus human, talking about how to do this. The first two subroutines took about 3 weeks The next set, based upon what we learned, was about 3 to 4 days work. So we're speeding up. So using agentic AI with Cloud Code, we can now do this transformation in about 40 minutes. So this is a significant speed up, and so that's pretty impressive. Here's some more observations about that. We've currently converted 9 subroutines. 7 are bit for bit correct. The other 2 revealed a bug in our scaffolding code. So we have scaffolding that allows the connection between the C++ and the Fortran. Conversion is quite quick, so it'll take 30 minutes to load the skill that we've written and then to convert one subroutine. And then once it has all this knowledge and context, then it's much quicker. So it's about 10 minutes to convert subsequent subroutines. So far, code conversion does not appear to require more than a Claude Pro account, unless we go into production. So a Claude Pro account is about $20 a month. So this is a pretty good deal. PR review is really now the rate limiting step, not code transformation. So that's we've just moved the bottleneck somewhere else. And of course, this approach is really not possible without robust test-driven development infrastructure. We really don't trust the AI very far. But I mean, if you ask it to do a small task and then you verify that it did it correctly, then that gives you more confidence. And the other thing to note is that this isn't really radical. Somebody provided a citation that came out like 5 days ago about publishing on converting an ocean model written in Fortran into Cogos using agentic AI agents. And there's already a citation on that. So, all right, so Fortran versus C++. So the previous work was the work of everybody in the group, and this is kind of more of an opinion. So this is I'm not like, my opinion. Fortran versus C, this is C++. This is a little bit of a religious thing. I've heard stuff that Fortran is clearly the best language for scientific programming. And I don't believe that. I think Fortran is the most familiar language for scientific programming at NCAR. I mean, you can think about it if you go to a foreign country and you go there and you say, oh my gosh, I can't understand the language and the culture is all different. But does that really make it a bad country, or does that just make it that you didn't grow up there and you're not familiar with it? So I think that's something to keep in mind here when you look at this Fortran versus C++. So what's our experience? I mean, honestly, we've had a lot of experience with Fortran, some of it kind of painful. And so this project is useful in the sense that we're collecting information on C++ during this project. So compiler bugs. First Fortran compiler bug we hit was 1.5 weeks into the project, and there's probably been about 3 or 4, maybe 5 since. C++, none yet. Performance, so that's advantage C++ performance. It's actually faster. This was not expected, and we don't entirely know why at the moment. Converted code volume. Actually, the Fortran is more larger from a lines of code, which means maintainability is higher. Readability, I think it's just as readable. There's some links when this talk is posted. There's some links, and you can go and look at it yourself if you're interested in looking at that. All right, so some conclusions. We're leveraging the GFDL Access NRI work, partial implementation of the MOM6 continuity solver written in Emmerich's matches bit for bit. So that's kind of cool on both Fortran and CPU, or on both CPU and GPU. It's currently faster on the GPU, and it's currently faster on the CPU as well. And we see a 6.3x reduction in execution time when we compare a 100 GPU versus one derecho CPU node. We have a well-defined continuous integration and test-driven development pipeline, absolutely critical for this kind of work. It took us a long time to set it up, but I'm confident that we'll reap the benefits of it moving forward. Agentic AI for language conversions. Again, it's we trust it to do stuff only so far. Multiple Americ C++ implementations to be able to compare them, look at them side by side, and so far very positive experiences with the C++ compiler quality. That could change next month, but right now it's looking good. All right, questions?
Thank you, John. We are at time, but let's entertain one quick question. If there is one. Go ahead, Jesse.
Sorry, I'm being greedy. No, John, yeah, good talk. I was curious about your kind of the agentic workflow stuff, because we're in a similar boat where the PR review is the bottleneck. And so I was just kind of curious of your thoughts. Are you determined to keep that kind of human in the loop at that point, even if it slows the workflow down? Or have you thought, yeah, basically, what are your thoughts on that?
I don't know the solution for that. I bug the team members. I have a bot that bugs them if they haven't responded in a week. Sometimes they're good and sometimes they're not. I mean, everybody's really busy with the stuff. I don't trust stuff going in that's not human reviewed. So I guess the answer is I don't have a solution for that.
Cool. Well, neither do I. So yeah, great. Thanks.
Yeah.
Okay, thank you, John. So our next talk is going to be by Vanish Venumudala. Did I say your name correctly? Close enough, on Crocodash. So, all right.
What's up? Thank you guys for having me. In this talk, I'm going to be talking about Crocodash, which is a Python package to set up regional ocean models. And we're approaching version 1, so my boss thought it would be a good time for me to give a talk. So let's get right into it. Crocodash is part of the Crocodile project, which sits at NCAR, and the way to think about it is it's all thing regional ocean modeling within the CSM. And there's a lot of different parts to this, right? We run our own domains, we do stuff with data assimilation, we have our fast access cloud optimized database, Croco Lake, but here I'm going to talk about Crocodash, which is in some ways the hub package for a lot of what we do in Crocodile, where we combine a lot of the things we're doing. And it's built in Python, and it helps users build regional ocean models in kind of the easiest way possible. So one of the focuses of Crocodile is to make regional modeling as accessible as possible for like students and maybe early career scientists as well. At least that's the goal. And so we're approaching version 1 on this. And we've had a lot of really cool development on it, including some beta tests, and we actually had a workshop last year, and we have another one this year, where we were able to show Crocodash off and use it. And it's been really cool, and I thought we'd take this opportunity to discuss Crocodash. So what I'm going to be talking about is I'm going to go through a really quick demo that's going to be a little bit stressful because it's a video. I'm going to talk about a few cool features, and then I'm going to do some discussion topics. And I don't know if discussion is the right word, but I thought maybe there would be some interest in what this is. And it's not quite rage baiting, but there's a little bit of discussion. So a little bit of background before we get into the demo. The way we thought about Crocodash is that there are a lot of really cool tools out there already, like for regional modeling, both in MOM6 and CSM. So we think of Crocodash as an orchestration package. It brings in a lot of tools underneath the surface. And this is kind of the way to think about it. Let me see if I can use, oh, perfect. So we do grid generation with a package called MOM6 Forge, which is like the first step of generating a regional model. And then we work with interacting with the CSM through a package called Visualcation, which was made by Alper, as many of you know. The last thing that we do as part of Crocodash is that we generate our data, things like initial conditions and boundary conditions, through a package called Regional MOM6, which was built by Ashley Barnes from Australia, which has a lot of really cool and fancy things. So that is how we think about Crocodash. We do very little coding inside of the actual Crocodash package, and we do a lot of major development in the sub-modules, which is pretty fun and works really well. So with that, I'm going to get right into a demo, which looks like is not showing up. Is there a Google? So this was a Google Slides. Can I go to that instead? Oh, never mind. Yeah, so it's not showing up. Is there a way I can go to the slides? Nice. Okay, so back to the scheduled programming. Let me see if I can go back here. I'm just going to go through a quick demo of Crocodash. It takes about 5 minutes, and I'll just kind of narrate through it. So the first step in a regional modeling process is we got to say, what are we actually modeling? So you have this tool in Crocodash called the Grid Creator, which lets you kind of mess around and pick a domain. I picked the Gulf of California because it's pretty cool. And it's just a nice way to represent the tools we're using. There's a bunch of ways to create grids, but this is like a drag edit tool that's really fun to use. I'm like, let's pick a resolution that's a little bit smaller, and I'm going to name it Gulf of California 2. So once I create a grid, which is just, remember, like a discretization of like your spatial domain, we then have to say, what does our ocean actually look like? So I do that in an object-oriented format with a topography object called topo, where we pass in a grid. And then what we do is we take a raw data product like Gebco, which is just a topography tool, and we put it on our grid. And as you can see here, there's a lot of stuff printed out. But what's happening is that in Crocodash, we use ESMF and XESMF beneath the surface to do all of our regridding. And it's kind of like the heavy lifting of the project. This is where we spend a lot of time like working on and trying to make it a bit faster and stuff like that. But yeah, so this is going to run for about 10 seconds. And one of the things I'm trying to show with this demo is I'm not speeding anything up. This is pretty much all you need to do to set up a model. So it looks like it's finished. So now I can look at it inside of another tool that we have called the Topo Editor, so I can adjust anything I think is weird about the ocean. Looks like there's a random land cell. Like, I don't like that, so why don't we fill that with a depth of 265 meters? And so we do that, and it's just, and I don't know why I did that, but it works. And it's just a way of editing topo, and it's kind of an advertisement for what you can do with Crocodash. The next thing that you do in the Crocodash workflow is create a vertical grid, which is just how many layers you have of the ocean, and you can mess around with it however you like. So that is grid generation. The next step in the process is then you got to interact with the community Earth system model. And this is going to take about a minute, so I can kind of like mess around, like tell you about it. When I run this command, what it's doing is it's calling the CSM command, create new case and case setup, and we pass in things like our CSM root, and then our grids, as well as our comp set. And for Crocodash, we decided to go with aliases that are pretty standard. So CR_JRA means we're using a data atmosphere from JRA, ocean only, and it's in regional format. And the R doesn't do much, but it's there in case we need to do stuff with it. And so this takes about a minute, but what it's doing is that when we run this is we interact with SEAM. So we're calling all of them directly through Python, and some sub-process stuff. And then we write in all of the things that make our case regional. And this can take about a minute based on what kind of computer you have and what kind of file system you're working on. So it should be going, hopefully. Okay. That's a lot. Yeah. Okay, so it's working now. And basically what it does is it sets up your case how you'd expect, and then you can look at your case, and I can show you, as many of you are familiar with the CSM, this should look very familiar. So I'm gonna open a terminal here and go to my case directory. Okay, cool. And if I look at this is what a CSM case looks like. And I can actually look at my user NL mom, which is where we put all of the regional parameters. And if you notice here, there's like an input directory, there's all of our grid files, how many points we have, things like that. Once I do that, there's only one step left in the process. Let's get our data. Let's get our boundary conditions, our initial condition. So I can configure my forcings, which is where we just write all the parameters we need, and I can request anything I want, like tides or chlorophyll, for example, and I can put in my time dependence. So once that's done, it writes a bunch of parameters, and we can look at that in our user.nl-mom file. And there's all these tools inside of Visualcation to make this easier. And I'm showing some stuff here, but you can see that we have initial condition and boundary conditions all written in our files. Once that's done, the last thing that I do as part of the process is do the heavy lifting, getting the data, regridding it, and formatting it in the style that MOM6 and CSM want. And this takes about 15 minutes. So the rest of my presentation will be staring at this video. But no, so like one of the things we think about when we make things easy for users is just heavy computation is really complicated. And like if you're running things, you might not know when to allocate the right amount of resources for things. So that specific step does a lot of calculating beneath the surface. But once it's done, we just build and submit our case using the standard practice, and we get results out of it. And this is actually the results I got out of that example case. And so that's it. That is the basic demo of Crocodish. And I would say it probably took me half an hour to run that from start to finish. And so if you weren't paying attention to the demo, which is completely fine, there's only one thing you need to know about Crocodish, is that it is at its core, its essence, a quick and efficient way to set up a regional model with three steps. Grid generation, CSM setup, and forcing file generation, which is things like your boundary conditions, your initial conditions. And within that framework, we can do a lot of freaky and funky things, which gets into my next part of the talk, which is just like cool features. So the opportunity that we get with Crocodish, is that I wouldn't say we're at the cutting edge, but with Crocodish, we're writing this package from the ground up, which lets us do a lot of things that are kind of newer and like experiment a bit with everything we have. So I thought I'd just highlight some of the things we're doing, and none of it's like revolutionary, but I thought I'd just point it out as things that are cool that we can do in this framework, and maybe some of you will want to use it. So starting with something really old, we have design patterns. And so inside of Crocodish, especially with my boss Alper, we think a lot about where we can implement design patterns inside of Crocodish. And so one of the things we do is we do registry patterns. And we do this in a couple different ways. So when we think about writing a workflow, we have our basic ocean modeling setup. But you might want to add different things to that, like tides and chlorophyll and stuff like that. And so having those as a divorced, like object-oriented kind of style format gives us a lot of flexibility, which I think is pretty cool. Another way we use registry patterns is with raw data, and this is just an observation I've had over my time in this project, is that raw data is actually kind of the hardest part about setting up Crocodish, or just regional modeling, because you need like a data atmosphere, you need your ocean stuff, you need any kind of tide files. Like there's stuff in Crocodish where like you can only get by emailing an organization, which is kind of crazy. So we think a lot about how we can make raw data access better and support it through Crocodish. That's something we've done here, and making the registry is nice because then if someone wants MESA clip results or CSM lens, it's really quick to add it into the process, which is kind of fun. Another fun thing that we did with design patterns was implementing something called a command pattern, which is where you just add a layer between like your button clicking and what you're actually doing. So for something like the topo editor where you're editing depth, which I saw in the demo, we have all these different commands to edit the depth, edit your mask, and yada, yada, yada. And it lets you implement a couple of interesting features. For example, in topo, we hold two different data sets. We hold a mask and a depth, and those come together in a way that loses data when you actually output it for your topography, and it's a little bit complicated when you do it on the back end. So having commands like this lets us hide the complexity a bit and do some fun things in like the topo editor, for example. We also do some git logging with this, which is interesting, and it lets us explain how you go from a raw data file all the way into your grid topo, which is a lot of fun. It doesn't work necessarily the best yet, but it's possible because we think about design patterns. Okay, so that's that. Another cool feature that we do, and I thought this might be interesting, is we run CSM containers in our GitHub CI. So things like, if we have Crocodish, we want to make sure we're doing the right stuff, and we can actually do that by building a Docker container and running CSM to say like, oh, is our ESMF mesh in NetCF 3 or 4, is that actually working in like the CSM? So I thought it was interesting, and it's a nice like thing to like feel confident about the work we're doing and speed up development. A couple of other basic things, we do docs, we do code coverage. We don't use read the docs because we're like ballers, but not really, but it's just nice to have in-house so we can mess around with it a bit. And then a final feature I won't talk too much about is just widgeting. So as you saw in the demo, we do things like we can create grids through the UI, which is makes it so much more accessible. And this specific one, I'll just highlight this, is you can actually do projected grids, which I think is a little bit complicated when you're first starting. And you can mess around with like having an Arctic grid or an Antarctic grid, which I did not understand when I first started. And of course, we have our topo editor, which does things we've talked about in previous presentations. And so that's kind of the cool features part of this talk. And this last thing, I just wanted to put some reflections I had as someone who has some experience in this field. Obviously, I have no experience in any other fields, but I thought it'd be interesting to point out if anyone else might have some opinions on any of this stuff. And the first one is just DevOps. So on the bullet points here, I've just put some things that we do in Crocodish. And that's just like tip of the iceberg, like coordinating CI across multiple repos, publishing packages, building containers, developing docs, making sure their data access is actually accessible. And all of that is like all about building CI and like making sure everything's working right. And I don't think we realized in the beginning how much time it would take to make sure that we're going from just the startup simple code of the workflow into something that's like properly maintainable. And I think it's just worth thinking about budgeting DevOps time or having DevOps engineers on your project. So I just thought I'd bring that up. Another one, and I won't spend any time on this because, but there's a love and hate relationship with submodules. I went to Australia recently with regional moms to work on regional mom 6, and there was a guy there who really didn't like submodules. And if I talk to my peers in other fields, they don't necessarily tend to like submodules. But we know, as cool scientists, that submodules are the right answer as software engineers, right? Because you can develop, I've talked to Alper about this, you can develop things across multiple organizations in a way to make an insane model. Like, it's the right answer. But it comes with its own problems, and building submodules with a smaller package like Crocodish can sometimes either slow down development in some ways. So I think it's worth thinking about when you build a package like this. A final thing that I thought would be interesting was with our Crocodish workflows, we do something called progressive disclosure, which I'll just say with an example, really quick example is when we think about bathymetry, we move our raw data onto our model grid. And that is just a simple function like set from data set, which is this left side. But it actually is pretty complicated. We do things like analyzing resolution beneath the surface, and we have to expose all of this to the public so that when you get freaking funky with your model, you're able to do that. So we think a lot about how do we move from the left side to the right side, and it's still an open question how we get people trained up on all this stuff. And I'll leave it there with what I was trying to talk about and just say, even though we're close to version 1, we actually do use Crocodish in the workshop. We're able to get a lot of models up and running, and we do a lot with documentation as well, but I didn't get a chance to talk about that. So if you're interested in using Crocodish, please do. We need all the help we can get. So I'll leave some conclusions on this on the screen.
It was really interesting. It was really interesting that you mentioned this thing about the submodules. I mean, your whole Crocodish is really cool, and you're a great speaker with your glasses and everything. But I really like that you mentioned this love and hate relationship with the submodules, which tied to the previous talk by Dan Sarmiento and the pains that we're having in the UFS. But you are pro the submodule. You're in favor of that.
Yeah, at least for Crocodish.
Okay, well, thank you so much. I think, Mike, we're going to wrap up. Thanks, everybody. Do we have any announcements before we go? Okay, no? So, yeah, go enjoy the break and come back at 3. Thank you.
Hey, Prani, if you're online, do you want to start sharing your screen? We're still trickling in from the end of break, so we're not quite ready to start. But-
Sounds good.
So I'll do like a real introduction thing in a minute or two.
Okay, and you can see everything, right?
Okay, so welcome back. Sorry, Jesse. Yeah, so save it till after the session. Wait, we have 4 more talks after the break. The first 2 are going to be online. And so our first speaker is Prani Naluri from Columbia, from the Lamont Doherty Earth Observation. So go ahead, take it away.
Okay. Hi, everyone. My name is Prani. I'm a PhD student at Lamont Doherty Earth Observatory. The title of my presentation is Parameterizing the Impact of Subgrid Scale Turbulent Air Sea Heat Fluxes and Climate Models. So without further ado, as I'm sure pretty much all of the audience knows, there are 2 main camps that heat fluxes between the atmosphere and the ocean fall into: radiative and turbulent fluxes. And these turbulent fluxes can be decomposed into the sensible and the latent heat flux. And the way that these 2 fluxes are typically estimated in climate models is with the bulk formula. And the bulk formula has, its own inaccuracies, and there are many scientists working on bringing bulk formula estimates closer to observations. But the focus of this study is actually trying to bridge the gap between bulk formula estimates in high resolution and low resolution models. So we find that these estimates are actually quite different. And presumably this is because low resolution models are not able to account for a lot of the smaller scales that are resolved in high resolution models. So there's actually a paper that came out of my research group that explored this a little bit, and this is by Busecki et al. So what's done in this paper is we start with high resolution CM 2.6 data, and then I'm going to go across the top row of this flowchart. We compute the air sea fluxes, and then we coarsen the data onto a low resolution grid. And from that, we get this purple Q bar on the right-hand side. On the bottom row, what we do is we first filter our data, which basically means we remove the signal from smaller scales. We coarsen it onto a low resolution grid and compute the air sea fluxes there. And what we get from that is this blue QC bar. And so Q bar can be thought of as a flux estimate in a model that resolves both large and small scales, and QC bar is a flux estimate in a model that's only resolving larger scales. And when you subtract these, you get this Q star term, which is the subgrid forcing, or the subgrid contribution to the flux. So this method can be used for any air sea flux. This paper particularly summed the latent and turbulent heat fluxes together, and that's what they call Q. But this can be decomposed to find the subgrid contributions to the latent and the sensible heat fluxes individually. So this paper was actually very interesting and had a couple key findings. Some of them were that this subgrid contribution could be as large as 10% as a large-scale flux in some regions. The large-scale flux plotted on the top left, and the small scale, so the subgrid contribution on the top right. We see also that the large-scale flux or the small-scale contribution enhances a large-scale flux across about 71% of the air sea interface, and this unresolved subgrid heterogeneity can cause a systematic ocean cooling of about 4 watts per meter squared on average, but up to 100 watts per meter squared regionally, especially in western boundary currents. So hopefully this is sort of enough information to convince you that maybe this is something worth attempting to parameterize. And that's what I've sort of spent my PhD doing. So I'm sure some of you have seen this figure before. It's from Azana et al. Preprint that came out recently. And one of the things this paper talks about a lot is the trade-off between error and complexity when it comes to different parameterization methods that are being used nowadays. So I guess, basically the most complex parameterization methods, to my knowledge, that have been successfully put into GCMs are convolutional neural networks. And then as you go left on this curve, you'll see that, physics-aware ANNs are probably just as accurate, but much less complex. And then equation discovery is less complex and less accurate, and it continues down. So because the process we're trying to parameterize has never been parameterized before, I kind of used this figure as a blueprint for my research. So I started with a convolutional neural network, thinking that, well, this is the model that's the most complex. And so therefore, if this relationship between some near surface variables and this Q star term can be learned, then this is the model that'll do it. So that's where I started. And it turns out the CNN did do well. So then I moved left and I tried working with the ANN. It also did okay. And I kept moving left on the curve. So I'm going to talk about my journey down the curve. But basically, I started from most complex and I followed this red arrow to try to find the point at which I can minimize error and complexity. So I came up with 4 parameterization methods. There's a CNN-based method, an ANN-based method. Then I have this non-dimensionalized ANN method, which is like, there is an ANN embedded into this non-dimensional functional form. And then I have some linear regression baseline that I've created just because there isn't a baseline or a parameterization that's been used for this before. So now I'm going to sort of describe the setups for each of my parameterization methods. So this convolutional neural network-based flux correction, it takes in the same 6 inputs that go into any package that predicts the bulk formula. And what it does is it actually takes 12 pre-selected regions across the globe and looks at them in training. And then in testing, it does inference across the entirety of the globe. So I have one CNN that does this for the subgrid contribution to the sensible heat flux and one that does this for the latent heat flux. And this model did pretty well, but as you can imagine, it was pretty expensive because we're training and testing on regional and global swaths. So since this performed well, the first question I sort of asked in my parameterization development is, okay, how much non-locality do we really need? Do we really need whole regions of the whole globes, or can we go smaller than that? Because smaller would be cheaper in this case. So that kind of inspired me to develop this artificial neural network-based flux correction method. So I have the exact same inputs for the most part as for the CNN, but what I actually discovered is, and I've tested this for different amounts of non-locality, is if I take a particular grid point and a border of one grid point around it, so like a 3x3 stencil, for each of my input values, and then make my prediction at the center point of the stencil, my results are pretty much just as good as I have for my CNN. So this was like a massive win because I was able to make things much cheaper, but did not really give up on accuracy. So then I thought, okay, well, can we push further along this error versus complexity curve? And I tried to create a non-dimensionalized flux correction method. So this might seem a bit complicated, but it's kind of inspired by some non-dimensional ANN flux correction methods or subgrid parameterization methods I've seen in M-squared lines, which is a group that I'm a part of that works a lot on data-driven parameterizations. So what I have going into the model is, rather than raw variables, I have the gradients of the variables scaled in such a way that they'll always be between -1 and 1. And then I have a certain coefficient that I have divided the output by in such that what's going into the ANN and coming out of it is roughly non-dimensional. And just as for the previous raw ANN version, I do have 3x3 stencils going in, and then my prediction is done at the center point. So I'm going to show you a bit more about this. So this method, I've written out the functional forms for each of my different flux predictions. So the predictions for the subgrid, latent and subgrid, sensible heat flux contributions. And these do look a bit complicated. I'm going to just talk a little bit about my motivation, though. So in M-squared lines, there have been several parameterizations, such as one by Dhruv Balwada, where he was working with mesoscale thickness fluxes, and there's also several done by Pavel Perezhogin. But what they've basically done is, by non-dimensionalizing their functional form, or what was going in and out of their neural network, and they were able to actually create a parameterization that was able to generalize better to unseen regimes, so regions not seen in training data. Unfortunately, this did not work as well for us, but it was a good exercise just to kind of understand the limitations when it comes to different sorts of parameterization methods. So A couple reasons why I think this didn't work as well for us is because the fluxes or the expressions for them that this worked for in the past were much simpler than the expressions we are trying to parameterize for. And also, I want to mention that, this is just one method of non-dimensionalizing. There are a variety of non-dimensionalizing methods out there. And so my non-dimensionalization isn't unique. And sure, we could have tried to continue to push down the curve and find a non-dimensionalization that was ultimately performing just as well as our ANN method, but we had very high R-squared values, which I will show you soon. So we decided to not push forward because this method was actually, the non-dimensional method ended up being more complex to implement online anyway. All right, and our very last method is this linear flux correction method where we basically scale the resolved scale flux, like the coarse latent and sensible heat fluxes by some ratio to get the subgrid contributions. So on this slide, I'm basically showing you a snapshot from a random point in my time point in my test data. Note that I've masked out the maximum sea ice extent and also a small border around my coastlines. I've maxed out the max sea ice extent just because it's known that the bulk formula can be a little bit less accurate when sea ice is present. The physics become more complicated. And I've masked out some area around coastlines because the point of this parameterization is to develop something that will work for the open ocean, not necessarily coastlines where the physics are a little bit different. So on the left, you'll see a target image of this Q star term that I've mentioned. And so this is what I've diagnosed from the data. And on the right, you will see the differences between the predictions of each method and the actual target. So on the top left, you see right here, I don't know if you can see my cursor, there's the CNN method, which we see is quite accurate. It's mostly, the difference is mostly zeros across the whole globe. On the top right, we have the ANN method, which is roughly as accurate, but not quite at the same level. It's just a little bit off in terms of R-squared values. On the bottom left, we have our non-dimensionalized method, which has a more moderate R-squared value of 0.6 rather than 0.9 and above, like the ANN and CNN methods. And then the linear regression is pretty terrible. And then I also want to show you this particular graph, which I think is very illuminating. Here, I've actually plotted results for the subgrid sensible heat flux contribution, but they look quite similar for the subgrid latent heat flux contribution. What I've done is that every single grid cell in my test data, I took the targets and the predictions through time and compared them and computed an R-squared value from that. So what you're seeing in each of these plots is that particular model's predictive ability at each particular grid cell. So I've plotted the R-squared values, and yellow corresponds to 1. As you see for the CNN method, the entire map is basically yellow, so it does incredibly well. The ANN method does almost as well. If you go to the top right, the non-dimensionalized method has more moderate R-squared values, again around 0.6, and the linear regression method has R-squared values around 0, which is not great. So this is kind of it for offline results, and I notice I'm running close on time, so I'm going to quickly go into my online results. Okay. So we did train and test on CESM data, on CM2.6 data, which you can kind of see here with our with the line plots. But we actually wanted to see if without retraining, we could test well and perform well on CESM data. So if you look at the polygons at the coarse resolution of 1 degree here, we just kind of have done it for 1 resolution so far, you actually can see that the results in terms of R-squared values for the CESM tests were actually roughly on par with the results for our CM2.6 test. So this is a very good sign and means that perhaps my parameterization can be generalizable across models. It might work well in CM2.6, but it might also work quite well in CESM. And then lastly, this is just a summary slide. I think at the end of the day, the parameterization I've decided to put online is this ANN method. If you look at my green and red R-squared line plots, you'll see that it's almost just as accurate as the CNN method. But then if you look at the parameter count in purple, the number of free parameters is about 2 orders of magnitude smaller than that of the CNN. So I think clearly, given if you think back to that error versus complexity curve, the ANNFC is where we want to be. All right. And with that, I will open the floor to questions.
Great, thank you. Are there questions in the room?
Yeah, nice talk. Trying to get my head around it. So could these in terms of identifying errors, could it identify errors in the way that the actual parameterized fluxes are calculated, like something like the friction velocity or some aspects of the stability that is being done wrong in the model as it exists, just so you can get an understanding of what physically about the parameterization is incorrect?
Yeah, so I think that's a slightly different problem. In order to, because so like basically what the model is doing is if there's a structural error in the high resolution model, my parameterization is going to learn that structural error, unfortunately. So it's basically pushing the low resolution model such that it's as accurate as a high resolution.
Oh, okay.
Not correcting the baseline bulk formula as is. But there is other work doing that. And if you shoot me an email, I can send you some papers.
Okay, thanks.
Yeah.
Okay, thanks again. Our next speaker is Iris Link from NCAR, who's also remote.
Just a minute. Sure.
So can you share your screen? Oh, here it comes.
Yeah, is there?
Yeah, perfect. Thanks.
Yes, perfect. Okay, I'm sorry. A lot of screen in my front here. Good afternoon, everyone. My name is Iris Link. I'm a postdoctoral fellow in CISL. I'm going to introduce you to LEFT, LLM Assisted for Translation. 2 minutes. Okay. Introduction and the motivation. Atmospheric models such as CSM, WRF, and CAN still rely heavily on legacy Fortran physical routines. So these codes are scientifically trusted, but many were designed for CPU execution, which makes GPU modernization difficult. So manual GPU porting requires deep Fortran sciences and CUDA or OpenACC expertise, so it's costly, hard to scale. This motivates my main question: can LLM accelerate GPU portion of Fortran atmospheric physics? Yes, in this work, I translate Fortran to JAX because JAX supports JIT, VMAP, and XLA fusion. But the key point is that correctness alone is not enough. We also evaluate GPU performance using profiling signals such as kernel launches, fusion efficiency, and scaling behavior. So before introduce LEFT, I would like to introduce JAX for you. JAX let us write code in Python style, okay? But when we apply JAX JIT here, the compilation is traced into a static graph and passed to XLA compiler here. The important point is that the first call pays the compilation, but later calls runs a compiled GPU code. So here, this slide addresses one challenge with JAX performance. The first execution could include the compilation, but in my experiments, this compile step took around 1.2 to 1.8 seconds. So, but this is mostly a one-time cost. We can reduce its impact in 3 ways: ahead of time, persistent disk cache, or serialized exports. This is depending on how we will deploy your code. So you can choose one of this. Now here I introduce LEFT, the workflow I use for LLM assisted Fortran translation. The main idea is to separate deterministic zone from the risk LLM steps. First, let's parse the Fortran code, analyze the dependency, and generate the bridge for memory layout here. These parts are deterministic and they reduce errors before LLM sees the prompt. In the stochastic zone, the fourth part here, LLM generates the DEX translation, and the final validation phase checks syntax, runtime behavior, and numerical agreement with the original Fortran. For this study, I evaluate the Kessler physics on the Rachel 800 GPU using multiple LLM, Gemini, GPT, Claude, and Queen. And these are the version of 8 LLM I used, Queen 2.5, GPT-4, Gemini 3.1, Claude Sonnet 4.6. Let's look into each phase of left. In this first phase, we have a 3C parsing that based on Fortran code. The 3C parser generate extract parameters, procedures, and modules, and put in JSON file. And then after this, the dependence uses this information to build a structured metadata file. The goal is to make the later translation step more controlled because LLM receives reliable structural information instead of having to infer these details from raw code. In the bridge generation, Fortran stores array column agent, JAX store, then raw majors. So instead of trust LLM handles the layout conversion, we generate a deterministic bridge straight from the parsed metadata. The bridges also handle the CPU to GPU transfers, giving every model the exact same correct foundation. So in phase 4 is where LLM actually enters in the pipeline. So we divide the translation. First, instead of sending one very large prompt with all policies and code together, we reject this idea and use a multipass interactive refinement strategy. So we divide the translation into smaller specialized phases. One pass establishes the niche of JAX structure here, pass 1. After generate this draft phase, we feed for the code for the next phase that LLM will check the JIT safe phase. After that, we focus on vectorizations and then finalization with check and type checking and self-annotation here. So the result is break the task into sequential specialized paths, drops the token count, keeping the LLM entirely with the sweet spot of its attention window. And another thing, you can see that each path has around 150 to 350 lines because in the reliable LLM code translation, we have practical limits according to literature here. Prior work identified a phenomenon said lost in the middle. Problems show that models tend to use information more reliable when it appears near the beginning of the end of the prompt, while information in the middle can be overloaded like this. So for code translation, this is important because critical information may be buried in the middle of a long prompt. Here in phase 5, validation. We begin with linting, that a cheap first gate before we spend compute on runtime tests. The linter checks syntax, idiomatic JAX patterns, styles, and semantic correctness, and the basic security practice. So, lint catches surface problems, not execution semantics. Next, After lint, still in phase 5, we have a validation, a runtime validation we call smoke test. So before profiling performance, each translated JAX version must pass basic smoke test. We have to check that it's correct importing modules, the JIT compiler is working, the function is executed properly. So according to this, in this phase, we checked the Cloud GPT Gemini passed in all this validation, and the Queen failed in the JIT compilation and the function execution because we found out that Queen understood Jack's vocabulary but failed the grammar. So Queen mixed up Python level commands into traced XLA boundaries and broke the compilation here. Also, the numeric parity here, we measure by mean absolute error, and the numeric equivalent to Fortran double precision float point tolerance across all variables here. The slide summarizes the execution choice made by each model. So most important difference is how they expose parallelism to XLA. For example, in column loop, Cloud GPT and Gemini using VMAP, while Queen using for loop. What does it mean? It means that VMAX here allow the compiler to see all columns at once, while for loop forces sequential execution and prevents intercolumn parallelism. And the level loop here, Gemini gave XLA the full array using arrange and clip, and Cloud GPT using a subset of the loop. What does it mean? It means that this is like for Cloud GPT, we have irregular memory access, which broke the vectorization, while in Gemini, we have a fully XLA fully fuses. So profiling the code, this summarizes the GPU profiling results for any call equal 1000 and NZ equal to 72. The important point is that all successful translations were numerically correct, but they did not have the same execution behavior on the GPU. You can see that Gemini is the fastest with the lowest end-to-end time in GPU execution time. You can see 0.8 milliseconds, 0.4 milliseconds. While GPT and Claude here, we have 1.2 for end-to-end and 0.8. This is because the loop strategy I already showed before. Queen executed in sequential, so the performance is very bad. Now, next we evaluate execution scaling from 15 to 10,000 columns here, 200 times increase in data size. Gemini scales efficiently here. Increasing runtime only about 3.2 times, while Cloud GPT increasing 5.7 times, and because Queen for bad choice, the scale factor is 197 times. The scalability. This slide compares serial Fortran on CPU against the translated JAX version on GPU. Here on the left, the plot shows that Gemini, GPT, and Claude all stay far below the Fortran. Here in the red, we have Fortran, and here we have Gemini, GPT, and Claude. And on the, while Queen here scales poorly and eventually becomes slower than Fortran. On the right here, the table shows the exact speed up at 10,000 column. Gemini is the best, is about 162 times faster compared to Fortran, serial Fortran. In kernel-only execution, but when we add the overhead caused by the bridge, that is transfer data to GPU and transpose the data, this performance here drops to 330 times. Here. So the key finds are, to conclude, we found 3 main lessons. First, correct is only the baseline. All 4 modules produce numerically correct code and showed no memory leaks. Second, hardware-aware code structures is what determines performance. And third, context limits matter. We found a practical sweet spot. Keep procedures under about 300 lines. So for longer code, split procedures and using multipass refinement leads to much more reliable translation. So this is a work in progress. So we are working in more experiments right now. Thank you.
If there's a quick question, I need to shuffle slides, otherwise we can move on.
Oh, this was really awesome to see. Thank you for presenting. I'm wondering about, if I were to do this, I would probably choose one AI, and I might accidentally choose Quen, which really gave lousy results. So I wonder, I mean, after it's done, can you then work on optimizing the solution that the AI come up with? Or have you thought about that, like after it's done the rewriting, what you do then?
Yes, because I use prompts. I saw, for my surprise, Gemini was the best, maybe because Gemini was developed by Google and JAX was developed by Google. Maybe Gemini is very well trained in this language, but it's a supposition. I cannot tell you that is true because I need more experiments, okay? But I used Claude to fix what Quen did wrong using my prompts. Basically, and then Quen now is doing the same thing as the others. Yeah.
Oh, okay, right. So you could use the AI to improve what it was doing. Okay.
Yes, because I have an agent that improved the code based on the on my prompts. Yeah.
Okay, cool. Thank you.
Yeah.
Thanks again. Our next speaker should be in the room. That's Yuki Chen from CU. Yeah, 12 minutes. I'll stand up at 10 minutes. 2 minutes.
Okay, sure. Good afternoon, everyone. My name is Yuki Chen. I'm an assistant professor in the CS department of CU Bodo, and happy to be here today to present our multi-LLM agent system design for the CESM rewriting. If I start, I need to state that all the things that I'm going to present is from the perspective of computer science. I'm not an expert in the earth science and atmospheric science. And this is a joint work with contributors from 3 institutions. And they are Qinwen, Reitong, and Jianwei, my students from CU Bodo, Guanhong from University of Utah, Feng, Jesse, and Peter from NCAR. So CESM is working well. Why do we want to rewrite it? To be honest, initial motivation is not for scientific innovation, but just to deliver an SF program called SafeOSE. And the goal of this program is to improve the safety, security, and the privacy of open source ecosystems. And the CESM is a very good test bed because it's large, it's widely used, and it's open source. And it's scientific important. And our teams believe that it couldn't be more secure if we can somehow rewrite the Fortran a memory-safe, unsafe language into a memory-safe language, for example, like Rust, Python, and JAX. So we started writing. And during our writing, we somehow discovered that this writing might also be helpful with usability and future development, for example, for the numerical and AI integration. And our current scope is basically two writing cases. The first is for Cam5. The target is relatively conservative. We want to write it from function-based CPU only to function-based to Python-based and the CPU only. And the second case is for Cam6. The target is more ambitious. We want to write it from function-based CPU only to JAX-based and CPU GPU hybrid. And we do this with this agent design. I believe there's no need to describe the reason why we want to use large language model and when you to design the agents. And in this design, we use two models. One is the Cloud 4.6, another is GPT 5.5. And they are used for different purposes. What we observed is Cloud is better at complex coding tasks, so we use it for most of the writing and the validation. So you can see we have a loop here. We have a supervised agent, which basically is entry of the system. And the supervised agent will give the instruct the write agent to write rewritten version based on the original version and then submit it to the HPC, to the retro. And then the retro is going to run, execute, and give us results. And the result is going to the validate agent, which is going to validate whether it's bitwise identical, whether it's ensemble consistency. And then the validated agent report back to the supervised agent, and supervised agent will check and either determine to continue the loop until the supervised agent is satisfied, and then once it is satisfied, it's then going to submit and give it to another agent, which is called review agent. And this agent is powered by the GPT, because GPT have a totally different perspective from the cloud. So we can use GPT to somehow complement the limitations of the cloud. And finally, the GPT is going to submit, the commit agent is going to submit to the GitHub. So, I mean, agent design is always about two things. So the first is harness engineering, another is context management. So here we use a memory agent for the context management. So memory agent, they basically maintain short-term context, long-term context. Short-term context, basically this context is going to keep reminding the supervised agent that what's your current goal and what's the long-term goal, and you shouldn't divide something like that. And we use GPT for memory agent because GPT is slightly cheaper compared with the cloud. Okay, so the results. The good thing is the model can write 99% of the code from Fortran to Python. I think it's not surprising at all. And the second good thing is like we can achieve bitwise identical for tested code base. The reason why we can achieve it is whenever we find if we cannot achieve it, and then we call back to the Fortran. So you can see on the right side, you can see we have a diagram showing how that code looks like. It's a basic ARIA architecture. So the entry is still Fortran for compatibility to make the CAM be compatible with other modules. But most of the code is right now written into Python, but we still have some Fortran callbacks here just to make sure it's bitwise identical. And we don't see any performance degradation. The reason because we're using Coden. So Coden is able to compile the Python into executable binary, so it's have the same performance as the Fortran. And our approach is bottom up. So instead of trying to write the entire CAM at once, we start from the lowest level physics and chemistry routines, and it allows us to do iterative validation. And the whole writing continues until the outermost Fortran wrapper is all written into the Python. So the ARIA becomes the real. The outsidemost is totally replaced, and then we stop the writing. And you can track the progress on this dashboard. Maybe I can quickly show how it looks like. Maybe I move.
Yeah, we can drag it up.
Drag up.
To the right.
Oh, to the right, okay. Right, so this is the current progress. We have touched 1,400 files, including 21 lines of code. And some is still native. So native basically means is Fortran callback. And the partial means like is a mix of Fortran and Python. So you can see the state, for example, down here is basically means all these subroutines are already being rewritten. The coverage basically means like we have already, during our testing, we have coverage so many lines of code. And this dashboard even provides a formula which is give you some, I need to say again, I'm not an expert in this area, so I don't really understand all these formulas. But this view gives you another view how it looks like. For example, the code to compute these items, this item in the formula is already done, and this the code to compute these items is partially done. So you can use this dashboard to track the progress. Maybe I need to speed up a little bit. Okay, and the bad things. The devil is always in the remaining 100%. For example, if you want to achieve data-wise identical for all the code, it's sometimes it's very hard because for untested code base, you cannot say that, right? So we need to keep testing, keep using more comp sets and using more different inputs until finally we saturate the input space and the observed behaviors. And another bad thing is the model sometimes will make subtle but fatal mistakes because it's autoregressive nature. So for example, sometimes the variable is just omitted by the model, and sometimes the code in this branch is mistranslated. So for example, in CAM6, so this is a macro. This macro is actually not defined at all in CAM6, but the model will still think, okay, it's the code in this branch is used, and then the model is going to do the translation. So finally, the target code base, well, including some code that is not part of the CAM6. And we also observed that the errors will become more common as the semantic distance between the source and destination increases. So if you want to write it from Fortran base to CPU only, to Python base, CPU only is not that hard. But if you want to finally write into the CUDA level and GPU accelerated, the model will make more and more mistakes. Another bad thing is the floating point is always very annoying. So it's a persistent source of the debugging noise. So some examples here. I believe you are very familiar with these examples during your own development, right? For example, this formula, I mean, mathematically, they should be equal. But when it's computing the floating point, it's actually not, right? And this implementation of the power calculation in Python is actually not equal to the V times V. And sometimes the Fortran will have some optimization that is specific to one compiler, and you cannot replicate that in Python. And when you translate it to a GPU, the thread scheduling is non-deterministic in GPU. And then finally we'll give you different results because A plus B is not equal to B plus A in floating point calculation. Right? Okay, and the ugly part. Right, so we observed that when you write the code to the GPU-based, of course, GPU is faster than the CPU, but the data movement between the GPU and the CPU becomes new bottleneck. So in this example here, we run this first comp set, and the time for the GPU, it takes 3,000 seconds to complete. And for GPU, it's also 3 seconds to complete, okay. And if you're going to analyze these subroutines, and you can see, okay, so the kernel, GPU kernel run is much faster than the CPU, but the data movement takes almost the same time as the computation itself. And some other ugly things, for example, the larger the model will have some hallucinations. It says like it's bitwise identical, but actually the model doesn't run the code in the target HPC environment at all. So you need to do the instrumentation and monitoring. And the last ugly aspect is the frontier model is very expensive. So currently our cost is 2 cents every lines of code, so which basically is $200 every 10,000 lines of code. If you consider the CAM or the entire CESM, it's almost a million lines of code to complete the rewriting. So our next step is we are going to improve this agent design, right? So we are going to include more comp sets, more production simulations, and more inputs to improve the testing coverage. We want to use neurosymbolic reasoning, some formal methods that can identify the fatal mistakes before submitting to the HPC. And we want to embed some domain expertise into the review agent to aim for the ensemble consistency. And we're going to model the data movement between CPU and GPU as a combinational optimization problem and solve it using some solvers. Right? And instrumentation to deal with hallucination and try some open source models to reduce token cost. Okay, maybe I should skip this page. So this page is talking about some security issues that we find in the code base, in supply chain, and in the HPC environment. We have already reported all these security issues to CISO and also to NSA. Hopefully they can solve it. Okay, so this is the last page. Some useful links. So for example, this is our repo for the Python CPU version for Cam 5. And the feedback are very welcome, so help us to improve. And this is a website to track the progress, and this is a Google Docs that list all the bad and ugly cases, very detailed cases, which might be helpful. I can take questions.
Are there any questions? We probably have time for one. Yeah, come on up.
Yeah, thank you very much for the nice talk. I was wondering for your agentic model system, did you use the supervised agent as to create the definition for the agent system, or did you also write the definitions or markdown files for specific reviewer agent, coding agents, or things like that in your system?
You mean for the implementation of the system?
Yeah, exactly, in this figure. So yeah, this one. So for example, validation and rewrite agent, did you ask the main agent to create those sub-agents, or you had like definitions for specific agents?
So half and half, right? So we have the design in our mind, and we implement some of the Python modules to implement these agents, and sometimes we ask the cloud to rewrite some the agents to solve some bugs. So half written by human, another half is written by the cloud itself.
I see. Thanks.
Thanks, Ian.
Okay.
Okay. And our last speaker is Ren Stengel, and I will get this going. So I'll stand up for 10 minutes and you have 2 more minutes.
Okay, great. Hi, I'm Ren. I am a postdoc currently in CISL. And today I'm talking about utilizing CAM Fortran physics in the E3SM C++ atmospheric model, and talking about evaluating the feasibility of language interoperability for atmospheric modeling. So really briefly, some of the motivation for this work is that there's been a lot of ongoing and past projects involving code modernization and different approaches to do that. So we have CCPP, which aims to provide interoperable physics written in Fortran. We've also seen Earthworks, which has focused on GPU enablement through OpenACC directives. StormSpeed, which is integrated performance portable Cocoa C++ for the dynamical core. Right, and then we've heard today there's a lot of interest with JAX. And so code modernization efforts all have different goals, all of which are important, and it's difficult to merge them all together. But so one of them, of course, is complexity containment. We also obviously have talked a lot about physics package portability. It's nice to be able to run your code on different systems. And then GPU enablement is obviously also a very, very big factor here. And so right now in sort of the more modern language realm, we mostly see industry support for Python and C++. And we've been seeing, unfortunately, decreased support for Fortran and decreased support from that for Fortran on GPUs. I'm also like a recent PhD graduate, and I never used Fortran before. And so a lot of the newer workforce and students are not really learning Fortran as much. And so, right, a lot of people are relying on Python a lot more. And so the aim of this project is mostly what does multi-language support look like in this community? And so as I mentioned previously, we've had StormSpeed, which uses a C++ Cocos dynamical core inside of a Fortran application of CAM. And then this project is sort of the inverse of that, where we have a Cocos C++ application from E3SM, and we're porting in Fortran physics. And so sort of the overarching theme of this for me is how do we take all of this work that other people are doing and glue them together so that all of these different projects can play nicely together. And so the E3SM is the Energy Exascale Earth System model out of DOE, and it's their Earth System modeling framework. And the goal is to provide an exascale simulation capable framework. So we're going to focus on the atmospheric component, which currently supports language interoperability for parameterizations in physics, and more recently now also includes support for bridging in machine learning emulators. But it is hardware portable and performant on GPUs because it relies on Cocos, and it also has a lot of built-in performance metrics, as well as some very extensible and customizable logging features, which is really nice. And so sort of the overall interface with EMXX is we're using the standard XML change functionality that a lot of us are familiar with to change ComSet grid, set up compilers, machine, blah, 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 all of that jazz, setting your runtime and time stepping, everything that we're familiar with. And then they also use a similar version specifically for the atmospheric component, which is ATM change. And this allows us to change atmospheric process settings. And so I'll show an example sort of how this works in a minute, but basically I don't have to write a new driver if I want to change my parameterizations that I want to use. And so that's really nice. And so we've seen similar approaches with CCPP, which is used by CAM-SEMA, which uses an XML file to determine atmospheric process settings and then generates the code from that. And so the way that this ATM change feature works is we go through like our config, and then it creates runtime config for us, piles everything, and composes our EMXX commutable. And so if I wanted to change my processes for the atmospheric portion of this, I can just set the list in the order that I want with one line. And then if I want to change it, I can just kind of do whatever I want. And my disclaimer on this slide is I'm not an atmospheric scientist by any means. So please don't come at me if this is like the most obscene atmospheric condition you've ever seen. But the point is here is that we can change things very easily. I don't have to write a new driver. So that's really, really nice. And we can also use the ATM change to set our logging settings, topography files, initial conditions, all of those sorts of things that we need for our atmospheric simulation. And then EMXX does also sort of provide a lot of, for lack of a better word, automation and sanity checks for us. So it handles grid management and time stepping. Pre and post condition checks are available to us. So that's what the screenshot is here of. We're checking to make sure that different fields are within the range that we're looking for, and also maybe don't have any NaN values. And so that's just like a nice sanity check, especially for someone like me who has effectively no scientific knowledge in this realm. And so I can still make sure that we're not getting values that are like physically like insane to get. The other thing that's nice, of course, is that it offers file I/O for us, and also handles passing the fields between processes for us, so we don't have to deal with that. And so, in short, the way that we would add a new parameterization, it's just at its core 5 different functions that we have to create. So there's a constructor and like a cleanup finalize function, which are generally empty depending on what you need. Set grids, the name has actually changed since I made the slide, so sorry about that, but we're just defining our fields and our grid layout. And then for initialize, right, we can create our field checks for pre and post step checks. And we can also initialize anything that we need to, and then the run function obviously runs our physics for us. And so sort of our proof of concept toy example here is just a identity function that I was told to name this parameterization after myself. But all we're doing is multiplying pressure and temperature by 2, and then we're dividing by 2 again. So hypothetically, nothing should change. And this was just to figure out how to operate within this, this framework. And so we started out just doing that with C++ and Cocos, and then we've also set up a Python bridge, and then we also have a Fortran bridge. And then one of the more exciting components of the Fortran bridge is that we have it working with a OpenACC ported version of the Fortran code as well. So we'll go through this a little bit more in a minute, but we don't have to copy data back and forth between the CPU and the GPU in that case. And so for the Cocos version, this is just like the most high-level example of basically what's going on in each of these different functions that form our interface, right? And so we're just grabbing our temperature and pressure variable from the physics grid. I didn't have to do anything to initialize anything. And then we're grabbing those specific fields again and then doing our identity scaling. And so with the Python, it's basically the same thing, except we're going to use a Py module. And so within initialize, right, I do call a function from Python called initialize. It doesn't do anything. And then for running it, again, we're calling another Python function that does our scaling for us. And so integrating with the Python script is incredibly easy with this. For the Fortran code, it's a little bit more layered of effectively we're doing the same thing, except we have to create a C-bound function. That's our bridge code that then calls our actual Fortran code. And so again, right, we have the middle blue color is a C++ code that's then calling a C-bound Fortran code, which from there we can call whatever Fortran we want to. And so a few things to note is that C++ and Fortran have different data layouts, which means that we always have to transpose our fields when going to and from Fortran. We did, again, get this to work using OpenACC Fortran directives, which is really nice because we don't have to copy stuff every call between the CPU and the GPU. And then the thing that's really nice with this framework is that we can bridge directly into existing code from other repositories. So anything that has like the modular structure, we can just bridge directly into, which is really nice. And so we extended the little Stengel parameterization to Kessler, which is just a really small microphysics parameterization, and it has been CCPP enabled. And so it's about 780-ish lines of code, including the meta files, and then the CCP generated version of that is on the order of thousands of lines of code. The EMXX bridge that I wrote was about 1,200 lines of C++. At the time when I put that in there, I had a lot of debugging and comments and whatnot. And then there's about 80 lines for the Fortran bridge. And so it took me about 2 months to get the Stengel parameterization figured out and sorted. And then it's taken about 3 months for the Kessler port. And a lot of that was mostly just lacking domain expertise for me personally. And then fine-tuning the OpenACC version of Kessler took a little bit of time. And then since it's 4 o'clock, I thought it would be a great time to throw a bunch of numbers on a slide. So really briefly, I know we're low on time, but for the hardware side, what side is that? Left side of the slash is where EMXX is running, and then the right side of the slash is where Kessler is running. So CPU means everything's on the CPU. If I have GPU/CPU, EMXX is on the GPU with Cocos, that whole thing, and then the Fortran is on the CPU. The last 4 lines all have OpenACC directives added into them, but then these are different Cocos backends. Based on these numbers, there's not a significant difference between which Cocos backend we're using. But these are sort of the very initial results that we've gotten. I don't have a lot of time, so if you want to talk about this later, I'd be happy to talk about it. And then we did do some performance comparisons to storm speed. The one thing to note is that the very bottom line with the 10-day GPU, I actually had a typo in the script, and that's also 1 day, which is why that like magical scaling exists. That's not true. But one thing to note of interest here is that overall, our EMXX ports are faster for 1 day at least, but also our power numbers are, depending on where we're running, right, they're relatively close to storm speed as well. And then for actual memory usage, we're using about the same amount of memory regardless of where we're running. So those Fortran transposes aren't actually adding that much to it, which is nice. And then the thing that I found interesting was that if we look at virtual memory, EMXX is not really using anything, but storm speed is actually using quite a lot. And so we are seeing at least memory performance improvements with EMXX in this case. So really rapidly, next steps, we want to look at a more complicated physics package. So we've been talking about using Club. We'd also like to explore more of the bridge functionality. So we've talked about Python and JAX. I have a particular interest in Rust. There's also been discussions of using LLMs to help with automating that bridge code generation and help try to reduce the domain-specific knowledge required to do these things. And then also, we've talked with like Iris about translating Fortran code potentially into C++ or Cocos, and then obviously extending our performance study to include larger grids and more in-depth analysis on what's going on between EMXX and storm speed. So that's all I have. If you're curious about the code, I do have some branches available on GitHub. And then this has been supported through the community software facility. And then some notable call outs to people outside of the group who have been very helpful. So thank you.
So we have time for one question. We're 2 minutes past the hour, but we started like 5 minutes late. And I blame that on the fact that you all came in from break late. So if there's a question, take the mic. If not, we should thank all our speakers again. And also thank our AV help in the back of the room. Thanks, this went very well. I don't think I have anything else other than oh yeah, thank me. And we will see you at the winter meeting and then again next year.